Okay, so welcome everyone. We meet in strange times. The world feels more volatile than usual. And in moments like these, I think it is grounded to gather and focus on the steady, impartial clockwork of science. It's been over 10 years since the RMS software was conceived. So the first lines of code were written on Sunday, May 10, 2015. And I wanted to celebrate this big occasion, but life got in the way. And back then in 2015, this project was just an idea, a few lines of code, and a budget of exactly zero. We approach this project with the philosophy of science for everyone. And if there's one thing that we've proven, and that's that science is messy. We're working at the absolute edge of knowledge, often in total uncertainty. We're thought to expect aha moments, but those are exceedingly rare. And most of the time, it's just noise, debugging, and a slow grinding process of figuring out what is going on. That is where the power of this group comes in. The GMN has been a massive learning experience for me personally, and our global approach doesn't just give us coverage of the night sky, it gives us the coverage of the human mind. The open discussions that we have here unearth our biases and force us to see perspectives we hadn't considered. You help illuminate the unknown unknowns and expand the edge of our knowledge in ways that I could never do alone. We started with nothing, free software, cheap hardware, and volunteers. And that scarcity is now our greatest strength because we rely on passion rather than grants and large infrastructure. We are extremely resilient. There are no funds to cut to make the GMN go away. We are here to stay. The main idea behind this meeting is to provide an overview of our impact, but also to look outward. We have invited speakers outside the GMN who are doing incredible science, like to work in meteor spectra and killer asteroids, to talk about their work. We want to learn from you. As per established tradition, I also want this meeting to be a safe space for criticism. In fact, I prepared a little presentation about the criticisms. And for those of you who watch Seinfeld, you might be familiar with Festivus. So consider this meeting our airing of grievances. If there are things that you don't like or things that could be better, we want to hear it during the discussion sessions. Do not hold back. And I want to end with gratitude. A conference like this is inevitably a dog and pony show of the latest results. We're going to see amazing things about contrails and drone-assisted meteorite recovery in the next session. But it's critical to acknowledge the people who are working in the background, not presenting today, or just starting out. Our journey of 1,000 miles begins with a single step. And some of you are there. I commend everyone for your dedicated work, and we have confirmed over a dozen meteor showers. We helped recover 4 meteorites, including the 2023 CX-1 impactor. We're observing unique events. We're currently standing by to observe the sudden brightening of the star T Corona Borealis. Our data has been used in over a dozen scientific papers, enabling science that could not have been done otherwise. Thank you for being a part of this. All right, so we usually start these meetings with a round of introductions. And usually I set the introductions to only 10 minutes, but because there are so many people who want to introduce themselves, I expanded this time to 15 minutes. So I'm going to start with myself. I'm Dennis. I'm a research scientist and a research professor at the University of Western Ontario here in Canada. I like meteors. All right, so who would like to go next? Please raise your hand in Zoom, and I'm going to call you out and just quickly introduce yourself to all the members, all the new members, the returning members. All right, so here, go ahead.
Hi, everybody. I am Zuhair Ben Khaldoun from Morocco, indeed, and now at Sharjah University at the United Emirates Arab. And we hope we can extend the network to the EAE. We will discuss about that. And we are to expand the network in Morocco as well. We already have 3 cameras, and we already scheduled to have 2 other cameras the next month. So I am happy to be with you, and as Denis said, we can do a lot of exciting science with this network. Thank you.
Thank you so much for here. Okay, Will Joy, go ahead.
I'm Will. I'm a citizen scientist with a very big interest in meteoritics and recovering meteorites for an academic principles and procedures. Background is mining, a bit of drilling, and looking at sustainable interests for both now. So that's me. Thank you.
All right, thank you, Will. Jamie.
Hi, I'm Jamie Shepherd from Scotland. That's a real painting behind me, not one of these computer backgrounds. And I've been a meteor nut since I was a kid, studied astrophysics at university, became very fascinated by orbital mechanics and the whole analysis business. And after 50 years, I've found a second life doing trajectories and dark flights and all that stuff. I'm an analysis fiend. I just love it.
Thank you, Jamie. All right, and we have Edward Cooper. Go ahead.
Hello, I'm Edward. I'm in Wales in the United Kingdom. I've got 16 cameras that I look after. Only 2 of them are immediate to me. All the other 14 are remote. About 7 of those are either in schools or public spaces where they're gathering data for outreach to education. And I've been monitoring meteors since 2015, I think, and so that's me.
Thank you, Edward. All right, Justin.
Hello, my name's Justin. I'm a second-year student at University of Western Ontario. I worked with Dr. Vida this summer writing some software for RMS. Some other work I've been doing is some sub-millimeter astronomy stuff, but I'm relatively new to the meteor game.
Thank you, Justin. All right, Nedim, go ahead.
Hello, everyone. I'm Denis from Boston. I'm coordinating small and growing network in Herzegovina's new country on China. Cameras so far much future. I'm so glad to see you all here. I watched all previous conferences, so I know all the faces, all faces. So I'm glad to see you in real time.
Thank you so much, Nen. All right, Stuart, go ahead.
Good evening, everyone. I'm a retired computer programmer, but I have a large interest in amateur radio, electronics, and astronomy. So this is a sort of a natural extension. I'm recently set up a camera, just I think about 4 or 5 months ago, and been monitoring. So it's all very exciting for me. Thanks.
Thank you, Stuart. All right, and then we have Tone.
Hello, everyone. My name is Tomek Walesiak. I'm from Poland. I'm independent researcher specializing in impact craters, but also in physics of meteors, stream fields, meteorites. Last year, I managed to calculate a stream field of Drelov meteorite. the initial parameters was given by Skytina network of meteor cameras, which is working in Poland. I wanted to help and revealed calculated data, and thanks to this, first meteorites were collected. So I was part of this success. Currently, I am building also my first cameras because I would like data to have better availability of data, because Skytina is a little private project. I really appreciate your materials, your knowledge, which you are sharing. It's nice to meet you. Thank you.
All right. Thank you so much, Tomek. All right, and we have Gino.
Good evening, good morning. My name is Regina. Oh, somebody else wants to
Sorry, it was a misunderstanding. Sorry.
Okay, no worries. So my name is Regina Rodawska. My background is a scientist, now currently mixed with a little bit software engineering. I work for planetary defense at ESA, so I'm supporting that group. But for the sake of this meeting, I'm going to giving a talk in behalf of Meteor Data Center that I'm still part of. That's my core, let's say, of my background. So meteoroid streams, they parent bodies, and yeah, on the site, whatever the things are for ESA at this point as well. Thanks.
All right, thank you, Regina. And now let's go to Gino. Oh, if you're saying something, you're still muted. All right, it appears that he might have.
Sorry.
Oh, go ahead.
Sorry.
Yeah.
I didn't had Zoom until now, and I just logged on. I'm new. I'm from Romania. I think I have from 1 month a new GMN camera pointed at west, and I'm glad to be a part from this community.
Thank you so much, Gino. All right, and then we have Mr. Rothier.
Hello and welcome. We are a high school in Germany, specialized on natural science. And as a teacher, I supervise the project, but the students do the work real. And today is the first day of the winter vacation here. And they are voluntarily here. And one of them introduce ourselves.
Hi. I'm Leonard, and I'm one of the students. We are 3 students, and we try to place the camera to see some meteors in the school. So we'll try to get that done, and yeah, we'll be happy to see what you've prepared in the presentation. So thanks. That's it.
All right. Well, thank you so much, Leonard, and the company there. All right, and then Hervé, go ahead.
Hello, Denis. Hello, everyone. So I'm Hervé. I work at the Belgian Institute for Space Aeronomy in Brussels, Belgium. I'm mostly interested in radio or radar observations of meteors, but I also like to participate to optical networks such as GMN. So I'm running 10, 12 cameras now. I think I lost track in Belgium. Which are complementary to our observations, but I also started 2 years ago now collaboration with Zoer in Morocco for a small network in Morocco.
Perfect. Thank you, Hervé. Alex, go ahead.
Hello, everyone. I hope you can hear me. My name is Alex Tudorica. I'm originally from Romania, but I live in Germany for quite some time now. So if anyone needs help around Berlin with setting up a camera, I could lend a hand. My background is in observational cosmology. I did my PhD at the University of Bonn quite some time ago, and then I moved into data science and software development consulting. And missing science, I joined the Global Meteor Network, and I can say that I'm quite positively impressed. And I will show you my work for the past 2 months and I'll talk a bit later.
Amazing. Thank you, Alex. Paul, go ahead.
Hello, my name is Paul Rogemans. I'm from Belgium, and I'm busy with meteors for more than 50 years now. Since 2 years, I am retired, and that means I have finally more time for meteors. My main interest is meteor showers, the composition of meteor showers, the structure of meteor showers. And for all this stuff, Global Meteor Network is providing the best data I can say I could find so far available to do this study. So I'm curious to hear what others have to say here.
Thank you so much. And then Pavol, go ahead.
Hi everyone, I'm Pavol from Comenius University in Bratislava, Slovakia. I'm a researcher and I'm mostly focusing on meteor spectroscopy, so I'll be giving you a short talk about that.
Thank you so much, Pavol. All right, and Patrick.
Oh, you hear me?
We can hear you.
Hi, my name is Patrick Shober. I'm currently a postdoc at NASA Johnson Space Center in Houston, Texas. But I did my PhD with the Desert Fireball Network in Australia. And then I did a postdoc with the Football Network in France. And now I'm here in Texas. So I've been hopping continents, but in the last 4 years. And I do research on fireballs and meteorite dropping fireballs. But I'll be giving a talk later today about the work that I did while in France. Thanks.
All right, thank you so much, Patrick. And Razvan, go ahead.
Hello, everybody. My name is Razvan Orbu. I'm from Bucharest. I'm a member of Astro Club of Bucharest. My background is IT. I'm working in cybersecurity. And in astronomy, I'm doing astrophotography, spectroscopy, solar imaging. And since December, I have 4 cameras on my rooftop hunting for meteors. That's on me.
All right, thank you so much. Chloe, go ahead.
Everyone, my name's Chloe. I'm a second-year PhD student at the University of Manchester, so I'm pretty new to meteor physics as well. My background is I did my first degree in physics also in Manchester, and I'm super interested about what everyone's working on, and I can't wait to hear your talks.
Thank you, Chloe. All right, well, I don't see any other raised hands, so I'm just going to call people out. It's just how it's going to be. Damir, go ahead.
I have a feeling that will happen. Hello, everybody. My name is Damir Shagon. I'm in meteor astronomy, well, for I think as long as Paul, so about 50 years. Long journey. On the road, I stumbled on some CCTV cameras a long time ago. Started with Croatian Meteor Network, and it ends like this. Hopefully, everyone from you having similar ideas will have the outcome of the kind. Welcome to everybody, and wish you will have a nice time, as we all do for quite some period now.
All right, thank you, Damir. And Mark Severance, go ahead.
Hi, good morning. This is Mark Severance. I'm new to the New Mexico Meteor Array through Pete Eschman, and got introduced to the whole network via the Society of Amateur Radio Astronomers. I live in Alto, New Mexico, at about 7,100 feet. Excellent seeing conditions. That's about 3 hours south of Albuquerque, for those not too familiar with the geography. I'm a retired NASA engineer and manager, spent 30 years in human spaceflight operations, been involved in a number of citizen science projects over the years, satellite tracking, radio astronomy, weather ops, and so on. I'm also a W5ASR licensed amateur radio operator. I've been reading up a lot on what the GMN is doing, and this is really impressive science. I was talking to Pete about it. It's absolutely professional grade, and you guys are just awesome in what you've been doing. I'm bringing my first camera online here in the next week or so, and hope to evolve into a 6-camera system here in the not too distant future. But it's really a pleasure to be working with you folks. Thanks.
Thank you so much, Mark. All right, Jürgen, go ahead.
Hi, everybody. I'm Jürgen from Germany. I've also, like Paul, been observing meteors for decades. Actually, my first observation was done in 1972. And so I follow the evolution of meteor showers and try to combine data from different techniques in order to make sure that the structures we try to identify are real ones.
And that is also the connection to the GMN data. We started to analyze a few things about the Leonids oocytes, which I'm talking about. But I'm also interested, of course, in all other phenomena around the meteors. I was also hunting the Røbæk meteorite in 24 and luckily found one piece. And so that's things which keep my fascination for that.
Thank you so much, Jürgen. Pete Ashman, go ahead.
Hello, I'm here in New Mexico. We started out with GMN, I was looking just now, in about August of 2021. So we've got about 30 cameras in the New Mexico Meteor Array, and we're looking to add another 16 more within the next couple of months, trying to fill in coverage in part of the state. So I've been interested in astronomy for a long time. I'm a retired field archaeologist. Used to work for the university here in our contract archaeology program. But I do recall many years ago now, a really awesome display of the Leonids that we saw here in Albuquerque. And it's just been a source of interest for me for a long time. I look forward to hearing from all of you today, and let's keep doing some real science here.
Thank you so much, Pete. All right, Rob Steele.
Yeah, Rob Steele. I'm in Fraser Park, California, which is well, we've got nice sky viewing. We're located about 5,500 feet in elevation here in California. I was a retired software engineer, spent 30 years at the Jet Propulsion Laboratory. If I think back to it, I built my dad and I built my first telescope when I was 15. I think we started on the project when I was 14, which was 60, a long time ago. And so I'm still doing amateur astronomy, working with a high school. We've got 2 cameras currently running. One's coming online, working with some students, and really interested in hearing the talks. And really enjoyed being part of this project for the last several years.
All right, thank you so much. And Jessica, go ahead.
Hi, I'm Jessica Klusmeyer. I'm in New Mexico State at the university, and a part of my dissertation work will be looking at meteor flares.
Thank you, Jessica. All right. And I don't see anyone with their hand up. So Luke, go ahead.
Hello, I'm Luke. Live in Phoenix, Arizona. I'm kind of a newcomer to GMN. I think I discovered GMN less than 3 years ago. And I'm responsible for dragging Denis and the network into the contrail field. My background is I'm an airline pilot. And yeah, and I've been helping with RMS, with the code.
Perfect. Thank you so much, Luke. And I believe this is our time. There might be more opportunities to introduce yourself during the breaks, but let us start with the first talk. So Pavol Matlovič is going to tell us something about meteor spectroscopy. I know this is a topic of interest, and people have asked previously to hear more and learn more about spectroscopy. I am far from an expert, so what I decided to do is to call an actual expert to tell us something about meteor spectra and spectroscopy. So, Pavol, go ahead.
Yeah, thank you. I hope you see everything correctly. So thank you for inviting me, and thank you for calling me an expert, Denis. That's very very nice of you. So yeah, I assume this is not a topic often discussed at these meetings, so I will try to give like a more general overview of what meteor spectroscopy can do and how we can use it to study the composition of meteoroids, and just give you some results from our research in the past few years using meteors. I also using laboratory meteorite ablation data that we used for some experiments. I will go maybe quickly through more things, but feel free to contact me or ask me more about whatever you find interesting. So it's a topic I've been working on with my team. We operate a network of cameras called AMOS, most closely working with my two students, Veronika and Adriana Pisarčíková, who also focused on spectroscopy. So, as you know, when we observe meteors, what we see is a hot cloud of plasma that's emitting light, and there's a lot of excitation, ionization going on, which creates photons at specific wavelengths, which we can then trace in the spectra as spectral lines of specific atoms, giving us some information about the composition of the original meteoroid. It's not so straightforward, so there's some obstacles to actually connect the composition of the plasma that we observed with the composition of the original meteoroid, as I will discuss, but it gives us a very interesting imprint of what the body is like. It's quite an advantage compared to, for example, asteroid spectroscopy, where we only observed reflections of the sunlight from the surfaces. We have the actual ablating material from the meteoroid. So we look at the night sky, we wait for something to fly by, and if you have a diffraction grating on top of your lens, you can see something like this from our systems. So besides the meteor itself, you also have its light diffracted in the visible wavelength range, and you can see these imprints of different chemical elements that we can study. Usually we focused on visible range, so if you would have a color camera like our colleagues from Czech Republic, you would see something like this. You would still have to correct it for the color sensitivity, but it looks very nice. But then we go back to these black and white spectra and we measure intensities of these different lines and try to figure out the composition. I try to come up with a short overview of the different spectral instruments that I'm aware of. I'm sure I'm missing some. This is just from some of the recent publications of meteor spectra. And this is just to basically give you an idea of the typical instruments that are used. Usually it's a very simple optical spectrograph. So using a camera, wide field lens, and on top of the lens, there's a transmission grating that just diffracts the light into the spectra, usually all of them operating in the visible range with a little bit oversight to the near UV. So this is what we will be talking about today. And there's an alternative approach by your colleagues from the Western University who are also trying their very interesting tracking system to also observe spectra of very faint meteors. So this can give us some information about those very small meteoroids that not usually are studied using spectroscopy. So the instrument that we are using, it's called AMOS, and it looks typically like this. So there's this large system, which is an intensified all-sky camera used mainly for dynamics and studying some physical properties. So we have multi-station observations, and each system is also linked with this smaller camera, which is a spectrograph with smaller field of view. It's approximately 60 by 45 degrees of the night sky right now. At some stations, for example, in cooperation with our friends in Australia, we operate more spectral cameras to cover potential meteorite falls. It's actually a global network, not as populated as the GMN, but we have some nice stations at good observatories around the world. And I would say that probably the most unique thing about it is the combination of these instruments to provide this complex set of data for each of the meteors that we observe. So combining the dynamics, the physical properties, and the emission spectra. All right, so and why are we interested in this? From my point of view, there's many reasons. As soon as you realize that there's actually so much unknown about the composition of these minor bodies, and it's very difficult to study the composition of meteoroids, you can come up with many interesting open scientific questions, and then you can pick and choose what your interest is. For me right now, it's just trying to figure out what actual diversity of meteoroids in terms of composition is, compared, for example, to the diversity of meteorites that we have on Earth. We also spend time on studying the presence of water and organics in meteoroids, study the effects of space weathering and how the composition of these bodies is affected when they go very close to the sun. And you can also study, for example, spectral properties of meteorite streams, try to connect them with the parent body to say something about the composition of their parent asteroid or comet. There's many different types of studies you can do once you start doing spectroscopy, which I recommend. Right, so some basic information about the spectra. So what we see actually, and we believe that meteors have, are two spectral components. So one, we call it the main or low temperature spectral component. Its temperature is around 4,500 Kelvin. It's from the main plasma around the ablating meteoroid and consists mostly atomic lines of the main species present in these meteoroids from the destructed minerals. For faster meteors, mostly cometary, we also observed a high temperature component, which has a different temperature. We believe that it's formed in front of the body, near where the shock wave forms. It can have temperatures of around 10,000 Kelvin, and it consists, for example, lines from the atmosphere, like oxygen and nitrogen, but also some interesting ions, and also this hydrogen line that we use to study the presence of water or organics in meteoroids. So already starting to kind of see that the spectra not only depends on the original composition of the meteor, but also the conditions that we observe the meteor at. So the plot here shows how a spectrum can look like. This is actually not a typical spectrum. This is a very interesting meteor that I will discuss a little bit later, but you have some idea of what the data that we work on look like. So as I said, the main thing to remember, the spectra are not just affected by the composition of the meteoroid, but also at the conditions that we observe, this bright cloud of gas. So depending on the speed and the brightness, you can have different temperature of the plasma, which affects the amount of line intensities that we see. And it's also important to remember that the plasma composition that we can infer from these observations is not exactly the same as the composition of the meteoroid itself. From modeling the spectra that we study, we believe that the spectra or the composition of the gas is more rich in volatile species, and it's less enhanced in the refractories like calcium, aluminium, titanium. And we believe that this is because some of these species are not evaporating completely from the meteorite during the ablation process. And data resolution matters. It's not a very profound conclusion that I found, but in spectra, I think it's very evident when you look, for example, at this comparison of a typical spectrum that we get from our AMA system compared with a very high resolution spectrum of ablated meteorite studied by an Eshel spectrometer. Here directly, if you're losing resolution, you can just lose some minor components, some lines that you cannot study because they get blended with some stronger lines, and you can quantify actually what elements, for example, you're missing, and you cannot study if you don't have sufficient resolution. You can still get very interesting information with low resolution spectra, but you cannot study everything about the composition if you're missing some of these species. So if you saw some papers already published on meteor spectra, you may have seen plots like this. This is or used to be one of the most common studies done by meteor spectra, because you can do it even if your meteor spectra are low resolution. So the main species that you can observe even in low resolution spectra present in almost all meteors are magnesium, sodium, and iron. So there was a spectral classification method proposed by Jiří, which plots these kind of ternary diagrams when you have three corners of this triangle, where the more of these species, the sodium, magnesium, and iron you have, the closer you are to the edge of this triangle. And you can kind of classify the differences between different meteors. And it can be used efficiently to identify, for example, pure irons or meteorites that are depleted in sodium or have low iron. But most of them will fall somewhere in the middle of this diagram, and you cannot actually distinguish like very detailed specific types of material or classify the composition exactly. But it gives us some interesting information. So we also did a survey of these medium-sized, centimeter-sized meteorites using this method. Ideally, if you can combine your spectral observations also with orbital data, you can study how, for example, on the plot on the right, the ratio of iron to magnesium changes with the dynamical origin. So you have the different parameter above 3 are for asteroidal meteoroids, which typically have more iron than the cometary ones, which are in the white region. So this is just an example of what many people that are doing spectroscopy try to study. We also use it, for example, to qualify some average spectral properties of some streams, just based on these three species, or, for example, on the plot on the right, you can also study the effects of space weathering. So for meteorites that have perihelion distances very short, they go very close to the sun, we observe that they are usually depleted in volatiles like sodium, which is a direct effect of the fact that they get heated and they lose these volatiles. It works not only for sodium, but for example, also for hydrogen. Okay, so these are some examples of what is frequently done. What we also did, and I'm not going to discuss it in detail, we published a couple of papers on it, is to study, for example, the water and organics content in meteorites by studying the emission of hydrogen and the CN band. We studied it in a meteorite spectra. I will discuss this experiment a little bit later, but basically we already showed that when you study the intensity of hydrogen and CN, they directly correlate with the original contents of hydrogen minerals and organics in these meteorites, and they also correlate between each other. So you can directly identify meteorites, for example, that are rich in water and organics this way. So we did a brief survey and showed that cometary meteorites have stronger emissions of hydrogen. And we also saw some stream meteorites containing these species like Taurids and Geminids. And now recently there was an update by our colleagues from Czech Republic. They also did a similar study looking at hydrogen in their survey. And they basically showed similar results. And very interestingly, they also showed that it seems like the abundance of hydrogen in these large cometary meteorites might be even higher than in those very primitive carbonaceous chondrites or Halley's dust. But obviously, this is still very new, and we will be definitely studying it in the future. But let's go back to the main question today, and which is how we can use this spectra to actually classify the composition of these meteoroids, for example, in comparison to the meteorite types that we have on Earth. So these low-resolution spectra and studies of sodium, magnesium, and iron, which I showed on these triangle graphs, can give very interesting science, but they are not sufficient to recognize, for example, ordinary chondrites from carbonaceous chondrites or these different types of materials. So to move forward, what we would like to do is obviously get a higher resolution spectra. It's quite important to also get some signal in the near UV, for example, between 380 and 400 nanometers, because there are some interesting species like silicon and the CN band present there. It's important to study also the minor components, and if you want to be actually sure about the composition of these bodies, it's better to also model the spectra by radiative transfer models and not just study the intensities of the lines, because they can be affected by the conditions of the meteor, as I mentioned. All right. So we know from meteorite studies that there are different types. And the population of meteorites is very diverse. There's a very different types of materials depending on what their parent object is. So we know that at least this is the part of the situation also in the interplanetary space, and this is already something that we are not able yet to distinguish fully using meteor spectra. And realistically, the situation is much more complicated in the space, because meteoroids not only contain these type of materials that survives atmospheric entry and it's found on Earth, but usually also different types of materials that are more fragile and they don't survive the atmospheric entry. So we need to find a way in which we are able to use the spectra to classify all these classes. So our effort in this was to kind of combine these meteorite measurements with the spectral observations. We did an experiment in plasma internal facilities in cooperation with the University of Stuttgart and the Natural History Museum in Vienna and other colleagues, where we tried to kind of recreate the meteors by ablating different types of meteorites and observing their spectra in very high resolution. We also observed it in a very wide range of other instruments to study the ablation, the fragmentation of these bodies, and other types of interesting science that can be used in meteor science. We published a special issue in Icarus on this, so around 10 papers on different instruments if you're interested, but right now I'm mainly going to talk about the spectra. So basically, we try to create artificial meteors in a lab by shooting hot plasma on them. It looks like this, so you can imagine that maybe if you're very close to a meteor, it would look similarly to this. There are, of course, some minor changes. The laboratory cannot, for example, simulate conditions which are similar to higher speed meteors, only very slow ones, but they are realistic conditions for example, slow asteroidal meteors. And we repeated this process for many meteors and try to figure out how their spectra, depending on the known composition of these meteorites, change so that we can use it for future studies of meteors. That would be for a longer discussion, so I just recommend you looking at this paper if you're interested, where we try to kind of classify how the different types of meteorites spectral properties are compared and what diagnostic spectral lines that we can use to identify different types of materials. So the next step for us was to search for similar interesting spectral features in our meteors, in our meteor spectra from our AMOS network. And this is just the first step that we have done in the past year, which is that we were looking for the most atypical meteoroids, the ones that are the most different from the common chondritic meteoroids. So we did a study of a selected 180 high-resolution spectra, good quality spectra that we have from our network. We have much more data, but this is just so far that we have got. And we identified 5 irons, so pure iron meteoroids. Those are quite easy to spot. Their spectra just look like purely iron lines. But for the first time, we were able to also identify 2 achondrites, or what we believe are an obrite and a eucrite. So this is kind of the first step that we saw that we can use the spectra to identify the types of material that's not usually recognized using meteor spectra. In the future, what we want to see, what we want to study is also the diversity of chondritic meteorites to see if we can distinguish carbonaceous and ordinary chondrites. But for now, we'll see how it goes with these atypical ones. So this is just an example of what these atypical meteors look like. From the view of the meteor, it might not look very different. The one at the bottom, the meteor is a typical asteroidal, probably ordinary chondrite. The one at the top is what we believe is a eucrite. You can see that the light curve is a little bit different. There's like 2 different components. I will discuss it a little bit later. And the spectra from the first view might look very similar, but they're actually quite different. So when we look at the details of the spectra, for example, at these plots, we have normalized spectra of 3 meteors. The orange one is the eucrite, so similar to HED meteorites. The blue one is an obrite, similar to Riebeck, recently discovered. And the black one is an ordinary chondrite, very typical material. So they're normalized, and you can see what are the regions where they differ very much. For example, these lines of calcium at the top, manganese, or titanium and other minor species. This is just to show you how much they can be different and what we are looking for. This is just a continuation for wavelengths closer to the red. So you can see, for example, here at the bottom plot, there's much stronger lines of calcium in these achondrites. So they already looked very different, but obviously, if you want to quantify the differences in the composition, you need to do modeling. So we applied this radiative transfer model, Borovichka, and tried to come up with what the conditions of these meteorites were and what their composition was. So these are the numbers, which might not tell you as much, but if you look at it in a plot, so here at the upper plot, you have a mean composition of obrites, eucrites relative to H chondrites, so ordinary chondrites, and relative to magnesium. And at the bottom here you have these 3 meteors that we studied, these 2 achondrites relative to magnesium and relative to the chondritic meteoroids. And you can see basically the same pattern in differences between these different elements. There are some minor differences, but they are usually quite easily explained by the conditions that we have. And basically the results of the abundances are very consistent. So we are quite sure that we identify the eucrite and the obrite. It can be also very interesting to look at time result spectra. It's a bit more maybe complicated issue, but if you have also video cameras with larger frame rate, you can study how the spectra evolve in time. And you can study, for example, we saw that for the obrite, there were some transient peaks where at some point of the ablation, the refractory elements were much more rich than at other points. So we believe, for example, that you can also identify some internal heterogeneities in the meteoroids, and which are linked in how the specific chemical element is bound inside the meteoroid. Okay, I'm getting out of time, but this is just to tell you that we also studied the physical properties of these two chondrites, which were also consistent with the estimated composition. For example, we modeled the light curves, which you can see that are quite strange. For example, for this euclid, there's this dip in brightness between two phases of the meteor. The estimated bulk density is very similar to euclides from laboratory measurements. For the Albright, there were much more fragmentation events. By the way, both of these chondrites drop meteorites, but the one from the Euclid was observed on Hawaii, so it dropped into the Pacific Ocean, and the Albright, it's a little bit difficult to search for. We cooperate with the Desert Fireball Network, but the search area is very large because there were some clouds and we didn't get very good terminal altitude. Orbit's also quite consistent with this estimation. I'm not going to talk about it too much. So this is just to show you how our basically first steps in quantifying the composition of meteors using spectra looks like. We were able to identify first very atypical chondrites using meteor spectra. And in the future, we would like to implement higher resolution spectrographs to also see these minor species and get into more detail, maybe try to recognize these ordinary chondrites and carbonaceous chondrites. And yeah, I'm going to stop here. I think this is all I wanted to say. So thank you.
Thank you, Pavol. That was a great overview. We have maybe 1 minute for questions. Maybe one question. Please raise your hand. Hervé, go ahead.
Hello, Pavol. Nice talk indeed. I was just wondering if are you still interested in searching places to place new AMOS cameras or systems?
Yeah, it might be tricky. I think we are quite overwhelmed right now in just keeping all of the instrumentation that we have alive because it's all over the world and it's kind of difficult for us. We are quite a small team to get it right. But if there's something interesting, the spectral cameras are not too expensive. So yeah, it's possible.
Okay, thanks.
Just let me know.
Yes, I will. Thanks.
All right, thank you. I see there's a lot of interest, but in the interest of time, we have to move on. Please put your questions in the chat or ask them during our break/extended question period. Thank you. And next up, we have Jamie Shepard and Will Joy. Go ahead.
Good evening from Scotland. Picture a mild summer night with clear skies over most of Scotland. At 10 minutes to local midnight, it's still twilight. The piece is shattered by a fireball brighter than the full moon. And we had this amazing view from right underneath the trajectory secured by a fisheye weather cam. And that turned out to be very important for the later analysis. It was also imaged by many cameras of the Global Meteor Network, and we'll just go through a few of these. Unfortunately, these only gave us good data for the beginning part of the trajectory, because being so bright, after the big flare happened, the subsequent frames were completely bleached out to white. And even the twilight low over the north horizon got in the way as the fireball disappeared into the blaze. So we had to rely on citizen scientist cameras. This is an Aurora cam from southern Scotland, and these had a much better view of the end of the trajectory, including that giant flare. And the best one was from the shores of Loch Long. A wildlife photographer was filming some deer by the shoreline and swung round his iPhone Supermax Pro camera to get this amazing high detailed view. And the still frames from this are just off the scale in sharpness and detail. You can see every single fragment. Now, Damir Shigon got this video and decided to spend a week of his life doing frame-by-frame analysis using an advanced astrometry technique to get us full data from the film. And this is just a small snippet. The original image of this that Damir sent me, it's as tall as my house. And we put it all together, GMN for the start of the trail, the IMAX, the Super iPhone Super Max Pro camera for the end. And we got a pretty accurate trajectory, which was nailed down in horizontal dimensions with that underneath fisheye view you saw at the beginning. And the fireball made it all the way down to 20 kilometers height. And that's very promising prospect for meteorite dropping. And it came in over the Atlantic Ocean, west to east, and ended up near Loch Treig. Went right over Ben Nevis, UK's tallest mountain. Now, when you're doing meteorite fall predictions from an event of this type, you don't stand a great chance of finding main masses at the end of the trail. And the much better way is to look at smaller fragments that have been released in fragmentation events, of which this event had 4 or 5 good ones. But one thing we desperately need for dark flight analysis is an accurate velocity estimate. And the software in its raw form gives this scatter of velocities. So we have to model that somehow. And I used a polynomial sliding fit. So we get the whole trajectory on the left, height versus time. And then on the right-hand side, we're fitting time to height, time to all the other parameters at the end. And it curves upwards because of the rapid deceleration. And this is the flare at the middle at the 10-second mark. And the velocity curve, well, at the beginning, it's not that great. It bumps up and down. That's because the GMN data was very saturated. But once that iPhone 16 video took over, we see rapid deceleration after the 10-second mark and a nice accurate velocity curve. As a byproduct of this technique, we also get the tracking of altitude and azimuth of the radiant point as the fireball tracks across the curvature of the Earth's surface. Then on the right-hand side, as gravity takes over, the elevation starts to increase very rapidly. Put it all together, we can put it in a data table. Each line is a table of seed data for the dark flight software. And Denis Vida very kindly let me use his open dark flight software. And we plugged in data from 3 or 4 of the flares. Each colored line is a mass value. We did 1 to 100 grams. And this gave us several possibilities for strewn field areas. We can also add in the large masses from the endpoint. And these are the masses from 1 kilogram up to possibly 20 kilograms that we thought might be involved. And if we look from the west to east along the whole possible strewn field, about 25 kilometers worth, we can see it went over some pretty remote and rugged terrain. This is wilderness. Hardly anybody lives there. And I'm now going to pass you over to Will Joy, who's going to talk to you about the field search. Thank you.
Thank you, Jamie, and thank you, Denis, and everybody for having us here. Can you see my screens okay and hear me?
Yes, we can.
Excellent. So here is our arrival by train to the highest rail station in the UK. And as you see, there's a lot of boggy terrain there, so searching is very difficult. Then we moved on to the beautiful youth hostel, which is a mile away on Loch Ossian. This was our search headquarters with most of the team camping outside. Professors Martin Lee and Luke Daly were team leaders, and Ona had made a tremendous organizational logistical success in coordinating us all being there with equipment and food. It was simply a beautiful location. Here's a map of the search area with Munro tops in white and the calculated strewn field shown. Long day trip searches were possible on the shore of Loch Traig, ridge of Garba Bain, and along available low-lying search areas, which were not too boggy. Wild camping searches were planned at Stop Khorasan and then the challenging Ben Alda. So searching the Loch Traig area. Loch foreshore and the forest searching was actually more challenging than it looks. And here we are, just a little view of what it's like.
Nice place to sit. Nice bit of wind. Weather's good. Grass tree keeps all the plagues away and all the change. See how these trees and the roots are coming out.
Moving on, route up to Garba Bain Ridge. And ridge searching conditions were extremely good.
Coming into the zone, hopefully you can see Loch Traig down there, just glimpse down. It's good for hunting. See how it goes.
The low-lying areas offered varying levels of searchable terrain, with most areas being difficult bogland, as you can see here. But there was the odd riverbank possibility. And moving on to the midge-infested wild camping site at Stop Khorasan, search areas were reasonable in areas on the mountain slopes and good on the Munro Ridge.
Tea break 2 on a nice little gully. There's Jens having some little mixed nuts. Going down, we've got Jamie doing the maths, human calculator. Prof Luke, team leader. We've got Angia there with beautiful Elsa. And we got the beautiful view of some of the Munros around. In the zone, if you're looking down there, that's our base camp one. So here on the ridge, in the zone, Loch Traig down ahead. At this pack team over on that ridge. That's the forest down there, already been searched on the shore.
Unfortunately, the next planned difficult 16-kilometer walk-in and wild camp on Ben Alda had to be called off due to severe lightning storm warnings for the following couple of days. But weather improved later in August, and I decided to make a solo search with guidance and backup support from Jamie and my wife, Mayram Fatima. And here was my initial camp location for 2 nights after the 20-kilometer walk-in from Dalwhinnie. My first ascent of Ben Alda, which basically followed the deer up. And here's the view from Ben Alda summit plateau and a view of the search terrain.
19th of August, 4 o'clock in the afternoon on Ben Alda summit plateau. Came up a very, very steep route over there. Just came up on the grass about 50 meters over there. On the southeast side, the beautiful loch, walked around the loch there, down to where I was camping. Anyway, this is it. This is Ben Alda summit, big plateau, about 2 kilometers to where Jamie's estimate for the 5 kilogram pieces. So we'll see what we find. So, gotta keep going, gotta find these black rocks.
The summit offered mixtures of very good, fair, and poor areas of search terrain. And to improve access to Ben Alda summit, I changed camp location after the first 2 nights. And here was my campsite for the last 4 nights, camping on the west side of Ben Alda with incredible views. Here is a view of Ben Alda while climbing and searching the Munros of Ben Ebin, Anak Beg, and Gil Khan. Search conditions were good, but again, no success. This was after a few days searching on Ben Alda and was just to check and see if there had been any stray for perhaps fragments, oriented fragments, which had drifted off, for example. I didn't even find 1 meter wrong on these Munro tops. In fact, the only thing found which had come from out of the sky was the remains of a very old aircraft wing. And my final day of searching Bernalda was in thick mist. My final search was made during my walk down into Kourou station, but search terrain was extremely difficult. So our search so far is unfortunately without success, but searching is planned to continue when weather improves. This was our great combined search team. And a big thank you for watching and for inviting us here. And a huge thank you for all who helped, which is detailed here. Thanks again.
Amazing. Thank you so much, Will. Is there one short question for Will? And Jamie, of course.
Yeah. Hey, so what I'm wondering is, sort of a bit unfamiliar, but when searching for a meteor on the ground, in my mind, you're kind of just looking for a rock. So I'm really wondering, is there any technologies or strategies you use? Because I mean, with such a large radius and there's all these mountains, I imagine it's quite difficult.
Yes, it is very difficult, and that was the hardest terrain that myself and Jamie and the team have been searching on. Everything was obviously narrowed down with the analysis of the meteor coming in to try and narrow down. But equipment-wise, we're using GPSs and serious looking, and in that sort of area, you need survival gear. We had water filters for water. You walk in 20 kilometers, and you've got to carry all your food, everything in, and drink from streams. So water filter is necessary. But really, it's eyes only, dedication, and thorough searching. We were searching when we were in our groups. We were searching in teams, stretched out in lines, typical meteor searches on ridge areas or any areas which could possibly be good for searching. And really, it's just dedicated search. But the search is not over, and I definitely, and myself and Jamie and probably the rest of the team will hope to continue and find a piece of this meteorite. Thank you.
Perfect. Thank you, Will. Well, we have to continue with Justin, but please, if you have any questions, please put them down in the chat, and we will have an extended question period and a break at the end of the current section. All right, Justin, go ahead.
Give me 1 second to set everything up. Everything looks good for everyone else. Able to see the presentation?
Yep, you're good to go.
Okay, perfect. So I'll be presenting Astra. This is a piece of software I wrote this summer working at the Western Meteor Group. It's the astrometric streak tracking and reduction algorithm. I wrote this in conjunction with Denis Vida and Peter Brown. A quick introduction to myself. My name is Justin, of course. I'm a second-year physics and scientific computing student at the University of Western Ontario. So previous research of mine, I worked briefly on a CubeSat called Skylark, doing some orbital analysis. I again worked this summer at the Western Meteor Group, and I'm currently working on some dark matter stuff with experimental submillimeter astronomy. So quick background. The Western Meteor Group has two main optical methods for detecting meteors. The first is CAMO, which is the Canadian Automated Meteor Observatory. This is a tracking camera with extremely high quality positional data, but with a relatively low quantity per night, and it requires a lot of manual calibration and processing. What was recently introduced is the EMCCDs, and these are extremely sensitive cameras with allegedly single photon detection and extremely low noise. They have about a 5 times higher detection rate than CAMO, but their main struggle is to require manual reduction. And manual reduction is just a process in RMS where you pick and you choose where the meteor is on each frame. We have about 160,000 different meteor detections, and this is growing. So you can imagine if we have someone look through each one of these events, we're not able to cover every single event and analyze the data in its fullest extent. And the largest challenge in meteor reduction, as many of you probably know, comes from the fact that low spatial resolution results in low trajectory accuracy. So this is a video frame from one of our EMCCDs, and let's zoom in right here. This is about 52 times from our original frame. And think in the mind of a manual reducer, when we're trying to pick the leading edge of this fragment, We could pick here. We could pick here. These are both pretty reasonable results and pretty reasonable choices going purely off the data. But the issue and the struggle comes from the fact that these are about 100 meters apart. So you can imagine when you're picking maybe 30 different frames, these small differences in each pixel result in massive differences in our calculated trajectories. So a bit on the methodology on my program. We have a very brief overview on how the algorithm works. We take in 3 seed picks, which is the first frame, the last frame, and the middle frame of where the meteor is present, and just a really general location of the meteor, just anywhere along the streak. What my program does is it crops the image, runs a PSO, a global particle swarm optimization, followed by an LBGFS local optimizer to fit a moving Gaussian onto the image. Then we feed the data we get from this Gaussian into a series of parameter estimation functions, which just tell us what the meteor will look like and where we think it will be on the next frame. We continue this and we continue this for each frame until we reach all of them, and we get our data from that. So obviously the first step is just image calibration. And this is pretty standard, dark, flat reduction, background subtraction, and we also do a lot of stellar masking. One thing that's important to note is that the EMCCDs have extremely low noise, which makes this a very easy process for us to do. The second step is our Gaussian fitting. So on the left-hand side here, we can see what the original subtracted and processed image looks like, zoomed in, and in the middle is the moving Gaussian, and on the right is the residuals. And you can notice that our moving Gaussian very well encapsulates what a general meteor streak would look like on these EMCCD cameras. And the red dot is our leading edge pick from the Gaussian. The next step is to put this into our parameter estimation functions. And what these are simply just first degree or second degree moving fits on our data, which allow us to estimate where we think the next meteor will be in the image, and importantly, what it will look like. This is really important as image fitting for moving Gaussians have a lot of local minima and are quite noisy in that respect. So this makes sure that we have a good, clean, and convergent fit for each image. And the last step is photometry. And this is, again, relatively simple. All we do is you take our fit, we cut off all the pixels below a certain luminosity threshold. We take those pixels, some background subtraction, compare the noise from the background and the signal to get both the SNR and the level sum. So on to some results. So just kind of a quick recap. So currently we're using manual reduction, and this takes about, it takes about 10 to 15 minutes for me. I'm pretty unexperienced, but for the pros, maybe down to 5 to 10. So you can imagine for 160,000 different events, we're only really able to analyze the ones we find really interesting. So it's quite time inefficient. We get a medium quality, but the largest issue is we get a large bias. Because each pixel has such low spatial resolution, what ends up happening is that we're not actually able to fit purely qualitatively on the data. What happens is the manual reviewer or the reducer will pick a point, run a quick trajectory simulation, see what it looks like, and kind of tries to smooth the points together and smooth the points to each station. So what's happening is the reducer is not actually always acting purely quantitatively on the data, on the video that we see, but is more trying to get a good fit and imposing their own bias onto that. And this is where the strengths of the Astra algorithm come in. This is a fully automated algorithm. So we're able to take our first seed picks from another algorithm, which is automatic and already implemented. And we get results that are about 3 times more accurate than manual. And most importantly, this is an unconstrained model, meaning that Astra, when it looks at the video frames from each station, doesn't even think about the other station. All it does is it looks at the image and fits a PSF onto that, meaning that we're not trying to fit, each station to each other or fit to a certain model. Anything that we see is purely from the information we get in the image. And you can see a lag versus time and velocity versus time graph here. And what we're able to see is that in the very smooth curves and very tight curves, that is the camo data. So we're treating that as a ground truth. And on the left-hand side, we can see our manual reductions, and on the right, Astra. So you can see for the lag curve, on the manual reduction, we get a very jagged path. that near the end doesn't really match the camo data. And this is from the fact that the manual reducers are often trying to match the data to each other and not necessarily to the actual video. And for the velocity, we see a path that relatively makes sense and matches what we see, although the residuals are much larger and there's a lot more uncertainty. And on the right, we see Astra. And Astra, although there's still some jaggedness, which is important because that represents systemic uncertainties and inaccuracies within the data itself, matches camo quite closely and is representative of what we physically see with the meteor. And more importantly, we get very low uncertainties and it closer approaches and approximates our camo data. And for a larger comparison here, so this is a test run on about 110 different fast and slow meteors, ranging from about higher and lower than 20 kilometers per second. On the top, here's just a scatter plot of our uncertainties for right ascension and declination, where we have in purple our manual fits, our manual reductions, and in cyan our Astra reductions. As you can see, over a wide range of different velocities, Astra is continuously performing with larger uncertainties and more accurate than the manual. And on the bottom, you can see a quick table of these different values. And you can see that we're getting, on average, about a 3 times improvement in our uncertainties, especially within our spatial residuals. Or for example, for slow meteors, we're getting an average of about RMSD of 12.5 meters or 12.2 meters. Whereas for Astra, we're getting about 4. So in conclusion, Astra is unlocking accurate trajectory data for a growing collection of 160,000 events. We're finally able to solve this issue of measurement cadence and our inflow being a lot faster and a lot larger than we're able to process. We're very effectively able to eliminate the systemic biases present in manual reductions, and you're able to save researchers hours by limiting their need for manual reduction. And on the left-hand side here, you can see a GIF of what our process looks like over time throughout the different frames. Any questions?
Thank you, Justin. That's right on time. Yeah, questions for Justin? All right,
Yes,
lots
Mr. Shober.
positive. That's awesome. All right, so if there are no specific questions for Justin, then I'm opening up the question period for everyone. So essentially for all 3 previous talks, feel free to ask questions or take a break while the speakers are here. Now is your chance for the next 7 minutes.
I think there was
Luke,
a question
go ahead.
by Colin.
Yeah, actually, that was a question for Justin. Like super impressive work. I had a question, like when comparing camo to the other camera, how much of the error is coming from difference in calibration of the image versus actually tracking the object itself?
So to clarify, you're asking how much of the error is coming from the reduction versus like
Versus
systemic in the camera?
the calibration of, I mean, I'm sure the camo image and the other camera have different calibration tolerances. And are you able to separate the error from tracking the meteor versus the systemic error of calibrating?
If
the
you don't
image?
mind, I can take that one.
Okay.
So essentially, camo is a bit more difficult to calibrate because it's a tracking system. So the image is moving across the sky, so you need to have the calibrated positions of the mirrors, and you need to find a way to convert the differences from the center of the mirror into the mirror coordinates. So there are 2 calibration plates, and they both have to be correct. And they're very tricky to get. And you can't calibrate directly on the image because there is nothing directly to calibrate. So there are these whole special calibration runs that have to be done. What Justin here is showing, I would say that I would more trust the absolute calibration of the EMC city data because you see the stars immediately behind it, and you make your pick. So most of the errors that you get are random errors. Camo is different because the resolution is incredible. I mean, we're talking about 6 meters per pixel, like an arc second per pixel, essentially. Sorry, a few arc seconds per pixel, but after saturating, you get down to the arc second level. But then the absolute calibration is trickier and takes more time to do right. So you still have the whole manual process, and the whole goal behind this project is to have something that can completely, in an automated way, achieve camo-like precision, so you don't have to spend so much time on camo reductions. Now, camo does something else. You get a better insight into the meteor phenomenon. You see the individual fragments flying off, et cetera, et cetera. So it's still necessary for some work. But for let's say 50% of what you're trying to do, the MCCDs are probably sufficient. So yes. All right. Any other questions for our speakers? Oh, Alex, go ahead.
Yeah, so I wanted to ask a bit about the meteor spectroscopy. I asked about the required hardware that is necessary for this. Can you give us a bit more of an overview of what kind of sensors would be good, lenses, and what are the constraints? Because the one you mentioned in the chat, I can't really find it, to be honest. And I think a bunch of people are interested to find out how can they join and contribute.
Yeah, sure. I mean, I just give you an example of what I know because we've been using it for a while and it works quite well for us. But it very much depends on what you want to get out of these meteors, what brightness of meteors you want to study with spectra. So we are studying like medium-sized meteoroids, so we get spectra for meteors brighter than -2 with this setup. But it depends. I mean, as long as you have a similar resolution and size of the sensor and you combine it with a good lens, you can get probably a good setup with many different kinds of combinations. I'm not really that well versed in the instrumentation, so I can give you many different examples. But yeah, I mean, just from what I saw, like who I was presenting, the different teams that I'm using, it's usually quite similar, but it depends. Yeah.
Okay, thank you. So in principle, we could.
I would say it's easy to even like experiment with whatever setup you have, because to get like a good diffraction grating, it can be quite cheap. You can buy like a film diffraction grating, which is a few tens of euros. You can cut a nice holder above your lens and see what you get with whatever you have and go from there.
Okay, thank you.
All right. Any other questions for our speakers? We have about 2 more minutes.
So I can ask another question about that. So it sounds like the concept is not to have a camera that's looking at the sky when you're doing the spectral analysis, but to just be collecting the spectral data with the diffraction grating, right? So are you okay with just looking at a broad view of the sky and collecting the spectral image, which I could do possibly with like a linear array under a diffraction grating or a something to separate the spectra?
You mean like without a camera, without having like the...
No, in addition to a camera. If you have a camera that's collecting the concept of the meteor being there, but another camera to be monitoring the sky spectral content.
Yeah, sure. Yeah, it should work. I mean, you can even get just the signal for some kind of spectrometer, which is just collecting everything that it sees in the night sky, but then you might not be able to resolve like what the signal is coming from if there's some stray light. So yeah, for us it's good to have the combination to see the meteor, but also the spectrum. But yeah, both could work.
Okay.
All right.
If I can chip in to this question, you could use 2 cameras, which is, as you said, one is tracking, and use it as a reference for spectra recognition for those lines. So you could already think about pairing that one. It's just that you would need to have some prerequisites concerning like what will be my matrix going from one camera to another one to help you with the proper recognition. So, but it is possible to pair two cameras.
Thank you, Rita. All right. Well, we have to start with our second part. We're going to have a talk by Quanzhi. Unfortunately, he couldn't make it, but he sent me a recording. And this is about potential killer asteroids. So, topic of interest. I will be sharing my screen, and please do tell me immediately if you have any issues, if you can't hear any sound or anything like that. So I'm going to share my screen with a share sound option. I hope that works. So, all right, I'm playing it, and please do yell if something's wrong.
Good morning, good afternoon, and good evenings. And thank you for having me here. My name is Quanzhi. I'm a research scientist at the University of Maryland in the United States. I apologize that today I can't give the presentation in real time because of conflicting commitments, but I should be able to join for the Q&A session. So please do save your questions until the end of my talk. Today, I'm going to shift the gears a little bit towards the larger side and talk about asteroid-sized objects in the Taurid resonance swarm. So Taurids is one of the most prominent annual meteor shower. We know that it's the debris stream. It originated from comet 2P Encke, and it has been hypothesized that the Taurid complex, meteor complex, was originated from a large breakup of Encke, of the proto-Encke object that broke up maybe 10 to 20,000 years ago. And one of the interesting relics of this breakup is that it gives rise to a feature called the Taurid resonance swarm. So thanks for the meteor observations, we recognize that the Taurid meteor shower, while not as strong as more well-known showers such as the Geminids, Leonids, Trichonids, it has this enhancement that occur every once in a while. And dynamical simulations have shown that this is because of the dynamical perturbation from the planet Jupiter. A fraction of the materials from the creation of the Taurids ends up in a mean motion resonance with Jupiter. That means that every once in a while, when our Earth passes close to the center of the mean motion resonances, we are going to see an enhanced activity from the Taurids. So folks have looked into the meteor data, such as the plot shown here by Dubitis and Art in 2007. And you can see such fingerprints from the concentrations in the mean motion resonances in the meteor data. So this feature is well recognized, and we know why it's there. But at the same time, the detection of this enhancement has been most ambiguously only found in meteor data. There have been discoveries of some larger, I'm saying 100-meter class asteroids that may be associated to the stream, actually may be associated to the swarm. So this gives rise to an interesting question. Are there larger asteroids? By asteroids, I mean objects larger than about a meter across that reside in the swarm that can occasionally cross, and maybe if we are unfortunate enough, one day could hit the Earth, so to speak. Or the other question is how many potentially hazardous asteroids, or sometimes smaller objects, but could still present a hazard to a smaller area such as a city, reside in the Taurid swarm, resonance swarm. And a good time to look into to do such a search is it's during the encounters, during the Earth encounters the to this mean motion resonances. This happens every a few years, and most recently, this happens in 2022. Actually, 2019 is a better provides a better opportunity to study objects reside in the mean motion resonances. And my colleague David Clark and collaborators, they tried to get telescope time to study it, but it wasn't successful due to various reasons. But after that, the next best opportunity was in 2022. So we decided to use survey telescopes to study it. And this survey telescope is known as the Zwicky Transcend Facility. It uses a 1 meter class telescope at Palomar Observatory in Southern California. And this telescope is currently equipped with one of the largest cameras mounted on the telescope. And each image is about 7 by 7 square degrees, which can include about 200 full moons. And here you can see how big it is. This is the Andromeda Galaxy, and here you see the field of view of LSST. And LSST is a much bigger telescope, so it's much more sensitive to fainter objects. But if you look at the coverage on the sky, ZDF provides a larger coverage, based on the lower sensitivity. And ZDF is able to scan about 4,000 square degrees per hour down to limiting magnitude about 21 during new moon. And astronomers use ZDF for a variety of sciences, things from supernovae to variable stars to tidal disruption events, and of course to small bodies in the solar system. We have two systems running on this data set. They are each of them are good for different things. We have a deep learning powered system that's optimized for looking for objects that pass very close to the Earth and therefore smears or streaks over multiple pixels, as shown here. Let me see if I can get the animation to work. Well, not quite, but imagine that there's this stick moving across the image, not because of the object is streak-like, of course, but because it's moving so fast that it smears over multiple pixels during one exposure. And we also have a more traditional detection software that looks for point sources moving across the sky, and this will be for slower objects that don't smear over the course of an exposure. And we secure time to search along the corridor where the Taurid resonance ones will be. And if you plot it over the sky, this looks like a very long arc, because imagine that it's like a river in the planetary space. And when you zip past it, it will appear like a long, very narrow arc in the sky. And ZDF is perfect for these purposes because of its large field of view. So we did a simulation where these objects will be in the sky, and then we command ZDF to cover this very long arc. The plot may be a little bit deceiving because you see that there's a long tail here, but if you actually check the particles, the distribution of particles, we actually cover 99% of all the simulated swarm particles. And then we run our detection software and both of our detection softwares on the collected data to see if we can see any streaks or any slower moving objects that follow the path of what a Taurid resonance swarm object would be moving. And we didn't find anything. The short story is that we don't find anything. But of course, when you don't find anything, you can turn it into a non-detection. So we did a bunch of calculations to try to understand what constraint that such a non-detection would provide to us to the Taurid resonance swarm. And long story short, the results here on the right, these are all upper limits of objects of different sizes that our non-detection would constrain. And translating this to numbers, this means that our observation shows that there are no more than about 10 to the second Tunguska-sized objects and less than 10 to the third Chelyabinsk-sized objects. And if you flip this number over, this will mean less than one Chelyabinsk class impact every 4 million years. So that's a very long time. And another way to look at this is that if we sum all this object up, this means that the parent object that assuming that the parent objects all turn into the Taurid resonance 1 plus the modern day Enki itself, this means that the parent body that produce common Enki and all these resonance 1 objects, it's probably about 10 kilometers in size. So this is much smaller than the roughly 100 kilometer class object that some hypothesize, even though this is a hypothesis made it a long time ago. All right, so this number seems not overly impressive. That means that we probably won't see a Chelyabinsk size impact from the Taurid resonance 1 asteroid. Does that mean that we can sleep better? Hopefully it does, but we need to consider this caveat. The caveat is that this whole results depends on the assumption that the distribution of the Taurid resonance 1 objects are kind of homogeneous, meaning that there are not a large breaks in the size distribution of the objects, which we know from those better observed meteor showers isn't quite true. Of course, this is better than nothing because other than that, you don't really have better constraints on it. You have to start from somewhere. You have to assume that it's a single power law distribution. And we know that it's likely imprecise. But this is something that we need to keep in mind when we try to interpret this result. Now that we have ZDF result, now that we have constraint on ZDF, which is very nice, but because of the caveat that I just mentioned, that doesn't mean that we don't really need more data. And actually, we will have better facilities to get a better and more constraining, hopefully, data on the Taurid resonance 1. So this is a quick calculation that we run as part of our research. We devise a figure of merit, or FOM, which gives you an idea of how much more efficient, or maybe less efficient, that the telescope might be relative to ZDF. And LSST, Rubin Observatory, which will start formal operation soon, as you can see here, is going to be about 30 times more efficient than ZDF in finding Taurid resonance 1 objects. And the main reason is that, of course, LSST is a much bigger telescope than ZDF. By collecting power, it's about 70 times better than ZDF. But also, its field of view is more appropriately scaled for the width of the arc of Taurid resonance 1, meaning that each image will be covering the arc more efficiently and not wasting some of the coverage on part of skies that don't have such objects. And LSST will, as I said, LSST will soon start its 10-year main survey. And happily, this coincides with the next best encounters with the Taurid resonance 1. That's in 2032 and 2036. The delta M is a measure of how far we will be from the center of the mid-motion resonances. I said that the 2019 was a very good one because we are only 5 degrees in terms of mean anomaly away from the center, and 2032 and 2036 will only be 1 degree away. So this will be one of the very best encounters over a very long time. So in summary, with a ZDF campaign, we determined that there are probably no more than 10 to the second tungsten size objects and no more than 10 to the third cherubim size objects in the Taurid resonance one. And this translates to less than 1 cherubim class impacts every 4 million years. So a small number, but this is assumption dependent, so there are rooms for refinements, and we hope that LSST and other future survey telescope will help us to place a better, stronger constraint on this. And this also imply that the total Anki object might be closer to 10 kilometers in size rather than some of the previous theories that was about 100 kilometer class objects. So with that, I will stop here. Thank you very much. And hopefully the future me will be around and take your questions. Thanks.
All right. Well, the future Quanzhi is here, and he's happy to take your questions. Yep. Thank you for joining us, Quanzhi. I just want to mention, I don't know if people got this, but the reason why we know about the Taurid swarm is because in 2015, the Czech group observed the big fireball outburst. They noticed a lot of decimeter-sized fireballs that came from the right place. And the big question was then, well, if there's the small stuff in there, how about the big stuff? There were some early indications that there might be some big asteroids inside. And Quanzhi spearheaded the work to try to find killer asteroids in the stream. And so far, you've seen the results. All right, so questions for Quanzhi. All right, well, I have a question for Quanzhi. So are you planning to run the LSST survey or work with someone at the LSST to run the survey in 2032? Maybe planning some proposals, or what's the general plan?
Yeah, that's still 6 years away, and obviously LSST hasn't really started yet. But that's definitely within our consideration. So what? Well, I guess this first depends on how the real, the formal surveys pans out. Maybe some of the corridors are already covered by the nominal surveys. But they also have a channel in which the community can submit target of opportunity proposals and request a more tailored survey cadence. So if we are, I'm not trying not to be pessimistic here. If all goes well, and we can go to that route. We can submit a TOO proposal and try to do a more dedicated campaigns to the Taurid, just like what we have done on ZDF. So we will find out in 6 years.
Awesome. Thank you so much, Quanzhi. All right. Well, we have to move on to Jürgen, who's going to tell us something about visual meteor observations. Jürgen, go ahead.
Okay, so I will try again to load this. Probably not really full, but
we can see it pretty well.
Okay. Yeah, I want to bring you back to smaller stuff, not the individual large objects, but smaller stuff. And the idea or the thing which we started with was that in the Leonids, in 25, there were some signatures of old dust trail returns. And there was also something with the Ursids a bit later in December. And yeah, I'm always interested to compare the different results obtained by different techniques, including for radio forward scatter, for example, which covers even fainter meteors than the visual ones or the optical ones, and to compare it with model calculations. And so let's have a look at this graph, which you perhaps know if you go to the GMN page. And you see the full activity profile of the Leonids of 25. And down in the image, you see there were some predictions of additional activity. And so we can go step by step and try to identify these. And the interesting thing is, if we just start with the the first one, already on 9th of November, that's a week earlier than the main peak of the shower, you see there's some prediction made by Jeremy. So that's a very old dust trail from 1167, and it looks, the solar longitude, or the time of the occurrence, is almost perfect. And Jeremy himself was very much surprised that such an old dust trail can be found. We have to take care because it's only just one value, and we have to make sure from other data sets that this is not something fluctuation or something which has another bias effect. Next, we can first go through the list, and we see the next one. It's here. Another much younger dust trail from 1633, also modeled by Jeremy's calculations. And here you see there is a significant peak, so it's not just one value. You see that's a real kind of profile, but it's about 0.25 degrees later than the calculated position. So the question is it really possible to identify this dust, which we have seen here in the form of flux increase by this filament? And that's something which Jeremy is just running once more, because 0.25 degrees is quite a different position. It's about 6 hours. And there was one more predicted maximum by Mikhail Maslov, who had trace of the 1699, so even younger than the one before. And it was obviously not very sharp, so it had some width. And of course, we could speculate that it's here. And last but not least, there is the nodal peak, which is, or some people call it the regular peak, which occurs if the Earth crosses the nodal, the plane of the cometary orbit. And that's normally at 235.27, but the highest rates were only observed at 235.7. That's half a day later. So there's a lot of things which require careful modeling and comparison. And that's all video data. You see, it's really a complete and very continuous curve. That's, of course, the reason why it's done. You cannot do it with any other technique in this form, perhaps except for the radio and radar meteors, of course, because they do not depend on the weather conditions. But because I started with it and still continue this kind of observations, and another 200 something people do it as well. It's visual observations. Of course, that is one of the bad things which we all know, that the visual observers cannot cover all the periods because they get tired, not as the video cameras, which are awake all the time. But then we can still try to identify a few of these things and get a better idea what they are about. Unfortunately, there's no visual observation as early as the 9th of November. But if we go to the next positions, that's the graph which shows the visual data. It's only the short window, and you see I put it to the same solar longitude as the upper graph. So it's the same same window here. And of course, we see the nodal or the main maximum, which is in quite good agreement concerning the solar longitude. And what I found interesting, that's something which came out very late only, is this small peaklet after the main maximum. So far, we always looked to the dust trails which were predicted, but there's something obviously also here in the late part. It's another 1.5 days after the nodal maximum. And I mean, if you are very keen, you could speculate that it's also visible in the visual data, although, of course, it's no profile. But it shows that there is something or some significant activity of flux density also that late in the profile. That's something we have to double check with the radio data in order to make sure whether this is some true structure or not. But that's something which was not in any of the modeling. So that's something completely new. And Jeremy is busy to do the modeling of these things in more detail, but then there's an additional task arising from this profile to have a look and to find a possible explanation for this late activity increase. That's about the Leonids last year. Obviously, something more interesting than you expect. If you say normally Leonids now, it's far away from the outburst and storm years, but still there's interesting stuff to be seen. Another shower, which often is not considered as a very active one, is the Aurides in December, just before Christmas time. And the interesting thing also here from the GMN data is that the rate or the flux is about twice the value which we normally see. I put it here. The average ZHR is 15, and from this graph, it's at least 30. And it's about 0.3 degrees earlier than the average position, which has been found in so many analyses. So there's some activity outburst was going on. And that's interesting. Here I put the visual data to the top. And you see also there's confirmation by this data, and also the ZHR of about 30 is quite well in agreement. So we see there was an outburst, not really a strong one, but quite obvious. And this shower obviously is different to the model. What we always see is the prediction in the table of Peter Janiskin's book about the meteor showers and parent objects, where he has a list of filament crossings. Filaments are not dust trails, but regions where meteoroids are somehow accumulated. And they have not high activity, but sometimes there's a different kind of population, like larger meteoroids collected in this. And you see there is a small increase here, and well, again, very close to the speculation limit, I would say, also in the visual data. So at least there are two features which require complete evaluation. That's the outburst, which we have seen in different optical data, and also traces of this weak filament crossing at approximately the position which is also predicted. That's some summary so far. So for both showers, nothing was really expected in 25, but we found signatures of the dust trail encounters of different dust trails for the Leonids, and something which needs also to be explained, that the maximum, the nodal maximum, is reached much larger. And for the oocytes, it's this short outburst and the trace of the filament crossing. So you see there's some thing even for showers which seem to be not very much of special interest. And of course, as I said, I'm observing visually still. I'm trying to motivate people to continue this method as well for a few reasons. I'm interested, as I mentioned in the introduction already, in studying the stream evolution and to compare these results with the modeling. And of course, if you use different methods, change from visual to video or something else, then you need always an overlapping period to calibrate the data. Otherwise, you can just introduce systematic errors or systematic effects, which obviously or apparently produce something which must not be real. And so this overlap in different data sets is necessary to have some compatible and continuous data sets. And also the visual observer, if you observe showers for decades, then you can experience the changes in the shower. I mean, it's not only like the Leonids with the storm years, then everybody, of course, experienced it, but it's also that you see how a shower evolves if you observe it from one year to the next. And I mean, we have heard so nice talks about fireball analysis, the Scottish fireball with all this fragmentation. We had it the same here with the Rübeck meteorite fall, which was just in front of my back door. More or less, you see these physical processes. Of course, yeah, we can measure everything. We have all the video data, but I mean, if we do research, it means we ask questions to the nature. And the more you have seen or experienced or heard something, the more the better you can ask these questions and combine it with the own experience. So I think visual observations have also a value from this point of view. And something is also clear, these observations exist for decades, and sometimes it's important to, if you want to follow the evolution of a shower, to include also these old data. And last but not least, Dennis asked me to make some advertisement for the handbook for meteor observers. For the simple reason, I mean, we have nowadays hundreds, thousands of papers on meteor astronomy, and you find really everything. It's different to the time when I started meteor astronomy myself. Then it was just a few books you had and only a few papers. Now it's really a lot, but you have only few things where you have the description of the methods and also some details of the techniques, of the analysis, how is flux and ZHR related, about the accuracy, the error margins. For the last edition, we included a chapter on these analysis and calculations, which has also information or discussion about systematic effects and statistical effects. So that is something which probably is of interest also for other people doing analysis of statistical data. And as I said, there's much still to be done. This example, as I showed in the beginning about the Leonids and oocytes of last year, need to be completed, and we have still other data to be analyzed and to combine these to make the picture more complete. We have also the plan to look at the previous returns of the Leonids, which had also weak dust trail encounters, and nobody has yet looked at the data in detail, whether we can find something there and confirm it. And that's an important aspect as well, to have the observations and to have the modeling, because it's an interactive process. You get better data, then you can improve the models. With the better models, you can make new predictions for the next returns and so on. And for this year, there are different Perseid encounters, dust trail encounters, and also there are possible activity enhancements in September and November, which are described in the IMO shower calendar, which has all the information about the calculated and predicted maxima. And use all the techniques which are available, including visual. And yeah, thanks. That's it. Very brief.
Thank you so much, Jürgen. Yeah, thank you for bringing up the handbook. I think one thing that's really missing in our field is kind of a simple and approachable way of getting into meteor astronomy, and I think the handbook is really the only good book that anyone can pick up and start learning about meteor astronomy from scratch. So, all right, thank you. Any questions for Jürgen? Paul, go ahead.
Yes, Jürgen, thank you for a nice presentation. First, I wanted to notice that Hiroshi Ogawa has the same curve for the URSITS of 2025, which is almost exactly like you showed, but with radio observations. So that's another technique, and yielding exactly the same results. So that's a very good indication that all these different methods lead to the same results. And then I have a question. Often there are differences between the observed curves, profiles, activity profiles are not always in line with the predicted filaments. It's always compared, does the observation agree with the prediction? But shouldn't it be that the prediction should be revised in function of the observations?
Yeah, exactly. That's what I said. That's an interactive process. You produce the data, or you have a prediction and find out that there's a difference. And then you have to give the data back into the model and to try to improve the model to get the observation explained. So that's not one step, but it's a kind of iteration that you arrive at it. And thanks for the hint about Hiroshi's data of radio forward scatter. It's the same, or well, not the same, but also Hirofumi Sugimoto has also this rate curve for radio meteors. The only thing which you have to keep in mind, these radio forward scatter stuff, they refer to meteors of, say, rather 6 magnitude, and the optical is more, the main stuff is around 3rd or 4th magnitude. So there's this difference. But if they are at the same place, even better.
All right, thank you all. Let's go to Regina now. I think she has to run somewhere. So thank you, Jürgen, again. And if there are any questions, please put them in the chat. All right, Regina, I will not be recording this.
Yes, I will share. I will share the screen. So do you see the presentation in?
Yep, we can see it. Yep,
full screen?
Okay. Yep, go ahead.
Okay, perfect. Let me get rid of this. Okay, so this is a very short presentation that I want to give about our effort with our Moroccan colleagues to set up the first GMN network there. So I got the opportunity in 2024, March 2024, to go to the Ukaimden Observatory in the Atlas Mountains, a very, very beautiful place, as you can see. And so, well, the talk I'm giving here is the the result of a collaboration with Zouer, Abdelkarim, and Miriam, who helped us at that time. And I want also to mention Paul, who helps us with the optimizing the direction of observations for each camera. So in March 2024, it was not such a great weather on the, as you can see, but we installed the first camera there. The next day, fortunately, it was so much better, so you could see where we are. And the first night was, no, actually this was not the first night. I think this was taken during the Perseids that year. So we take advantage, of course, of the fact that the Ookhamden Observatory is a very good astronomical site with a very deep sky. This is where the TRAPPIST North telescope is locating. Shortly after that, the second camera was installed west of Marrakesh. This camera was provided by Mike Mazur. And as you can see, we had some initial problems with visitors. So Abdelkarim had to install something preventing any birds to stand there and do stuff. Later on, well, first of all, this camera was initially pointed, and the one in Ookhamden were pointing to the east. But unfortunately, when this camera here points to the east, it was right above Marrakesh, where light pollution was very, very strong. So we decided to point to the west instead. So, and I sent a second camera to Morocco. Abdelkarim moved inside the second camera, moved the first one, as you can see here, on the side of one of the astronomical domes there, and the third one now turning looking west as well. So this is the field of view. You see the Marrakesh in the red circle. Ookhamden is somewhere in the bottom red circle, and you see the three field of view with some overlap. Yes, so this is an example. Of course, with such a small network, you cannot have that many trajectories, but here is an example of trajectories retrieved during the Perseid. So you see that there are quite a few. So it's really a work in progress. But I was surprised that, and pleasantly surprised actually, that in the report posted or sent by Paul 2 days ago, actually this small network already produced quite a lot of orbits. Also, despite the fact that we had technical issues, sometimes with the SD card, which died, and very recently the cameras in Ookhamden were off for a few weeks, and the reason was this. As you can see, these pictures were sent to me by Zouer. There was an incredible amount of snow on the mountain, more than 1 meter, if I remember well, and so this caused, of course, a lot of local problems. So what we plan for the future, I have 3 more cameras at my institute that I plan to bring to Morocco this year, hopefully in April. Our goal is to have another one at the, well, it's here called Observatoire Trappist, but actually it's also Ookhamden Observatory. So pointing this time to the east, indeed. Another possibility is to install a second one at University of Ben Guerir, so north of Marrakesh, and another one at Agadir, near Agadir, where Paul gave me a contact there. So that's the plan for this year. So to increase this network to 6 cameras, which is of course far from enough to cover the whole sky above Morocco, but this is the plan for this year. And this will be, I will quickly mention this project led by Catherine Kohlenberg, which is a collaboration between Belgium and Morocco in a sense to bring science, technology, education, etc., near Marrakesh and surroundings. And in that sense, my mission to Morocco and bringing meteor science to Morocco falls into this category and this project. So we will use this, and I think that's all I needed to say. That's
Thank you, Hervé. Any questions? All right. Well, thank you, Hervé. And next up, we have Bulchera from Tajikistan. Bulchera, go ahead. We can see your screen. We can see your presentation. Still can't hear you, but let me see. I'm going to ask you to unmute. All right.
Yes.
We can hear you now. Yes. And
Good. 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 Good evening. Good evening, everybody. Do you see my screen?
We do see your screen in the PowerPoint mode, not the presentation mode.
Just a moment.
Okay.
Okay.
Yep, looks better. You're
Yeah.
good to go.
Okay.
Thank you.
Thank you. Thank you very much. I am Kokhirova. I work in Institute of Astrophysics, National Academy of Science of Tajikistan. And today I would like to present some initial results of our video observations, which we performed in Tajikistan. We have joined to Global Meteor Network project 1.5 years ago, when we kindly obtained from Global Meteor Network management 2 sets of video cameras, and we have installed 1 set in Dushanbe city and second in Sangloh Observatory of our institute. And we have obtained first light from these 2 cameras in June 2024, and starting from this date, we began our video observations within a Global Meteor Network project. Our cameras have been registered in Global Meteor Network database, and all our data accumulated at the main server of this project. And all and photometric reduction of our images is performing using standard GMN protocol. So I not provide here details of such processing, and I would like to present some statistical results, statistical analysis of our first results. So starting from June 2024 to October 2025, our cameras in Dushanbe have registered more than 7,000 single station meters, and in our camera in Sangloh Observatory have registered more than 14,000 single meters, and among them, only 617 meters are multi-stations, namely were recorded simultaneously by both camera, and from Dushanbe and from Sangloh Observatory. Thus, we obtain precise data, full set of precise data for 617 meters. Here we can see distribution of multi-station registration of sporadic and showers meteors. You can see that majority amount present by sporadic background. You can see here, and second place we have more than 100 Perseids, and when we have southern delta aquarids, alpha capricornids, and so on. About 14 known meteor showers are presented by from 1 to 6 meters. Here you can see a distribution of registered meteors, distribution on maximum absolute magnitudes and absolute brightness. And we can see that main flux was contributed by meteors with maximum absolute magnitudes ranging from 0 to -1 magnitudes, and initial masses between 0.01 and 0.1 grams. Along with dominant component, meteors with absolute magnitudes in the range +1 and to 0, and -1 to -2 magnitudes, as well as meteoroids with initial masses between 0.1 to 1 gram, also made a significant contribution to total recorded meteoroid flux. This graph shows a distribution of observed radiance in ecliptic coordinates relative to position of the sun. As can be seen, observed radiation area covers a sky region extended from 0 to almost 316 in sun-centered ecliptic longitude, and from -15 to about +19 degree and in ecliptic latitude. And a more or less uniform distribution of radiance is observed with respect to ecliptic latitude, while distribution in sun-centered ecliptic longitude is noticeably non-uniform. And you can see that we have a deficit of meteors registered at this area, which is situated close to the sun, and thus is impossible to observe. And we can see here some clear concentration of some radiance which relate to known meteor showers, such as Perseids, southern delta aquarids, and so on. And we would like to consider some statistical analysis of activity, Perseid meteor shower activity in 2024. totally was registered 134 double station Perseids, and here we present distribution detected meteors with respect to maximum absolute magnitudes and initial masses. And these data show that meteors with absolute magnitudes between 0 and -1 magnitudes and initial masses from 0.001 to 0.1 gram dominated Perseid activity recorded by video cameras in Tajikistan in 2024. It should be also noted that meteors with absolute magnitudes in the range from +1 to till -2 magnitudes, together with dominant component, made a significant contribution to the total registered meteoroid influx. Dependencies of the beginning and heights of Perseid video meteors versus maximum absolute magnitudes and initial mass. Firstly, it should be noted that averaged beginning and height altitudes for video Perseids are indicated here. And second, we must point our attention to strong correlation revealed for altitudes beginning and end altitudes, correlation with brightness and with initial masses. And under this correlation is more evident for more brighter and meteors, and for meteoroids with larger initial masses. And we can conclude that for small-sized meteoroids, such as and for bright meteoroids for fireballs, we can these trends confirm ability to penetrate more bright meteors and meteoroids with larger masses, penetrate deeper into the Earth's atmosphere. Next, we reveal a strong correlation between initial masses and the maximum absolute magnitudes. Our linear fitting show correlation coefficient near to 1, which pointed to very strong correlation between these two parameters. And plotting radiant drift, daily radiant drift using our observations allow us to determine daily radiant drift for Perseids in 2024, and our estimations are very close to those obtained by Braun et al. And Shober et al. Using video observations of meteors. Next, we determine geocentric mean geocentric radiant for Perseids shower in using our observations and compare with data obtained within GMN project. As you can see, if geocentric coordinates of radiant slightly differ from those obtained by another observations, but sun-centered ecliptical coordinates very close to coordinates obtained within Global Meteor Network in previous years using very big data set. And this closeness confirm again reliability of and very good accuracy for calculation of radiant position for perceived meteor showers. And my conclusion, we present some statistical analysis of registered meteors, and such results demonstrate scientific ability of newly established stations in Tajikistan, and hope that they will provide a foundation for future detailed analysis of meteoroid physical properties, dynamical properties, for studying atmospheric interaction processes and meteoroid stream dynamics based on expanding multi-station data set. And our acknowledgement, again, we would like to express our deep gratitude to management of Global Meteor Network for supporting us by providing video cameras. And this work was supported by project of from Fund of Fundamental Researches of Tajikistan. Thank you very much for your attention.
All right, thank you, Gulchera. An important thing to say is that your cameras are strategically located in Central Asia and cover longitudes that no one else covers. And thank you for operating the cameras and collecting the data. Brilliant work. All right. Any questions for Gulchera? All right. Well,
thank you.
If not, yep. Thank you so much for the presentation. And now we're going to have a meal/question break for about 20 or so minutes until the full hour. If anyone would like to chat, the meeting is going to remain open. If there's a particular person you'd like to chat with, I will open the breakout rooms. So if you want to talk to a particular person, if there's a lot of chatting going on, please invite them to a particular breakout room. There are 3 named after meteor showers, and please go there and chat. So, all right, see you all in about 20 minutes.
Hello, can you see my screen?
Yes, we can. You're good to go.
Great. Yeah, so I joined the Global Meteor Network just 2 months ago, just before the Geminids, and I was very highly impressed by the high technical quality and the potential for scientific research. This is the first stack that I managed to get for the Geminids, one of the second or third day for Geminids, which was pretty impressive because I just had a day to install it and everything kind of worked out of the box. And at the moment, the situation in Romania is that we have 5 stations in total, out of which 3 started in December last year. So I'm going to talk about the current situation in Romania and the plans that we have, the cameras that I have built, and the live detection pipeline I modified, and as well at the end some kind of outreach with nice Telegram bot integration. So as I was saying, I have started building quite a few new cameras, 18 of them. Right now we just have 5 working. The 18th new cameras have been already sent to Romania, and they are basically already there, ready to be deployed. And then a host of individuals and organizations have decided to also help out. So for this year, our target is to have approximately 50 working cameras, thus basically covering the entirety of Romania with at least one station, and hopefully by the end of the year having a double station coverage. Special thanks goes to Pavol for sponsoring basically half of these cameras. And yeah, we did 3D printing for the cases, which was quite a bit of work, especially by Florin. He had to, we had a lot of back and forth, but then also actually building them was a bit tedious because there were lots of heat inserts and screws that I had to put. And yeah, in the end, I think I spent quite a few hours just putting screws in. Yeah, so it took me about a month to build this. In total, as I said, I managed to build 18, and I just sent the package, and it should be arriving in Romania quite soon. Why did we choose this particular hardware architecture? First of all, because the Raspberry Pi setup, although it's super nice in the sense of it's kind of easy to use and it's small and it's not that expensive, it cannot sustain more than a couple of cameras easily. While if we choose a mini PC, this one has enough computing power to do a little bit more than what a Raspberry Pi can do, and also the marginal cost is quite a bit smaller. As you can see, basically for a mini PC with 6 cameras, we managed to get it to about 100 euros per camera, which I think is really great, and that was one of the main goals of this experiment, let's say. Yeah, the second goal is, as I said, to have added computing power, because what we can do is we can detect live instead of doing the detection in the morning, and I mean running the entire pipeline in the morning. Yeah, so I did a little bit of testing in Berlin from my balcony, just to see how it behaves with the new additions to the software and stress testing. And fortunately, I also managed to get during this balcony testing the northern lights that happened a few days ago. And yeah, this is a live capture from the system. How does it work? The camera stream is being fed into 2 pipelines. One of them is the stock RMS software, which is then changed to do the analysis live. And when a meteor is being detected, then the other stream, which is in color, which is continuously written to a RAM buffer, it's being written down as soon as the machine learning filter decides that a meteor has passed through. Otherwise, we would end up with way too many detections without this filtering. Yeah, so if a real meteor is detected, then the RAM disk data is being written to the hard drive, and then yeah, I cut the color clip, and it's kind of arbitrary. I just chose 15 seconds for it. Yeah, and this is one example of the RMS station working live. from Berlin, yeah, the skies are not that great, and I also didn't really have that much time. But you can see the same meteor after the RMS detected live. The meteor already wrote the 4 clips to disk, and I was also a little bit surprised that it actually managed to work. But yeah, happy to see that happening. Yeah, regarding the performance with these particular mini PCs, which have a 6 cores available and 16 gigs of RAM, I would say that we are somewhere around 4 to 6 cameras, which is great news, because with 6 cameras we would be able to have basically an all-sky system. But there's still quite a bit more testing to be done. I just prefer to send the cameras now to have them installed, and then we have a lot more time to do experiments and develop this further. But with 4 cameras, there was no resource hog or resource problem. So I'm very optimistic about this working further. Now, the question is, why do we want to have live detection? And that is because outreach is also a very important part of the network. And there are quite a few people who are interested in, including myself, in seeing an event live and then having a look at their phone and being like, oh, that was this kind of meteor, getting a color clip that they could share on social media. And I started building the integration for a Telegram bot, which would basically gather the data from all of these cameras. And all of the brighter meteors would be pushed with video color clips to the channel. And also some kind of data about the cameras themselves and the meteor. You could have a subscription model for this bot, as in, for your entire country, or also for your own camera, if you just want to see the data from your camera. And also at the end of the night, I was thinking I could add an overview of the detections from the entire night. The LLMs have become good enough that they can interpret this data very well. Of course, they still hallucinate, but I was quite positively impressed by how nicely the summaries can look like. And it's also not something which is expensive. Yeah, the use cases, of course, would be, as I said, the public outreach to have fireballs instantly shared on various social media cases. Also, you can get some notifications regarding your own system if it's working properly, or if you have some unusual activity. And yeah, you can start a little bit faster with the science to recover the meteors. And yeah, this is, I kind of, so this is the current, on the left is the current status, and on the right is with the cameras that I already sent to Romania. I didn't put the other 30 that are still planned because it's already clear that we will have quite good coverage. And yeah, I was working quite closely with the largest and the most active association of amateur astronomers from Romania, Astromania, and we are going to also create a nice webpage where we can show this data in a coherent and aesthetic way. Yeah, so the next plans are to deploy this first large batch, test it, see if the software works properly, see what can be improved. Maybe the 3D printing is not perfect because it's the first time we have been doing this. And then we want to build a second large batch, supporting anyone who wants to install a camera in Romania. And then, yeah, as I said, building the web page. And I'm also very interested in trying out new sensors and maybe also getting into spectroscopy at some point. Yeah, that's about it.
Amazing work, Alex. I mean, this is exactly the kind of thing that we're encouraging, and then it comes out of the open source approach. And we're very happy that, after some testing, we'd love to have this as a feature of RMS. I think a lot of people would be interested in this. Amazing job. All right, Kevin has a question. Kevin, go ahead.
Hi. Yeah, I was wondering, I think this is really awesome. I've been thinking about a lot of this stuff a lot also, and I was wondering if it would be possible to incorporate like a live Aurora cam into that, because I know that there's a huge amount of interest in that. And I think that if that could be a feature that didn't interfere with RMS, it could draw a lot of camera builders.
Interesting. I'm pretty sure it can be done. So now I'm feeding the stream, as I said, to the stock RMS, but we could feed it to another detection pipeline that would be specifically tuned for Northern Lights. And given that, as I said, this particular system has 6 cores and is not too expensive, in my opinion, if you have a reasonable amount of computing power left, I think we could be doing this.
Cool. Awesome. Thank you.
All right. Any other questions? All right. Well, thank you, Alex. I think there is a lot of interest in what you're doing, and I'm sure you'll be hearing from people via email. All right. And next up is Patrick Shober. Patrick, go ahead.
Thanks. Okay. Okay.
We can see the screen.
All right.
You're good to go. Thanks.
Awesome. Yeah, so if you weren't here at the very beginning, my name is Patrick Shober, and I am currently a NASA postdoctoral fellow at Johnson Space Center in Houston, Texas. But today I'll be mostly talking about the work I did as a postdoc with Jeremy Valbayon at the Paris Observatory, where I was there from 2022 to 2024. So yeah, the name of this talk is The Case of the Missing Carbonaceous Chondrite, How Global Meteor Observations Resolve the Mystery. A little bit of background about me and the work doing. So my postdoc in Paris was mostly working with the Frippon team. Throughout the talk, I've included QR codes because it kind of goes over several papers of the research that I did during this period. This one obviously is just a link to the Frippon website if you wanted more information. But the Frippon network is a French-led initiative video network. This is one of cameras in the French Pyrenees. They have pretty extensive coverage, mostly centered in Western Europe, but as you can see, there's cameras all over the place. With most of France covered, and UK, Italy, and Romania making up a bulk of the cameras. For my PhD, I continued from my PhD in Australia. I continued working with the group, which has expanded into the Global Fireball Observatory, building off of the work done by the Desert Fireball Network, which is the portion of the Global Fireball Observatory in Australia. This camera network is mostly built off of high-resolution DSLR cameras, as seen here. The observing strategy is a little bit different, coming from the DFN. As you can see, the camera network in Australia is a bit remote. It's a little bit harder to get to, and they have to be durable for the weather and the insects and everything else that you find down there. Using data like this, we can obviously get orbital information, and that's what most of my PhD was looking at the orbits that we collected from the DFN. This shows just the inner solar system with the green orbits being the orbital database of the DFN at the time of the end of my PhD. As you can see, they do observe some streams, but the primary goal of the DFN, the GFO, and Frippon is mostly meteorite dropping fireballs. So the meteorite type that I'm most interested in is carbonaceous chondrites. My background is a bit mixed. I did my undergrad degree in geology before kind of switching towards astronomy. So most of my research is trying to kind of bridge this gap between planetary geology, people that look at the rocks, and planetary astronomy, people that are using telescopes or doing observations. This particular type of meteorite is very interesting because it's chemically the most primitive type, with chemical compositions most similar to the sun's photosphere. It's very minimally altered, and they're rich in water. They're hydrously alterated. So this one particular meteorite, this photo is of the Winchcombe meteorite, which you might be very familiar with. So my work in Paris kind of started to focus on these meteorites and specifically focusing on we call the cosmic ray exposure age. And try to explain this as simply as possible. Cosmic ray exposure age is basically just the sunburn for a rock in space. If something is within 1 meter of the surface of an asteroid, or it's a small meteoroid in space, it's being bombarded with cosmic rays, and this generates some radionuclides, specifically helium, neon, beryllium. And you can measure these isotopes in the rocks when they land on Earth, and you can use that to determine how long it was a small body in space. For meteorites, this is quite important, and it can tie back to the dynamics because essentially you could look at the rock and say, okay, the sunburn, the cosmic ray exposure age is this. That means it took this much time for the rock to come from an impact somewhere in the main belt, for example, and evolve, its orbit to evolve, eventually impacting the Earth, where all of a sudden it's shielded again, and we get this ETA essentially. Looking at carbonaceous chondrites, they're really interesting because these ages are really short. Without context, this graph doesn't really make sense, but these are the exposure ages for Ci and Cm carbonaceous chondrites. They're the most common, and they're also the youngest in terms of exposure ages. Most meteorites, most ordinary chondrites, are on the orders of tens of millions of years. Irons tend to be even longer, 100 million years. But carbonaceous chondrites, particularly Cis and Cms, as you can see, tend to be less than 2 million years. They're abnormally short. So for the beginning of my postdoc in Paris, the question for me was why? And one way we explored this is by looking at modeling the near-Earth asteroid population and basically saying, okay, this was right around the time of the OSIRIS-REx arriving to asteroid Bennu, the NASA's mission to near-Earth asteroid, which is a carbonaceous asteroid Bennu. And they observed particle ejections from the surface. So we were kind of intrigued by, or everyone was intrigued by this. And one of the things that we asked ourselves was, okay, if there's some mechanism happening in near-Earth space, just theoretically, let's not worry about the mechanism. But if you have some activity in near-Earth space from near-Earth asteroids, what would the CRE age distribution look like? So for carbonaceous chondrites, they're really short. And basically, what is the minimum age? If you have an object that's already near the Earth and it's ejecting material, what's the age you would expect? And that's what we did in this model. So this plot shows the semi-major axis versus eccentricity, and the colored background is the predicted CRE age from the model. The 5 points, hope you can see it. The 5 points in the plot show the 5 carbonaceous chondrites that were found at this point. And the color of those points indicate the cosmic ray exposure age. What we found was the pattern relative to the orbits matches really well to the model, but in some cases, the cosmic ray exposure age for the meteorites are actually much younger than even what the model expects. And certainly much younger than what you would expect for an object getting being released in an impact in the main belt and being transferred. For the Flensburg meteorite, for example, you have the 7,000-year cosmic ray exposure age, which is extraordinarily short and does not make sense. So you have these really young ages that are, in some cases, younger than what you expect for recent activity in Earth space. So maybe there's activity, maybe there's activity in Earth space, and that's what we asked ourselves. Are there streams of potentially large impactors in the Earth amongst meteorite dropping fireballs? Of course, we're familiar with showers and all this, but for meteorite dropping objects, are there streams? For the brevity of this presentation, there's a whole paper on this, and you can find it there, but the answer is no, not really. The statistics basically are in line with random associations. We don't see evidence of streams amongst meteorite dropping fireballs. So the CRE ages of some carbonaceous chondrites are consistent with recent activity near the Earth, but there's no streams. What's happening here? The other kind of important piece of information to know is that based on meteoroid transfer models, it's predicted that around half of all large impactors on Earth should be carbonaceous. So not only is, and for context, less than 4% of meteorites are carbonaceous. So a majority of them should be. They have much shorter CRE ages, but there's no evidence of recent activity. How will we explain this? So why are carbonaceous chondrites so rare? And if they're so young, why are there no trace of them in the impact data? To get at answering this question, this is where we turn to these video networks like GMN, like CAMS, like databases like Edmund. And I collected all of this data and used data mostly from GMN to characterize the impactor population at the top of the atmosphere versus the meteorite falls we find at the bottom. Because one of the primary explanations for this lack of carbonaceous chondrites is that they're weaker. The carbonaceous chondrites are very friable, they're very crumbly, hydrously alterated, and they're simply just not making it through the atmosphere, and that's the normal explanation. So we wanted to test this. So we used meteor observations with fireball observations from the GFO and FRIPON and from the European Fireball Network to basically get a orbital distribution for the general population using meteor observations. What's the general population looks like? What is hitting versus what is surviving? And what does the difference between those distributions look like? And does it correspond, like basically, what are we missing? What does the atmosphere filter? And does that distribution look like they're all coming from carbonaceous source regions in the solar system? So this is the plot of our paper. This shows inclination versus perihelion distance. Essentially, on the y-axis, as it goes down, you're getting closer to the sun. The red indicates these are regions where there are more meteorites originating relative to the top of the atmosphere population, and blue indicates regions where there's less meteorites relative to the top of the population. And basically what we find is that at lower perihelion, the most important thing we don't find, I guess, is that the regions where the meteorites are missing is not coming from carbonaceous source regions. what we find is that objects that have lower perihelion distances, in other words, they're close to the sun, or have histories that are consistent with previous perihelion distances that were close to the sun. This pattern right here, all these lines, basically just mean that it's in this resonance, and the resonance can push the perihelion down to much lower values. So even if it's higher up here, like in the top right, it was in the bottom left in the past. So, but what we find is essentially these bins are much more likely to drop meteorites because the carbonaceous meteorites, the carbonaceous meteoroids that were in these bins before were already filtered before impact. They're being removed even before the atmosphere has a chance. And one of the reasons I think this ties it all together, this is observations of boulders from a paper on studying boulders on the surface of near-Earth asteroid Bennu. And essentially what this plot shows is thermal inertia versus surface abundance of fine regolith. And all this mean to say is that as the boulders get denser, they break up more easily under thermal fragmentation. These cycles in temperature thermally break down the rock. And I think how this ties to the meteorite population is essentially the objects that are the most likely to survive our atmosphere are the most likely to thermally fragment in space. You have this first filter, it's not getting through. And the objects that are more porous are more likely to survive in space, but they're not likely to survive the atmosphere. So the only way you can get carbonaceous chondrites, these meteorites, is that you need something that's dense, but it can't survive the first filter, so it should impact quickly, resulting in the short cosmic ray exposure ages we have. So in summary, you have thermal fracturing in space that's removing basically half of the meteoroids that are impacting the Earth. Then the rest needs to still survive the atmosphere, and then you get your rock on the ground. Thank you.
Amazing. Thank you so much, Patrick. Any questions for Patrick? And just to indicate that this work has been published in Nature Astronomy, so congratulations on that.
Thanks.
Shows you the impact of what you do, and what kind of research that our data can support. So
yeah, a lot of the research that I've been doing recently would definitely not be possible without networks like GMN, 100%.
Thank you, Patrick. And we're closer to resolving the mystery of why we're seeing so few carbonaceous chondrites. But one of the open questions is definitely what kind of filter the atmosphere actually provide. Quantifying the atmospheric filtering instead of saying, hey, it's just kind of a fuzzy filter. You've done a really good job on the orbital filtering part. So there's definitely still some open science questions in the atmospheric domain.
Definitely.
Brilliant. Thank you, Patrick. And with that in mind, now we're going to hear from Chloe, who might provide us an answer on the atmospheric part. Chloe, go ahead.
Hey everyone, I'll just share my screen.
All right.
Can everyone see this okay?
Looking good. You're good to go. Thank you.
Okay, awesome. So hi, if you missed my intro at the start, just to say my name's Chloe. I'm a second year PhD student at the University of Manchester. And today I'll just be talking about a project that I'm working on with Denis and collaborators to basically compile a complete up-to-date data set of GMN fireball observations. So this is a schematic that I feel like everyone will have seen in some shape or form. But when a meteoroid, which can be several micrometers to several meters in size, enters the atmosphere, if it's got large enough mass, it can form a meteor, or if it's brighter, a fireball, or even brighter, a bolide. And these can be sort of observed by the GMN cameras. And then if the mass is large enough, it can drop meteorites. So for my PhD, I'm mainly focused on sort of that final stage of flight, the dark flight of meteorites. But in this project, we'll sort of be taking it back and taking these observations from GMN cameras to work out the orbits and to see like where these objects are actually coming from. So this is a bit of a out-of-date map. It shows the GMN coverage in 2024 with those sort of lighter red regions showing the fields of view at the height of 100 kilometers. So we see that this data set would be great to sort of fully compile and take advantage of for this project, just because it's got such global coverage. And from this data set, we can work out the orbits. So the orbits of these meteoroids around the ecliptic plane, which we can see sort of shaded. And this just shows quite a high inclination meteoroid orbit. And it's sort of fully contextualized by the 6 orbital parameters that are displayed here. I think Patrick showed a really cool video of an orbit, so this is a lot less cool. So this is from the NASA Eyes on Asteroids website that shows sort of where everything is at the moment. So I think this was literally just from a couple hours ago, earlier today. And yeah, so what this project will allow us to do is to work out if there are any source regions in the solar system that will then in the future have a higher probability of being a meteorite dropper. So yeah, so are there any source regions in the solar system? So the GMN Fireball database has not yet been fully consistently remeasured. So this is a problem that this project sort of aims to tackle. And then with the end goal of it being publishable and open access with the trajectories and the orbits, but just not the station locations for operator privacy reasons. And once this data set has been compiled and then fully cleaned, then it will be a great position to obtain the flux measurements and to work out if there are these meteorite source regions in the solar system. And yeah, we also plan to quantify the flux of different types of material, so rocky and carbonaceous, and also use these novel terminal mass estimation methods to compute the actual distribution of the delivered mass to Earth from various sources and types. So why is this actually important? So these empirical constraints these allow us to put empirical constraints on solar system formation and dynamical evolution. For example, in this paper by Denis and collaborators in 2023, it's a good example from material from the Oort cloud. It also allows us to characterize near-Earth objects, which is super important for planetary defense, and also understand the behavior of material in Earth's atmosphere, as well as its survivability, which I know Patrick talked about, and also finally to link recovered meteorites to their source regions. So this final point is actually quite exciting because this figure shows all of the falls up until 2018 that have got information of their corresponding escape route from the asteroid belt or their source region. So you can see sort of on the y-axis of this plot are all of the falls, so the names of the falls, and then the x-axis shows their escape route or source region. So we've got the Hungaria and Phoenicia. I don't know if I pronounced that right, but those asteroids. We've got secular resonance with Saturn, which is the second one, and then we've got the 3 mean motion resonances with Jupiter, as well as Jupiter family comets. And then the size of the circle sort of indicates the probability that that is where it's come from, or that's its escape route. So we can see in this plot, which was from Grenvik and Brown in 2018, we can see that there's only about 25 falls, I think, but the GMN database would allow us to basically fill this in on the mass scale. So we can see how advantageous that would be. So the future work, this work is still in its early stages. So I've done sort of the first pass of the observations that we currently have, which is about 150. And that was just to see sort of what have we got, is there anything missing? But the future work would be to fully recompute the trajectories and the orbits using the most up-to-date methods to make sure that it's as complete as it can be, and then making it open access once it's all cleaned and ready. And then to use this database to identify these meteorite source regions in the solar system, and then potentially linking this calibrated flux of meteorite dropping fireballs to the flux of meteorites at the Earth's surface, so to tie it all together. And then I think it's good that I'm giving this presentation so early in the stages of this work, because if anyone who's listening does have sort of any data from the GMN that they might be willing to share to append to this database, yeah, please do get in touch with either me or Denis. I've put my email on the next slide. So thank you very much.
All right. Thank you, Chloe. Any questions for Chloe? All right. General idea is we want to collect all the fireballs. We want to calibrate the flux, see where they're coming from, how many they're coming. Yeah, Gina has a question. Gina, go ahead.
I'm curious, how does she or do you define a fireball?
I think so. There's meteors, which is like the faintest streak of light, then fireballs, which is slightly brighter. So I don't have the magnitudes in my head at the moment. And then even brighter than that is bolides. So it's based on the magnitude, I think.
Yeah, so just for Gene's sake, what we want to do here is quantify the amount of meteorite delivery on the ground. So we are going to use our dynamic mass estimation method. And if there has been no meteorite delivery on the ground, even a couple of grams, then that is not counted in the counted as a viable fireball in the analysis. So we're just primarily interested in where does stuff that falls into Earth come from, and it's purely going to be driven by what do we determine. If there is no mass delivery underground, we essentially don't care about the fireball.
So how do you know that? How do you determine whether or not there's been mass delivery on the ground?
Using our dynamic mass estimation method. So in our WMPR library, we put in, we look at the end of the fireball, we look at the deceleration, we assume a certain density based on the other ablation properties, and it spits out a number. If the number is consistently 0 or very close to 0, we're not going to count it.
All right, I understand. Thank you.
Awesome. Thank you, Gene. Okay, let's see. We actually have a few more minutes if there are any other questions. All right. Tamer, go ahead.
Perhaps you should just rephrase the title of talk and the complete work you're doing. It's not related to all the GMN fireballs, but to meteorite dropping fireballs, because this may be misleading if stated in this way.
Thank you for the suggestion.
All right. Thank you. Okay, well, we will move on now. So Miriam, I can't make the meeting, but she sent a recording, and she's doing something that's not necessarily connected to meteors. She's a part of a citizen scientist network of comet observers, and this is fairly close to what we're doing, and she wanted to communicate her experiences. So I will open her recording, and I will share my screen. This one here, share sound. All right, and I'm going to play it.
Hi, I'm Mirjana Malarić from Zagreb, Croatia. Since my teenagers, I'm an astronomer amateur with special emphasis on observing meteors. In 2010, I joined Croatian Meteor Network and afterwards Global Meteor Network. I work in vocational school teaching electronics and computer science, trying to get my students interested in astronomy. Cumbres Observatory is a non-profit science institute with the mission of advancing science and education, founded in 2005 by Wayne Rosing. It consists of 25 telescopes at 7 sites around the world, working together as a single instrument. Comet Chasers is a UK educational outreach project linking school with professional and amateur astronomers. Fox Telescope Project and the school's observatory, free educational astrophysics website. It uses Las Cumbres Observatory worldwide network of research robotic telescopes to monitor outbursting comets and make scientifically useful observations. Observations are going through the LCO observation portal where the requests are made. You choose the type of telescope, object and parameters and time of exposition. Furthermore, system takes care and you get the photos. Objects of interest are: first, Comet 12P Pons-Brooks, one of the brightest periodic comet orbiting the Sun every 71 years. It is first identified in 14th century, undergoing many outbursts and change in magnitude. Comet 12P Pons-Brooks is possible cause of the weak December Kappa Draconis meteor shower. We continuously observe outbursting comet 29P Schwarzmann-Wachmann 1 or 29P SW1. It was discovered in 1927 while exhibiting a strong outburst in brightness. This photo shows two outbursts at the same time. Outbursts are the result of sudden eruptions at the surface of the nucleus, about 60 kilometers across. They typically happen 20 to 30 times each year. You can follow results and data on British Astronomical Organization page Mission 29P. We are regularly contributing with our observations. Here is interstellar comet object 3I Atlas, third known object to passing through our solar system, with nucleus from 500 meters to 5 kilometers roughly, traveling around 240,000 kilometers per hour. It is scientifically important because its differences from the comets in our solar system may provide insight into the composition of other solar systems. Here is our photo of non-periodic comet C/2025 K1. Since discovery in May 2025, it has broken into 5 fragments. Fragments are traveling together. You can see them at our photos. Maybe we'll soon discover a new meteor shower caused by this comet. Comet Chaser project pages, there are more activities, especially for primary school students. But in my school we are proud to our observations and our contribution to scientific results. Comet Chasers project is not only meant for pupils and students, but anybody can also participate. For instance, Mr. Alan Hale, who discovered Comet Hale-Bopp, recently joined. If you have any queries or would like to be a part of the project and/or sign up for the FOX Telescope project, contact Helen or Mirjana. See you!
All right, and that is her talk. It looks very interesting. I believe anyone can join and do a bit of comet observation. If you have any questions, please reach out to her. And the final talk of this short session is Auriane's about 2023 CX1, the final, how'd you call it, the autopsy of the small asteroid. Auriane, go ahead.
Okay, hi everyone. Yeah, I'm very happy to can finally present kind of like a complete summary of the 2023 CX1 project. And even if I'm the one giving the talk today, you must know that everything I'm going to show here is actually the result of a very large international collaboration, which also involves several members from the GMN community. In total, the 2023 CX1 collaboration comprises 97 scientists from 22 different countries and more than 100 citizen collaborators, which really helped us retrieving the meteorites or collecting and analyzing the data. So if you're interested in learning more about the project or the collaboration, feel free to just check our Nature Astronomy paper from last September. So many of you know this object, but I'm gonna give a couple reminders about the asteroid 2023 CX1. I'm just going to call it CX1. Was discovered by the Hungarian astronomer Tristan Abbott on February 12, 2023.
Did Auriane drop out for you too?
Yes.
All right. That's not good. All right, let me try to get in touch with Auriane. Yeah, no answer. I'm not sure what happened. I hope it's not a giant power cut in Montreal where only Auriane lives. So I suggest we adjust our schedule. And instead of her talk now, we maybe push to break in the extended session period now, and then when Auriane joins back in, we'll continue. Okay, so are there any questions for any previous speakers? Alex, Patrick, Chloe? Any questions that we didn't cover previously? Oh, there's Auriane.
Hi, sorry.
All right, I'm not sure what happened there.
I don't know. I don't know how long I've been talking alone.
It's been a few minutes. It's right. I think we've seen essentially just the first slide, and then you disappeared into the abyss.
I'm so sorry.
If you don't mind going from there.
Okay. So, sorry. Just give me 1 second. I don't have anything running here. I don't know what's going on. My apologies. So, do you see my screen?
Yep. Yeah. You should be good to go now. All right.
Okay. Did I have a chance to say everyone was involved in that?
Yep. Yeah. I think after the first slide, you're good to go.
Okay.
Awesome.
Yeah. Sorry, I'm gonna start again. But yeah, so if you're interested in learning more about the project or the collaboration, please just check out our Nature Astronomy paper from last September. I'm gonna give a couple reminders about this body, even though many of you already know about this event. Asteroid 2023 CX1, I'm just gonna call it CX1, was discovered on February 12, 2023 by the Hungarian astronomer Tristan Abbott. Back then, it was at about 0.6 times the Earth's moon distance, and it was estimated to be a very small object, roughly 1 meter in size, but it was on a collision course with Earth. And that was quickly confirmed thanks to follow-up observations carried on by multiple observatories over the world. And thanks to a very detailed tracking and a novel observational strategy that was deployed by ESA, space agencies were able Okay, just checking that everything was okay. So the space agencies were able to predict the location and timing of the impact with great accuracy. And the asteroid was expected to enter Earth's atmosphere somewhere over the English Channel on February 13, about 7 hours after its discovery. And that was really exciting because discovering an asteroid just before it collide with our planet is still a rare event. And in that case, it was just perfect because CX1 was very small, so it was totally harmless, but it was entering the atmosphere at night over a densely populated area. So it just offered an amazing scientific opportunity to study it. And that's why the space agencies, camera networks, and also citizen science projects like the Fripon Vigicial project in France encourage people just to stay awake, go outside, and watch and record the event. And the result was amazing. As expected, a bright fireball appeared at night on February 13 at 2:59 UTC. And it was recorded by several camera networks like Fripon in France and by Global Meteor Network cameras also located in the UK, the UCMO network. These are the videos you can see here on the right part of my slide. And this is not the only data we gathered during this event. We received multiple video records of the fireballs taken by people from several countries, France, the UK, Spain, Netherlands, Belgium, and Germany. And this is just like, you can just see a few of the most beautiful ones here on my screen. So observing the atmospheric entry of the asteroid was truly a worldwide observation effort. And a very nice illustration of that is this video that was shared by Hadrien Devillepoix. Hadrien, he's a colleague from Curtin University, so he's located in Australia, but his family lives in Normandy, so very close to where the impact was predicted to occur. And so he coordinated with his family to make sure that they would actually watch and record the event. And I have a very short video of him like giving instructions to his family, so in French.
Allez, dans 15 secondes, là, tu déclenches Vic, dans 5, 4, 3, 2, 1... C'est parti. L'appareil photo est déclenché?
Making sure everything is turned on.
Allez, il n'y a plus que quelques secondes maintenant, normalement. C'est parti. Wouhou!
Ah, c'était magnifique.
So Hadrien mentioned to me that his family agreed to stay awake, but they say, "Oh, you'd better maybe." I mean, we hope it's going to be worth it, and we're expecting like a full show with light and sound. And they weren't disappointed because this is what they saw. You clearly see the fireball appearing in the sky and then suffering the fragmentation. You actually have like two big flares, as you can see here, and the light disappeared quickly after that. And what's amazing with that video is that we clearly see how several fragments separated from the main mass around an altitude of 29 kilometers. And this video taken by Hadrien's family is one of the best one we have to study the fragmentation of the body. So that's for the optical data. We also have different kind of data about this event. And in particular, we were able to detect the seismoacoustic signal that was produced by the atmospheric entry as far as 5,000 kilometers away in Russia. This signal was recorded by several CTBTO stations and dedicated infrared arrays in France and the Netherlands. And we also recorded the seismic signal that was produced by the event in France and in the UK. So shortly after the fireball appeared and everything was confirmed, the priority was to collect all these data to compute the trajectory. So we collected data from the Global Meteor Network cameras, from Fripon, all these targeted videos you just saw. And thanks to that, Denis was able to compute a trajectory for the asteroid, which is the one you see here. And so we knew that some fragments had landed somewhere in Normandy in France. And in just a few hours, less than a day, Denis and Hadrien were able to provide and compute a first strewn field for the meteorites, and is the one you see here. So the strewn field was quite long. It was extending between the cities of Autigny and Angers in Normandy, so 8 kilometers long. But it was amazing because, I mean, it was released really, really fast. And that was necessary because the Fripon Vigicial team was already there on the ground in Normandy, just ready to start searching for the rocks. So they were just waiting to have like just more information about where to start searching for the meteorites. So in the hours, days, and weeks that follow, they've been scanning the region. Some places were easy to search. Other ones were a bit more complicated. I love that picture because here my colleagues were just trying to find tiny pieces of the asteroid. Actually, a big meteorite like smashed on a tennis ground near Otigny, and some of the fragments were just too small to be perceived when you were standing up. But they did an amazing job, and actually in just 2 days, so 2 days after the fall, the first meteorite was recovered by Loïs Leblanc, which is a student part of the VGCL project. And so they found that this first piece of 93 grams that you can see here on the picture. And in the weeks that followed, many more fragments of the meteorites have been retrieved. In total, more than 100 fragments were recovered along this line you just saw of 8 kilometers, totaling a mass of 1.34 kilos. The meteorite is officially named Saint-Pierre-le-Vivier, and it was classified as an L5-6 chondrite breccia. So it's an ordinary chondrite. And that's actually kind of cool because, as I mentioned, detecting an asteroid in space just before it enters in the atmosphere is still pretty rare. We are seeing each time more and more of them, but we only have 11 imminent impactors that we have recorded in the past. And over these 11 cases, only 4 dropped meteorites on the ground that were retrieved. And these are the ones you see here in Africa and Europe. And when you look at these cases, actually, there's only 2 events for which we also have atmospheric data. The first one was 2023 CX1, and the second one is the one that occurred in Germany 1 year after that. And when you look at these 4 meteorites, well, most of them have a very weird type. You have uralites, obrites, and so they're kind of like not very frequent. But CX1 is the only ordinary chondrite that we detected in space before it fell onto Earth. And that's great because L chondrites represent about 38% of the meteorites you're finding in the meteorites collections here. So it's really representative of the kind of material you're going to find on Earth. So the dispersed fragment you just saw on the photo was sent for laboratory measurements very, very fast. Actually, so fast that we were able to detect very short-lived radionuclides, including the vanadium-48, which has a half-life period of 16 days only. It's not the only fragment that has been analyzed. We analyzed 7 of them in different laboratories across Europe, and many measurements were performed, so petrography, bulk chemistry, short-lived, long-lived radionuclide analysis, and also cosmogenic nuclides analysis in general, like noble gases. All these methods were used to constrain the body's nature and collisional history. So we were super happy. We'd seen this body in space, found the rocks, and it was just a great success for the planetary defense community in general, because the prediction was amazing. It also highlighted the role that the general public is playing in this planetary defense network. But so now we started just the phase where we needed to analyze this exceptional event, because for the first time in history back then, we had data of a small asteroid in space, in the atmosphere, and in our labs. And by analyzing this body in all the different mediums, using different data sets, different rejection techniques, that's great because it really gives you complementary analysis about this body, and you can really constrain its nature, structure, composition, and history. So I'm just going to summarize a bit quickly the findings we obtained with this study. But if we just start with the telescopic observations, we have 22 observatories that targeted the asteroid before it entered into the Earth's shadow. So we carefully reprocessed all these data sets to improve the astrometry and the photometry. So if we start with the photometry, the goal was just to construct the light curve of the asteroid, so measure the variations of its brightness in space, because if you find a periodic signal in this light curve, that will give you information about the shape and the rotation period of the body. Unfortunately, the light curve of CX1 was extraordinarily flat. We didn't see any periodic oscillation of the magnitude, and we tried really, really hard. which could be due to several reasons. Maybe we were super unlucky and we observed it from a pollen orientation. It was spinning like that while it was falling down. Maybe it was an extremely fast rotator, but another option is that CX1 was maybe roughly spherical. As I mentioned, we also work on the astrometry, refine the measurements positions for the body, and these enable deriving a very accurate pre-impact orbit. And what's interesting is that thanks to all the optical data we gathered of the fireball, we also had a very accurate fireball trajectory. Here you just see the residuals of the trajectory solution that Denis computed. So it was an amazing opportunity to just compare both data sets, the orbit we had from the telescopic measurements and the trajectory of the fireball we computed thanks to our cameras. And so to do that, we just compare the predicted position of the asteroid at a reference altitude of about 100 kilometers. So computed with the telescopic data in red and the fireball data in blue. And we found an offset of about 90 meters in the predicted impact location. And 90 meters might seem small, but when we just looked at the quality of the data we had, we were surprised by this number and we were expecting something lower. So we started investigating this, first looking into the meteor data, then the telescopic data, and we realized that actually the main reason of this discrepancy came from the telescopic data, but not because the measurements were bad, but just because we found lots of uncertainties or errors in the geographical coordinates of the observatories that were sent to the Minor Planet Center. Actually, we found that about 55% of these observatories reported heights, thinking they were heights above the ellipsoid, but they were actually heights above the mean sea level. And depending on where you are on the planet, these can change your altitude by a few tens of meters. So we alerted the MPC about that. The MPC updated the coordinates. We were able to recompute the orbit from the telescopic measurements, and that reduced this offset we had to lower than 30 meters, which is the difference between the purple pink curve and the blue one here. And this agreement was so good that it also enabled cross-calibrating the telescopic data with the fireball data. And we could use the first position of the fireball that was detected by our cameras to anchor the last portion of the orbit of CX1. And that really reduced uncertainties on the orbital solution and made of Saint-Pierre-le-Viger one of the most accurate meteorite orbits ever measured. So what do we learn from this orbit? Well, that like most L chondrites, CX1 likely originated from the inner main asteroid belt. If we use the model developed by Marseille, Brosse, and Vernazza, published in 2024, we see that CX1 has a high probability of coming from the young Massalia asteroid family. It comes from an asteroidal family from the inner main asteroid belt. And from the cosmic ray exposure age of the meteorites, so I'm glad Patrick really explained how that works, we know that CX1 separated from the parent body 30 million years ago. Another cool aspect of this analysis is that we were able to compute the initial mass and size of the body using 7 independent methods, including those based on the asteroid magnitude, on the light curve of the fireball, on the infrasound analysis, and several cosmogenic nuclide concentration like neon, aluminium, or cobalt using different techniques. And all these methods converge towards a preferred value of 72 centimeters in diameter and a initial mass of 650 kilos, which means that I've been lying during all this presentation when I called this body an asteroid because it was just a big meteoroid. Another key point of the analysis was the strewn field modeling. And actually, I remember seeing this animation at the GMN meeting of 2023. Denis just showed that after, I think it was Mark McIntyre's presentation. So this was in an animation of the dark flight and the strewn field that Denis produced back then, 2 years ago. This strewn field and the one published by the Czechs a few hours later were really used to orient the teams that were on the ground searching for the meteorites. But once they retrieved meteorites and we know their exact location, we had the opportunity to refine the strewn field computation. And this is kind of the final figure we have in the paper. I'm not going to describe here everything, but just to give you an idea, all the blue dots and crosses are the location of the meteorites that were retrieved, and the size of the circles depends on the meteorite's mass. And all these bananas you have of different colors and lines are different strewn field models that depend actually on several parameters, like when the meteorites separated from the main mass. So here they separated during the flares you just saw in the video. And here in this region, they likely separated closer to the end of the visible path. So from this strewn field model, we learned that actually all the small meteorites that were retrieved north of Hadrien really were ejected during the flares that we see in the video. If you remember all the fragments that we could detect in Hadrien Devillepoix family, yes, are you working? Okay, video from the beginning. Well, if you model just the dynamics and the evolution of these fragments, these are their estimated landing location in red. And we see that actually some of the large meteorites we recovered match these individual fragments. Another surprise was that there's a main mass that's still missing, the one just here. There's potentially a 2-kilogram rock that is still waiting to be discovered. So if you ever go to Normandy and you want to still searching for it, please do so. And actually, the strewn fields that were completed explain really well the distribution of the meteorites we found. There is just still some kind of uncertainty about this fragment here, the number 4, and this concentration there, because we have two competing scenarios which can explain their location. The first one is that they separated somewhere between the flare and the end of the visible path and landed here. And the second one, these are the yellow dots that just appear, is due to another effect. We realized that after the flare, we had a visible deviation of the direction of the main mass by about 0.8 degrees. So maybe the main mass went from one side, we had kind of an asymmetry in the ejection of the other fragments at the flare. And these are kind of these yellow dots that can explain the location of these meteorites located at the southeast of Hadrien. The thing is that the data currently cannot help us discriminate between these two scenarios. Both are plausible. And so to investigate into that, we can look at laboratory measurements and cosmogenic nuclide concentrations, because we have sampled several meteorites. Okay, that works. Along the cross field, these are all the ones that have kind of like a purple circle around them. And you have like some isotope concentrations, like for example, neon, that will give you information about how deep these meteorites were buried down, in the main mass. So whether if they were coming from the surface or the interior of the meteoroid. And in this case, we realized that first we had a remarkable homogeneity among the samples, and we had absolutely no correlation between the isotope concentrations and the position of the meteorite in the strewn field. And that indicates two things. The first one, that, well, maybe CX1 was too small to develop, a full nucleonic cascade in its interior. But the second one is that it's likely that it's fragmented in a weird way. And actually, the fragmentation happens so abruptly that it released material from both the surface and the interior all over the strewn field. And that's what's been confirmed by the optical data. In this plot, you see the light curve of the fireball. So you see that the magnitude is just slightly increasing, and then you have these two consecutive flares at heights of 27, 29 kilometers. It's very cool to know that actually these fragmentation events were confirmed independently, so both the timing and the position by the seismoacoustic analysis. CX1 reached very, very briefly an absolute magnitude of -17. So I guess we can still call it a super bolide, even if it was short. But what's interesting with the light curve is that we see that he didn't have any significant mass loss or fragmentation event before these two flares. Actually, nothing happened here over here. It lost maybe 30 kilos of material at most, and then suddenly during the flare, it lost 98% of its mass. So during this big double breakup we see in the videos. And this occurred at a dynamic pressure around 4 megapascal. You're probably familiar with that parameter, but dynamic pressure is just a parameter based on the speed of the body and the atmospheric density. And we use it as a proxy to say, okay, the body is going to fragment when the dynamic pressure exceeds the cohesive forces that are holding the rock together. And actually, this kind of behavior, so nothing happened and then just a big boom, is not very typical of what we observe for meteorite dropping events. When we compare that, it's actually very different from the 22 events that were analyzed by Borovic et al. In 2020, and this is the figure you see here. So for most meteorite dropping events, what you're going to see, if you look at the mass of the largest fragment over dynamic pressure, you're going to have a first fragmentation event at low dynamic pressure, and this is usually when the meteorite is going to lose most of its mass. And then sometimes this stage is followed by a second stage of fragmentation at higher dynamic pressure. And this is not what we observed at all for CX1. Actually, almost nothing happened over there until suddenly it lost almost all its mass and kinetic energy at high dynamic pressure. So actually, when you look into the literature, we found 4 events that had a similar behavior. Unfortunately, for 3 of them, we can't analyze them much because some crucial information is missing about the trajectory sometimes. Sometimes we just didn't retrieve the rocks. But there is one case that's well documented of a body that showed a similar behavior, and that one is the Novo Mesto fireball. Novo Mesto is a fireball that was observed in Slovenia in 2020, and it also dropped L5 meteorites on the ground. And just like CX1, it didn't show any signs of early fragmentation. And then suddenly around 3 megapascal, it lost 80% of its mass. It produced like a 0.3 kiloton airburst that was perceived as a minor earthquake on the ground. So we have these 2 bodies, likely of similar origin, both dropped L5 chondrites on the ground that just fragment in this weird way, releasing all their energy at once. And not showing this kind of progressive fragmentation we can see in other bodies. And so CX1 seems to confirm the hypothesis that was proposed by Denis in 2021 following the Novo Mesto event, is that maybe we're seeing a new class of L-chondrite-like asteroids that are able of producing disproportionately large airbursts compared to their size. So I'm going to conclude just right here, but what I love with the 2023 CX1 study is that it's the first complete autopsy of an L-chondrite fall that has been enabled by international collaboration, multi-network observations, and multidisciplinary analysis. It was a great, real life test case of our planetary defense strategies. The impact prediction was one of the most accurate that was ever made. It also showed the implication of the general public in the planetary defense network. And thanks to this multidisciplinary analysis we've done, we're able to validate some of the prediction techniques and to improve some of them as well. Among other findings, what the paper shows is that we're supporting the Vida 2021 hypothesis that we maybe are seeing a subset of the L-chondrite-like asteroids that produce disproportionate airbursts relatively to their size. And that can have implications because, of course, CX1 Novo Mesto were very small. They were totally harmless. But what if we have another body from this same family, but larger in size, that just one day entered the atmosphere and behaves the same way? Well, we're expecting this sudden release of energy closer to the ground to affect a larger area, so at the surface of the planet, than the bodies that are gradually fragmenting, for example, like what we observe for Chelyabinsk. And so why this happens remains a bit uncertain. It can be due to the geometry of these impactors, so their rotation, their trajectory. Another possibility is just the properties of the material. Both bodies show a dense network of shock veins that maybe somehow like are gluing the rock together. Maybe it's a combination of several factors. We don't really know because unfortunately we have limited statistics and only a handful of impactors that are well characterized. But this is likely to change because, of course, we have rapidly increasing detection capabilities. We're seeing each time more of these small bodies before they enter the atmosphere. And we also have these expanding camera networks and observer networks, and that, of course, includes the GMN. So I really think that this will allow us to better identify, quantify, and characterize this population. So thank you very much. And yeah, I'd be happy to answer any question you may have.
Amazing talk, Auriane. Thank you. And there is already a question in the chat by Michael O'Connell. Michael, would you like to repeat your question out loud, or should I read it?
Sure, that's okay. Great talk, thanks. Just a question there on incorporating atmospheric wind speeds into the dark flight model. Was that done, and how much of an impact did it have on the fall location? Thanks.
So yes, that was done. Denis, feel free to correct me if I'm mistaken here, but several models were used, including one from a weather balloon launched at Hermannsö and other ones that are more global. And it indeed made some differences in the Struenfeld location by, I would say, I don't know, was it like 2 kilometers, maybe 1 kilometer? It was shifting like, the global, it was shifting the Struenfeld location this way. But that's why it was great to find the meteorites quickly. Well, the first estimate was great because they all found a first fragment in only 2 days. But after that, once more meteorites were retrieved, that's what enabled choosing, what wind model was the best to use and validate her hypothesis.
Super, thank you.
Yeah, so it was interesting. For example, the first estimate that I provided was using the radiosonde data from Hermannsö, and which is across the channel, not really in mainland France. It was the first one. It was the closest one that we had, and I produced simulations of fragment locations using that wind model, and then an end ejection. And the first one that was found, Auriane, correct me if I'm wrong, but it was that exactly was that one here. And if you didn't use a wind model at all, it would just be all completely off. And then because it had such a pronounced bright fragmentation point, then the next strategy was to produce simulations of very small fragments at that major peak. And then using the same wind model, when I provided that strewn field, they found dozens and dozens of little fragments exactly where they were supposed to be found. Now, interestingly enough, when we used a more advanced assimilated model using the WRF simulations, it was worse. And that didn't really match the finds really well. So it was, I would say, we were fairly lucky that the wind model from across the channel worked perfectly, and it was spot on. Otherwise, it was, I think, significantly off that it wouldn't be able to find anything. So,
just to follow up on that, perhaps, given the major effect it has on the expected Struenfeld location and the likelihood of actually having any recovery. Is there merit, or is there normally time in these kind of events to actually launch a weather balloon in the immediate location around the expected time to try and more accurately refine the wind model?
Yeah, I don't think we have that level of logistical organization, let's put it that way. Yeah.
Well, you'd be more linking up with a local Met service. I mean, I presume most national Met services would be launching weather balloons.
Yeah. It's a good idea to connect to those people. But there is another startup called Windborne that flies weather balloons constantly around the world. Instead of just doing profiles from one location every couple of hours, that startup that recently got founded is flying hundreds of balloons at all times that are just traveling around the world, and the altitude just go up and down for, I think, weeks on end. So that might be another source of data, and I think it's being assimilated into the GFS model. So it's something that hopefully might improve the quality of winds in the upper atmosphere. So here's hoping. All right. Any other questions for Auriane? All right. Well, if not, we have an important event now, and that is the group photo. So please turn on your cameras, and you may or may not choose to smile depending on your disposition today. All right. All right. And I will take screenshots. So I have 3 pages here. Let me see if I can somehow increase the number of videos that I can see on a single page. And it doesn't seem possible. So what I will do is I will first take a screenshot of the first page. 3, 2, 1, cheese. All right, that's the first screenshot. Let's see. That's number 1. All right, second page. 3, 2, 1, cheese. All right, and that's the second page.
You would know at which page are we?
You just gotta smile. That's the only choice. All right, and here's the third one. 3, 2, 1. All right, awesome. I'm gonna save it. Perfect. And yeah, so now we have a break and an extended question period until 30 minutes after the hour, so which means another 7 minutes. Feel free to ask questions, chat, take a break. See you all in about 7 minutes.
Thanks, Pips.
many cameras suffering bad weather?
It must be partly due at least to the UK, because we've had several nights recently with 0 detections in the UK, and that's very rare. And because there's about a couple of hundred cameras in the UK, it's punching in terms of the contribution it makes to the network as a whole. So that would drag the numbers down for certain.
Mm. Yeah, I also noticed snow has been a problem this year. I think there are many cameras covered by snow this winter.
Yeah, not too bad this way. We've had a couple of snowfalls, but not bad at all this season.
Yeah, here in Belgium, depends a little bit from the area. If you are in the eastern parts, once there is ice on the cameras, you don't get it off. They go blind.
Yeah, yeah. And Jesse, how are you down under? You need to unmute yourself.
He is unmuted, but I think that something's up with the microphone. We'll give him maybe time to, no, we can't hear it.
One comment I had about the last speaker, which is an absolutely excellent talk, by the way. I really enjoyed it. Kind of anatomical dissection of an event. It'd be hard to beat that one. I just noticed though that in the error plot that there was a deviation to the left as you got below about 30 Ks.
Mm-hmm.
And that's something I've been finding very consistently, that if you do the planetary wind rotation correction, not just the dark flight wind correction, if it's just 100 meters displacement, almost every single time it just goes away completely.
So in this particular case, it was genuinely real. It was measurable, and if you break up the trajectory into multiple pieces, it happened only after fragmentation, and it has been noticed previously. So we looked into this, and the checks also couldn't get a good initial fit. So it was interesting. I believe when we were first comparing the asteroid trajectory produced by the JPL guys and our trajectory, there was an offset because there was a missing camera that didn't see the offset, the deviation to one side. But then when we got the other camera, we realized, oh, there's a break in the deviation. And then we just took the initial part, and then the asteroid trajectory matched really well. So during fragmentation, because it was so violent, there can be an injection on one side. But I think we have to go back because the other session is starting. But look, you had a very short comment. Go ahead.
No, there's just I'm ignorant, and I was wondering about the Coriolis effect, but we don't have to cover that now.
That's all covered.
Okay, yeah. I'm sure.
All right, awesome. Sorry, we gotta go back.
Righto, bye.
Okay, and now we have the contrail hour. So as you may know, in the last couple of years, we decided to enhance the capabilities of the GMN for climate change mitigation, atmospheric observations, and this is all primarily driven initially by Luke, and now we have quite a few other people on board. And the first speaker in the contrail session is going to be Emily Tracy. She is doing a PhD in our group, and she's going to tell us about the background of contrails and contrail observations and what the GMN can do about this important contributor to climate change. So, Emily, go ahead.
Thanks, Dennis.
We see the
Can you see my slides?
Slides, but unfortunately, I don't think we can hear you. Is it just me?
I can hear Emily.
It's all good. It was me. Emily, go ahead.
Okay, good. Okay. So today I'm going to talk to you guys about what contrails are, why we care so much about them, and how the GMN is perfectly positioned to make good contributions to this field. So if you haven't heard the term before, contrails are these line-shaped clouds that form behind planes. So they're composed mostly of ice crystals that form on soot that's emitted in jet engines. They typically form at high altitudes where it's really cold, which is about where planes always fly. So why do we care about contrails? Aviation in general is responsible for about 3 to 4% of all of climate change. If we break that up, we can see that contrails are responsible for about half of all of aviation's climate impacts. The other big contributors are carbon dioxide, nitrogen oxides, and aerosol radiation interactions. So since contrails contribute about half of aviation's total climate impacts, that means that contrails are responsible for about 1 to 2% of all human-induced climate change. This estimate has a really big uncertainty on it, though, which is why continuing to study and better understand contrails is so important. So how do contrails warm the planet? Contrails essentially act as a blanket that traps in the heat emitted by the Earth. So during the day, they both reflect the sun's incoming radiation and trap the outgoing long-wave radiation emitted by the Earth. But at night, since there's no sun present, all they do is trap in that long-wave radiation from the Earth, so the net effect of contrails is warming. Contrails form because the exhaust emitted by aircraft is really, really hot and also contains a lot of water vapor, so it's really, really humid. And when it mixes with the cold ambient air, this causes the water vapor to condense into water droplets on the soot particles that are emitted in the exhaust, and then they quickly freeze into ice crystals, and in the right conditions, they will continue to grow and persist for a long time. So there's a few different types of contrails. The first is short-lived in the picture on the left. So this is when the contrail only forms right behind the plane, but then it dissipates pretty quickly, so you can see that it doesn't last very long. These have negligible climate impacts, so we're not really too concerned about them. In the middle, we can see persistent contrails. So these you may have seen before. They're much wider and can last from 10 minutes up to like 5-6 hours. So these have pretty significant climate impacts. And then on the right, you see contrails cirrus. So these are when the persistent contrails are kind of broken up by usually wind shear, and then they start to look a lot like natural cirrus. So they also have significant climate impacts, but this can be highly uncertain because it's hard to differentiate what was natural cirrus clouds and which were human-caused. So to predict what kind of contrails we're going to see, it's really important for us to know the temperature and the amount of water in the exhaust, and also the ambient temperature and amount of water in the air. So this plot shows temperature on the x-axis and the partial pressure with respect to water vapor on the y-axis, which is essentially a measure of how much water there is. So the exhaust that comes out of the plane, it's really hot and has a lot of water, so it's far in the top right corner of the plot, so like off the plot. And the ambient temperature and pressure are the black dots shown here. So if we have, so the hot exhaust is going to mix with the cold air and follow this straight mixing line here. So if this mixing line crosses the blue water saturation curve, at this point is when the water vapor will condense and form a contrail that we'll see. To determine whether it's going to be a persistent contrail or short-lived, we look at that final pressure and temperature where the black dot is. Since it's outside of the contrail forming zone, or what we call an ice supersaturated region, it's going to be a short-lived contrail. Now, if we look at a different case, this time the mixing line crosses that water saturation curve, so we're going to see a contrail, but the final temperature and pressure is in the contrail forming zone, so we're going to see a persistent contrail. And then in this case, the mixing line does not cross the water saturation curve, so we're not going to see a contrail at all. And it's important to understand how the contrails form and predict that in order to reduce the uncertainty on their climate impacts if we can better model them. And then also if we can predict contrails, there's a potential for us to mitigate them entirely and just reduce aviation's total climate impact. So mitigation is possible because many studies have shown that just a small percentage of flights generate most of the warming from contrails. So it's estimated that about 3% of flights generate 80% of the warming impact, and these are often called big hits. So if we focus our attention to these big hits and just avoid those contrails, then we can mitigate most of contrails' warming impacts. So we just have to adjust the altitude of about 5% of planes by about 1,000 to 2,000 feet around these contrail forming zones, and this will avoid a lot of contrail warming impacts. This is a slight altitude adjustment that's done all the time for turbulence, so it's nothing new to pilots, so it's very feasible, and the average cost of this would be about 1% or lower for each flight. So now that we understand what contrails are and why they're so important, I'm just going to give a brief background on the ways that contrails have been studied so far. So the main way that they've been studied is using satellites. There are two main types of satellites. We have geostationary satellites, which provide frequent but low resolution images. So they can get images every 5 minutes or so, but the resolution is only 2 kilometers. Then we have low Earth orbit satellites, which provide infrequent, so like once or twice a day, but very high resolution images. So the pros of satellites are that we get global coverage, so we can see oceans, we can see the poles and remote areas. But the cons are that we are limited to either geostationary satellites, where we can only see really wide and old contrails, so about 30 minutes old, and we can't see the skinny younger contrails, or we can't observe how they change over time with the low Earth orbit satellites because we only get like 1 or 2 pictures of what the contrails look like per day. Another technique we can use to study contrails are LiDARs. So this is a remote sensing technique where we send a laser into the atmosphere and then we measure the light that's scattered back off of the clouds. So an example of a LiDAR measurement of contrails is shown on the right. The letters A through E are where all the contrails are, and it corresponds to the letters in the satellite view on the left. So LiDARs the pros of LiDARs are that they can measure physical properties of contrails. This is really useful because we can actually see the altitude that they form at, which we can't see when we're just looking at the top-down view from the satellite. They also give a bit of information about the thickness and how they interact with light through something called optical depth. The cons of LiDAR is that it's really difficult to tell what are contrails and what are natural cirrus without using the satellite view along with the LiDAR like it was shown here. Finally, we have ground-based cameras. So there have been lots of studies done in the past with ground-based studies, but usually it's just with one camera in one location, like was done in the study on the left picture and in the right picture. Whereas in the middle, we have a picture of what the contrails look like in a GMN camera. And this is very different from past studies because we have cameras all over the world, so we can get a huge data set in many different locations to look at lots of contrails. So the main pros of ground-based cameras in general are that they have high spatial and temporal resolution. So we can see a lot of detail in the contrails, and we can even see the plane form and the contrail form behind it. So that way we can match the contrails directly to the flight that it was made. And we can even see the really skinny young contrails. Cons of ground-based cameras are that we don't have as much global coverage as with satellites. It's hard to get cameras, of course, over the ocean or in really remote areas. They're biased to young, skinny contrails, and they can sometimes be limited by cloud cover that can block the view. So to summarize the gaps in current contrail research, first is in contrail formation, so it's hard to see the first 20 to 30 minutes of a contrail's life in satellite images, which is what has been used most often to study contrails. And then second, there's not really enough observations of contrails currently to validate models, which leads to really large uncertainties in their climate impacts. And then finally, the large uncertainties also mean that predictions of persistent contrails don't always agree with observations, so we're kind of limited in being able to redirect the altitude of flights right now to mitigate their effects. So how can the GMN help with all of these literature or the gaps in the literature right now? You can see in the picture on the left that we can get really good observations of contrails. And then what we do is shown in the picture on the right, where we have algorithms that automatically detect the contrails, which Liam and Luke are going to discuss in more detail. But a short explanation of what they do is we look at all of the flights near the field of view of the camera. We assume that all of them made a contrail, and then we advect them based on the wind data that we have. So we can see all of the green and the blue lines are where there could be a contrail, and then we see which ones match up with the actual contrails that we observed. So in this case, the blue flight is the only one that made a contrail. And what this does, it'll give us a huge data set of flights and whether or not they made a contrail or didn't make a contrail. And this is really useful because it can be used to provide ground truths to validate contrail models. We can also compare it to satellite detections, so we can kind of quantify how many contrails these satellites are missing, and we can also match it to flights and then track it as it grows and moves across much larger areas in the satellite view. And then finally, we can get some contrail physical properties like the width, the lifetime, the altitude, since we correlate it to flights, and we're even going to get optical depth, and these are really useful to inform contrail models. So here's a video of how our detector and associator works. So you can see that that circled in blue contrail is associated, and all of the green flights do not have a contrail associated with them. So finally, here are some early results that I have comparing our observations to contrail models. So in this plot, every single point is a flight. If it is labeled in dark purple, we saw it form a contrail for greater than 10 minutes. If it's light purple, we saw it form a contrail for less than 10 minutes. And if it's gray, we did not see a contrail form. Now, the location on the plot tells you what the model predicted. So if it's in red, the model did not predict a contrail. In green, we predicted a persistent contrail, and in blue, predicted a short-lived contrail. So ideally, you would see all the dark purple plot points in the top left, the gray points on the right, and the light purple in the bottom left. But you can see that that's not quite what we're seeing, which is really interesting. So this kind of can help us dig into the models to understand exactly where the differences lie and what the models are lacking. And then we can also learn a little bit about the limitations of ground-based observations as well, not being able to necessarily track the contrail's entire lifetime as it advects out of the field of view. So that's all I have. So thank you guys for listening, and let me know if you have any questions.
All right. Thank you, Emily. Questions for Emily? We have a few more minutes. This is something new and strange. I'm sure everyone is just full of questions.
On the slide in view right now, SAC at the bottom stands for what?
So that is something called the Schmidt-Appelman criterion. That is basically how we determine if it is predicted to form a contrail or not form a contrail. So all that plot is showing is like the temperature, how far away it is from being predicted to form a contrail. So if it's too warm, if it's like greater than 0, it's not going to form a contrail. If it's less than this threshold temperature, so it's negative, then we predict it will form a contrail. Does that make sense?
Thank you. I feel better that I didn't know, so thanks.
Yeah, I didn't explain that, so that's fair.
All right, another question for Emily. Go ahead.
May I? Yeah, maybe a silly question. Can this be used, if not already, because maybe I missed something, for cloud detection? And then when you have a meteor detection, it can be somehow combined to avoid clouds, basically. So then it's like an over detection of clouds because it's something moving in front of the camera. Is it something that could be reused in this context?
Are you saying like to use the observations to look at other clouds and stuff?
Yep.
Yeah, for sure. Yeah, it's not something that's being done right now, but for sure a potential. And to be able to compare that to like different models or cloud products would be really useful for the meteorology
Because I would imagine that you will reduce a lot of false detections just because of this smudges of clouds, basically. Okay, great. Thanks.
Yeah, the contrails do look quite different from the natural clouds a lot of times, which is good though.
We have a something in development for cloud detection and observation efficiency that's even more advanced than what we currently use in the GMN. We would just count the number of stars that we see that we're supposed to see, and we take the ratio. And if the ratio is above 50%, we say it's clear, and the other way around. So we have something more advanced in the works where you can essentially, for any given time, you can give a percentage of the cloud cover essentially.
Okay.
It's
great. Thanks.
Great question. All right, thank you. And it's time for our second contrail talk. Liam, please go ahead. And thank you, Emily. All right, we can see the slides and we can hear it. You're good to go.
Great. All right, so I guess first an introduction. I'm Liam. I'm in my 5th year of a computer science and physics undergraduate at Western. And my talk is going to be on the detection and association methods that I developed during a research internship last summer. So the first stage of the entire thing is detections, right? So here in this image, we can see a contrail pretty clearly, and we can see it, but we need an algorithmic way of doing this. So using some human labeled data, we want to make we have made a method that finds this area that I've circled here. Yeah. So the way that we do that, or one of the ways, there are many, uses something called a convolutional neural network. And the first question is, what's a convolution? So that process is taking this 3x3 little grid that you'll see pop up in a second, right here at the -1, 5, -1. And you can slide it across an input image, and it multiplies each pixel in the input by the corresponding number in the kernel, and you add all those together, and you get the output image. So that might seem kind of theoretical. Let's see what it does to the image that I just showed you, this one. If we apply the one that we just saw, we get this, which isn't very different. It's kind of subtle. If you look at the numbers in the bottom left, you can see that they're kind of sharper, and that's what this filter does. But there are some more interesting ones. So this one is called the Sobel filter, and it detects edges, specifically vertical edges. So if we look at the previous image, and then this one, we can see that it's white on the bottom edge of the contrail. And we might wonder, is there some kind of kernel that can give us a contrail? And the answer is it's not that simple. If only. So what we can do is we train a neural network to optimize the weights, these question marks in the kernel. And we don't just use one kernel, we use hundreds or thousands. And this is kind of the structure. It goes up, and as we go down in layers, we kind of capture more abstract information. So you can imagine that the first level detects edges, and then the second one detects corners or longer line segments. And then by the end, we have some notion of what a contrail is. And then what this model does is steps back up until we get an output image that's the same size as our input image. So the model that we use is called UNet, and it's a little bit older. It was discovered around 2015. Was kind of the first paper on it. And on the right here is the result of kind of a more modern approach. YOLO is a fairly state-of-the-art model in computer vision. But we can see it's a lot of metrics here, but the one that is important for the most part is MIOU, or average IOU. So on the left, UNet is a little bit above 80, and on the right, YOLO is pretty much exactly 80. So they're very similar, even though YOLO is kind of a newer, more modern architecture. So we're kind of at this stage looking at a bunch of different architectures and trying to choose which is going to be the best. But yeah, it's a quick overview of the detectors. Now we'll move on to, okay, we have these detections. How do we actually associate them to individual aircrafts, individual flight, or individual aircraft and individual flights? So we start with these advections, where you can see the flights going across the screen, and then the advections move with the wind over time. The next slide. There we go. And we also have our detections, which kind of look something like this. There's these white areas that we've detected as contrails, and they move, and we want to be able to match them up somehow. So if we take all of our detections in kind of an XY being our image coordinates, right, the pixel location of the detection, and we stack them on the z-axis over time, we get something that looks like this. It's called a point cloud. And comparing like individual detected points to individual advected points wouldn't be super useful. We need some kind of model to capture what a contrail is and what like the advection is, and then compare them. So here we're just using a plane to say, hey, this is what a contrail looks like. All these green points are classified as part of one contrail. And the way that we get these planes, because if you just try to fit a plane to the entire data set, you're not going to get something that looks like that. You're going to get something that's kind of slanted in the middle and tries to explain all of the information when it really shouldn't, because there are multiple contrails here. Really, there's this one big contrail and another smaller contrail. So yeah, the way we try to fit planes to these detections is using a method called ransack, which picks a couple points, 3 points randomly, fits a plane to those 3 points, and then sees, okay, how many of the points in the entire data set do these 3 points, does this plane like explain? And what you're optimizing for is a single plane that explains as many points as possible. But there are some pitfalls to that. This is the kind of thing you get when you try to explain just as many as possible with no restrictions. It does something weird. It goes through 3 contrails at once because it's just trying to get as many points as it can. What we can do, though, is we can set some restrictions on this and say that your planes have to be somewhat vertical, right? We can see that these kind of form in curtains. They're never horizontal, and that's because there's a finite speed to how quickly a contrail can move with the wind. And if we set this restriction properly, what we get is nice vertical-looking planes. And this is one contrail, and if we remove all of these points and try to do the same method again, we can get a second contrail. So in this image, we take out all of these green points, and we're left with a couple orange points around. And the second image, these points here, this line, will become green to show that we've found a second contrail here. And then we're left with the problem. We also fit planes to advected points, but it's a little bit simpler because we know which advected points come from one plane. We can just simply, or one aircraft, we can simply fit a plane to all of the points that were advected. But you can see the scale of the problem even then. We have, like 3 different advection paths from airplanes. We have a bunch of different detections, and we have some false detections over here. The way that we match the detections to aircraft is we take the planes that we got from our detections, and we find the angle between each detected plane and all of the advected planes. And we try to find the one where the angle between them is as similar as possible, where they're as parallel as we can get them. And we also look at the distance between the advections and detections. And with those 2 metrics, we can make a score and rank which are the best associations we could make. And the best association we can get out is the one that we list as our final association. And all of that results in videos that look something like this. You can see all of these aircraft flying through, and the colored ones, the purples and pinks, are the associated aircraft. And you can see the list up here as well. But even when we have a contrail, sorry, trying to get to the right part of the video. Yeah, for a second we can see contrails that overlap and that go through each other, and it still detects them and associates them properly, which was very difficult. So that's the end of the presentation, and I'd be happy to take questions. Thank you for your time.
All right, Liam, thank you. It's a very, very technical presentation. Any questions?
What languages are appropriate for programming this?
So the language we used was just Python. Yeah, it works fairly well. You have to do a fair amount of parallel processing to make everything work in a reasonable amount of time. But yeah, just Python.
Yeah. And one thing to note is that the data products that are coming out of this, it's still very in a testing phase. And there's a lot of development and debugging going on. But hopefully we'll be able to roll this out, and once there's more validation and more let's say once the method is published, we'll definitely see more from this. All right, other questions for Liam? All right, well, you're always welcome to write them in the chat. And next up, we have Luke. Luke, go ahead.
All right. So even though this is the contrail hour, I'm going to talk a little bit about the GMN software as well. So since our last conference 12 months ago, these are the metrics. So RMS is a very active project. We have had about 923 commits on the code the last 12 months. So since I've got 20 minutes, I've got time to cover them all. No, I'm kidding. I'm just going to do a very high-level overview. That work was incorporated into the master branch of RMS in basically 2 big batches. There was a June 2025 release and just a release very recently in January, just a few weeks ago. So hopefully, if you didn't notice, it's good news. That means that we did our job right and we didn't break anything. And if you did notice something happened, I'm sorry, and hopefully we fixed it already. So the June 2025 update was mostly about streamlining changes that we had incorporated in late 2024, and also trying to reduce the impact of the Contrail project on the Meteor project. So pretty much the impact of the Contrail project on the Meteor observation is essentially negligible at this point. So I'm not going to read them all, but these are the changes that we wrote in June 2025. And the change that we incorporated just a few weeks ago were mostly about modernizing and future-proofing RMS. Thanks in part with the help of Peter Eschmann, we can say now that RMS supports all major recent distributions, so Trixie, Ubuntu 24. RMS update use modern installation methods. Also, maybe a change that's a little bit more forward-facing that you may have noticed. Every morning, your station runs RMS update, and in the past, you would just reinstall RMS essentially every morning, no matter what. Now RMS update first checks if there's been any changes to the code before even touching anything on your computer. So it saves a little bit on SD card work, and it reduces the chance of things going wrong. Also, Cyton, you may have noticed, I don't know if that means anything to you guys, but you may have noticed Cytons was being rebuilt every morning. That's not happening anymore. It's just only when it changes is it being rebuilt. RMS install has been consolidated so that one script works for every platform. And we're not going to rebuild any more package from source anymore. There's no need for that. So that also greatly simplified the installation of our RMS. We've dropped Python 2 support, which was necessary to be able to move forward. There's been some changes. I think that David is going to present that tomorrow on the FOV sky map that are pretty cool changes. Logging has been a lot of changes in logging the last 6 months or so. One of the main forward-facing changes is that you can now configure the amount of logging that you see in the console. And that's configurable in the config file. You may have noticed that your log file, if you do run a station without rebooting, for example, our station here at Western University, it reboots every 7 days. You may have noticed this new log name scheme where we have a sequence number. So this is the log on for the first day, the second day, and so on and so on. So in case you're wondering what these last 3 digits are, that's what it is. And also we've reduced the noise. There are a lot in the log and in console. Quick public service announcement. Your config file is never touched by the code when we update the code. And so if it's never been updated, it may be running a very old version of the config. There is a utility called migrate config. I don't know if it's hidden. There we go. There's a utility migrate config that you can run on your computer, and it will migrate your config file without affecting your settings to the modern version of the current version of config. If you're wondering if you need to do that, every day in the archive file, you can open up the config audit report, and it will show you whether your config file is roughly up to date with the current template on the repo. There we go. Oops. So this is out of order. Because this is going to be posted on YouTube, and I'm sure people in the audience today are aware, but I just wanted to point out real quick where are the resources for RMS, where do you learn about the new feature? Where do you go when you have a problem? So obviously group.io is the place to go. We also have the GitHub and the wiki, which is being updated right now. So this is mostly for the YouTube audience that may not be aware. So what's next for RMS? What's currently pre-release? We've added a watchdog heartbeat monitor. So occasionally we've discovered that no matter what we do with the code, some packages are slightly unstable and will capture randomly in the middle of the night, and then nothing is happening until you reboot your computer. So we've added a watchdog heartbeat monitor that will monitor capture and revive it, restart it if it dies. We have plans to move the config file out of the RMS directory, which has been a very inconvenient place to keep it. And we're probably gonna follow the multi-cam Linux scheme and save all the custom files into the source stations directory. We have planned for fully autonomous calibration in SkyFit and out of SkyFit, and a new updated SkyFit, which I have a pre-recorded video showing the new feature of SkyFit. So we've got automated calibration. We have a mask making feature inside SkyFit, and we can also display starter. So here it is. I'm going to do a quick demo of the new version of SkyFit that's currently in development.
Hey, Luke, do you mind? We're hearing it through our speakers. Do you mind closing to share and then sharing with your share to sound and then mute yourself?
I have done that, so let me try again.
Okay.
This is share with sound.
Yeah.
I've done that.
Okay.
Let me see. All right. Okay, I'm going to do a quick demo of the new version of SkyFit that's currently in development. I'm going to open a data folder, archive folder from the States. Open, use that config file. It's going to ask me which plate power I want to use, and I'm going to say I don't want to use any plate power just for demonstration. I'm not going to tell it where the camera is pointed at. So it's starting from an uncalibrated state right now. I'm going to hide the menu. First thing first, as you can see in red here, the mask is visible in SkyFit, and you can create one or edit one as you wish. You can add a point. The point snaps to the edge of the frame, which is convenient. The edge on the corners here, so it's very quick. Once you've created one or edited one, you can save the mask to your preferred location. There is a navigation slider here at the bottom, which lets you navigate to an image very quickly. You can very quickly see, okay, where should I, which image should I pick for calibration? Another way to pick a good image for calibration is to use the Find Best Frame button, and then it will pick a frame for you based on the distribution of detected stars. Once you picked a frame to calibrate, you can click Auto Fit, and it will find a solution for you. So first, it goes to astronomy.net, the local packages on your computer. Even though it says .net, it's not going to a server. Unless you are if you're on a Windows machine, then these local packages are not available, and it will go to a server. But here, it's a Linux box. It just used local packages. It found a pointing solution, but it did not solve the lens distortion parameters. So now, using a nearest neighbor-based approach, the algorithm is going to find matching pairs of stars. So it's going to match the green detected stars to the red catalog stars and filter out outliers. And then once it finds good matches, it will perform the fit as usual. And there it goes. It found all these pairs all by itself, so all the blue crosses are matching pairs, and it performed calibration, which is pretty good. 0.2 pixel residual error. 3 new plots at the bottom of this astrometry fit panel. We have the residual error relative to signal to noise, magnitude, or full width half max for the stars. Photometry is same as before. It did filter out outliers, so this is pretty clean. There is a green restore default button, so if you were to choose different settings that are recommended default, it will light up in amber, which is fine, that's your choice, but just making you aware that those are not the recommended default. Fixed vignetting is on by default, and that's on purpose. If you wanted to fit the vignetting, I invite you to read the information panel, the information buttons here. They contain information about what to watch for if you want to perform the vignetting calibration. There is a new feature where you can display star names, spectral type, and constellation, as well as planets. So you can see that Jupiter is here. You can click on the name of stars and it will open a browser window with information on the stars. Okay, remove those to declutter. There's a new star detection panel. So in the past, the green detection, did I hide them? Yeah. The green detection circles, the parameters for detecting the stars are set in the config file, and you could not change that in SkyFit. So now you can change these settings to redetect the star if you wanted to. So I could choose a different intensity threshold, redetect on the current image or on all the image in the data folder. There's also a feature where you can auto-tune intensity threshold and segment maximum by clicking here. And what it does is that it's sort of sweeping all these settings to find a good balance between maximizing true positive and minimizing false positive. Okay, so it's sweeping through all these intensity threshold until it finds the elbow at which we're starting to pick up too much noise. So when we pick up noise, this will appear as an increased number of false positive. So we can see here that at threshold 7, we're starting to really pick up a lot of noise. All right, so it picked up 9. And there we go, intensity threshold 9, segment radius 5, and a matching catalog limiting magnitude of 7.3, which covers all these very faint stars. I think that's about it for what's ahead in SkyFit 2. Thank you. Okay, hopefully I'm back and you can hear me. And how am I doing on time? Okay. All right, so back to the GMN contrail pipeline. So as Emily has already mentioned, the field, the stakeholders in aviation are really needing those models to be validated correctly, and we are starving for that ground truth data that GMN can provide. So it's literally from your camera to the real world policymaker's desk, there is a almost straight line, and it's going to be very impactful. So all these stakeholders are breathing down our neck right now to see how quickly we can provide these ground truth data so that we can finally validate these models. all the stakeholders are aware that an event like the one in the picture, where we form contrails just before sunset in clear sky, is a very warming event, and then it seems like we should be able to do something about it. So you can help. So I'm going to talk a little bit about how technically the GMN pipeline works for contrails. So your camera is currently, unless you've went out of your way and disabled it, but normally it takes saves a JPEG every 5 seconds, and it's simultaneous across all our cameras. So see, right now they're all taking a picture if they're recording at night or the day. And then every morning after the RMS software process the meteor data, it would then generate 2 time-lapse based on those JPEGs saved every 5 seconds. So there will be a day time-lapse and a night time-lapse, and those are uploaded to the server. The impact on your computer, the storage impact is very small, and there's no loss of data for the meteor pipeline. Once it's uploaded to the GMN server, we then analyze it. Currently, this is done in batch. The plan is that it's going to be done as the data arrives, but we're still developing those tools. And so this is our batch processor on the server here. This was on, you know what, it's a video, so I'm gonna be quiet and let it go. Okay, once the videos, the time-lapse are uploaded to the GMN server, we can process that data. Here's our dashboard for our batch processor. For example, here we did a run on the first week of October 2025 over Europe. And you can see that for each day it's separated into a day time-lapse and a night time-lapse. And so we've run our detection and association algorithm on all these videos from all these stations. As you can see, unfortunately, very few stations in Europe are running continuous capture mode. They are mostly only running standard mode in safe frames. So what we would really like to see is more stations turning on continuous capture safe frames. So we've got, for example, this station in Hungary, or this station in these stations in the Netherlands, running day and night. So we can click on any of these and see what we have detected. So I can open a video, for example, here, and okay, I'm gonna pause to talk about what we're seeing here. So these lines are the flight track advected with the wind. So we know the flight data from something called ADSB, and then we get the weather data from it's called ERA5 weather data, and then we can advect those traces with the wind. So essentially it's as if every flight produced a contrail. Where should we find, where should we be looking for it? And so in green are flights that we did not detect a contrail, and colored flights are flights that we do detect and associate a contrail. So for example, this flight at 36,500 feet, Boeing 787-900, I'm going backward now. This was already explained by Liam. Our machine learning algorithm detected the contrail. So I'm going to skip. All right. So how can you help? By default, continuous capture, which means recording during the day, is turned off. So we've chosen not to impose that on anyone. We are asking if you could please consider turning on your camera during the day. And the way you do that is by turning on continuous capture in your config file, continuous capture to true, and switch camera mode to true as well. So this will switch your camera between color mode during the day and black and white mode, grayscale mode during the night. And as I mentioned earlier, no adverse impact on the meteor observation, and minimal storage impact on your storage device. So it peaks at about 2 gigabytes, and then as soon as the time lapse are generated, it deletes all these JPEGs to save space. So it essentially a very small impact. In partnership with our friend Peyton Oaks Bryden, we've developed an all-sky camera system, which is optimized for both meteor observation and contrary observation. It's a six camera system, all-sky coverage down to whatever obstacles you have around you. So this is, for example, the coverage of this camera over my house. And it's available. I mean, I hate to do some product placement, but it's available for sale, for purchase, and that's what it looks like. One thing to note, it's got a very large hard drive, which allows for that raw video recording. And as Denis can probably explain better than me, this is really great for fireball recording. And this concludes my presentation.
All right. Thank you, Luke. That was very comprehensive. And I'm sure there's a lot of interest in the automated calibration part. And I'm tempted, just so everyone can see how quickly one can do a calibration now. So I'm going to recreate it. I have something prepared here, if you don't mind.
Sure.
Just so everyone can see how brilliant and quick this is. Can you see my screen with the schedule and the RMS terminal?
I must you.
Yes.
All right.
Yes.
All right. So I'm just going to run SkyFit on some data that I have from Spain. I'm going to open it. I'm going to say, I don't have a plate bar. I don't have a calibration. Where's the pointing? I have no clue. I'm going to say cancel. And it's just pointing wherever. And then I'm going to do auto level so I can see stars better. And the cool feature that I don't think Luke talked about is that you can actually find the best frame for fitting. It's going to look at the number of stars, the distribution of stars, so you don't have to choose it yourself. Hit find best frame. And here's something really cool. It can find the best frame from the cal stars. You don't even have to have the VFF file. It just goes through the cal stars file with extracted star positions, and you can use that to do the fit. So it creates a fake image using that data. I'm not going to do that now. I'm going to say just go to the best image that we have right now. And now let's do the auto fit. And the button is right here. I'm going to hit auto fit. You can see in the background, magic is happening. It says the astronomer found a solution. So you can see the stars. The pointing is close. Do you want to continue with refinement, which means we're just going to go and pair the stars and do a complete auto fit? I'm going to say yes. And now it's doing things in the background. It's making the fit. And you can see the fit residuals, like, 1 arc minute, 0.8 arc minutes. And we're done. And now if we look at the astrometry residuals, you can see that the fit is really, really good. Maybe there's some outliers for sure that you can get rid of if you want to, but the current outlier rejection mechanism does a pretty good job. If we look at the photometry, it's a really solid fit. And from that point on, you just hit save and your plate bar is done. And yeah, as for the mask, as Luke said, you switch to the mask tab. Mask is already here, it's created. Let's pretend that we don't have a mask. I'm going to hit clear all. It's going to delete all the polygons. And then I'm going to make a new mask. I'm going to say draw polygon. And I'm going to go from this corner, this corner, this corner, this corner. And I'm just going to put it here. And I'm done. Let's do another one. Here, here, corner, done. Save mask. That's it. Station's calibrated. So FYI, it's that fast. All right. Any questions for Luke before we move on?
You're showing SkyFit improvements. You're talking about the future. When is it available? What, any guess?
We've been working on that a month and a half, and I think most of the bugs are out. I don't know, Dennis, what do you think? Couple weeks?
Yeah, I mean, I kind of hoped it would be done by the meeting, but there are always improvements and things that we're finding. We will let you know, but it's very near to being done. Very, very near.
I'm rebuilding the catalog again, right as we speak. It turns out that the 6 bright star were missing.
Yeah, so Luke has done many more things than just SkyFit. He fixed the catalog and all sorts of things. So yeah, it's going to be a comprehensive update for sure. All right. Okay, well, thank you, Luke. And now we have to move on to Tristan. So Tristan is an actual contrail expert who is going to tell us how our contrail findings are going to be used by the community, by the regulators, and how they're going to help us fix climate change. So, all right, Tristan, go ahead.
Great. Thanks, Dennis. Let's make sure I can share my screen.
All right, we see your screen.
Great. Do you see the slides now?
Yes, we do, and you're good to go. Thank you, Tristan.
Awesome. Great. Yeah, so I'm Tristan Abbott. I'm a research scientist at contrails.org. We're a nonprofit with a team that's split pretty evenly between the United States and the United Kingdom that works basically on developing tools for reducing the climate impact that contrails have. So I'll talk about one part of that effort today, which is work we're doing now to build a framework for benchmarking the forecasts that we hope eventually will be used for contrail avoidance, with the goal eventually of getting to the point where I can talk about how GMN cameras will help with that effort. Emily did a great job in the first talk of this session, sort of explaining why contrails affect climate. I won't rehash that. I'll just say something quickly about sort of the scale of the climate benefit that you would get from eliminating long-lived contrails. So long-lived contrails are in the atmosphere now. They produce some warming. If we were able to figure out a way of getting rid of all of them, the benefit you would get from that is a benefit that's comparable to the one you would get from a one-time removal of about 35 gigatons of carbon dioxide from the atmosphere. So that number is about the same as a year of global carbon dioxide emissions. So it's like winding back historical emissions by a year. It's also about 25% of the remaining carbon budget we have to stay below the 1.5 degrees Celsius temperature target that the Paris Agreement set. So it's, something like 1 to 2% of warming today, but has the potential to make a pretty significant impact when we think about things we can do to mitigate climate change in the near future. And what our group at least views as the most promising approach to contrail mitigation is one that's based on adjusting flight trajectories at the flight planning stage. So the idea here is that right now, flight trajectories are planned by dispatchers that work for airlines. They run a proposed flight, so an origin-destination pair, through a trajectory optimizer that tries to find, typically the route that will be least costly to the airline. The hope is that with the addition of a forecast of regions where contrails are likely to form, and some way of representing, or I guess adding a cost associated with contrail formation to the cost functions that trajectory optimizers use, there might be a relatively low overhead way of having planes follow trajectories that avoid most warming contrails without adding a large additional cost to the airline or burning too much additional fuel. So this figure is meant to illustrate what that might look like. This is showing a pair of altitude profiles for, I think this was a flight from New York to Cairo in January 2019. The red area, this red blob, is output from a forecast that our group generates showing where the forecast thinks warming contrails are likely to form. The black profile is the optimized altitude profile that this is a relatively simple trajectory optimizer that our group built. The optimal altitude profile for the flight, not making any attempt to avoid contrails. It goes right through the middle of a contrail forming region. So if it were to follow this trajectory, would produce a lot of contrails. The green trajectory is an optimized trajectory that's contrail aware and tries to balance avoiding warming contrails with not burning too much additional fuel. So in this case, the optimal trajectory, given the cost we've assigned to contrails, is one that avoids contrail forming regions altogether. So there are obviously two critical questions associated with this approach. One is how accurately pilots are able to follow contrail optimized flight plans. So in this example, if the flight ended up flying this section of the flight at 30,000 feet, that would be great. It would avoid making contrails. If for whatever reason it happened to fly that section 2,000 feet higher, it wouldn't avoid the contrail forming region. So some part of the work that our group does is working with airlines and ANSPs, and organizations that run air traffic control networks, to make sure that the contrail optimal flight plans that we generate are ones that are actually usable by airlines. But the other one, the one that I'll mostly talk about now, is whether the forecasts that optimized flight plans are based on are accurate enough. So again, in this example, if this flight flew this segment at 30,000 feet and the forecast of the location of the contrail forming region were accurate, it's great. If the forecast were wrong and placed the contrail forming region a little bit higher, so if it were down here in reality, again, you haven't accomplished what you wanted to, because though you avoided forecasted contrail forming regions, you didn't avoid the actual contrail forming regions. So the work I'm going to highlight in this talk is some in-progress work trying to provide information, largely aimed at airlines and regulators, since it's the sort of comparison that academic researchers can do on their own already about the accuracy of forecasts for contrail formation. The approach we're taking is assessing forecasts across two different dimensions. So one that tells you something about the effectiveness of contrail avoidance using that forecast, basically whether or not you avoid real contrails when you try to avoid forecasted contrails, and the other is the cost of contrail avoidance. So whether or not avoiding contrails based on a given forecast would end up being overly expensive to airlines. It's sort of obviously important, I think, that you need both dimensions in this evaluation, right? So avoidance needs to be effective without being too expensive. We, in some sense, already know how to produce very effective contrail forecasts. You could just say that contrails could form anywhere above about 27,000 feet. avoidance based on that sort of forecast would be very effective in the sense that if any, if planes never flew above 27,000 feet, you'd probably see very few contrails. But obviously that would be, at minimum exorbitantly expensive to airlines and probably in practice just infeasible because planes are not very efficient when they fly at relatively low altitudes. So forecasts evaluated this would give you a pretty straightforward way of making at least relative comparisons between pairs of forecasts. Better forecasts will sit up here, worse forecasts will sit down here. The initial prototype that we're developing is using the flight distance inside forecast contrail forming regions as a metric for cost. So the idea being that it's more costly if the contrail forecast requires you to reroute a larger cumulative flight distance. This is a property just of the forecast alone, so you don't actually need observations to evaluate it. And we're using a forecast hit rate, so this is the fraction of observed contrail forming regions that the forecast predicts as contrail forming regions as a metric for effectiveness. For this, you do need observations, obviously, and this is where we hope GMN will help. So this builds on a lot of work that's been published in scientific journals already. Our hope is that the thing that we can provide is some sort of ongoing assessment framework that integrates new data sets as they become available and refines the metrics used to evaluate forecasts with an eye towards especially making the results easy to communicate to somewhat less technical audiences. So, this is possible already. I probably, for the sake of time, won't dwell on this result, but we have some preliminary results already based on comparisons with in situ measurements, so measurements of temperature and humidity from aircraft sensors. And the two types of observations that will likely be included in the first version of this report, so we're calling it contrail bench, are in situ measurements and geostationary satellite imagery. These both provide some information about where contrails form in reality, but they both have limits that Emily largely touched on already. So in situ measurements are limited by sparsity, which means that the hit rate calculation in the evaluation ends up being based on quite a small and potentially geographically biased sample. And geostationary satellite observations, although the observation volume is a much larger, are limited by data quality. And so in particular, the fact that you need to match detected contrails to flights to get information about their altitude means that it's relatively easy for the hit rate calculation to get contaminated by false positive observations produced by matching a real contrail to the wrong source flight. GMN, again, this is a point that Emily has already made, does a lot to address both of these limitations. So one of our major goals for this year as we work on developing contrail bench is to work on integrating GMN contrail detections. So this provides lots of observations. It's way more than you get from any in situ measurements that you can use to generate a data set of observed contrail forming regions with very few false positives. So what I mean by that is basically, and I'll play this video forward until I get to a good example, it's pretty easy to find flights captured by GMN cameras that you can say with very high confidence did produce a persistent contrail. So like this one, this is a Southwest Airlines flight at 37,000 feet. It's very clear from this video that this flight is producing a persistent contrail, so you can say with very high confidence, yes, good contrail forecasts should predict that at this location, time, and altitude, flights can produce persistent contrails. So I'll finish by saying a few words just about plans for the future. We're planning an initial release of the first version of Contrail Bench. So this will mean a report plus codes plus some open data sets that people can use for whatever they want to do. This spring, this will be focused mostly on forecasts of contrail formation plus persistence. We're planning to include 2 forecasts, so one that our group produces and one that a research group at Google produces, and 3 sources of observation, so in situ measurements from IAGO's aircraft measurements, from radiosondes, that's GRON, and from a geostationary data set that, again, the Google Research Group has released recently. Future versions of Contrail Bench, we're hoping to aim for roughly quarterly releases. The near-term update that I'm most excited about is the addition, hopefully, of persistence and formation observations from GMN. But we're also likely to make improvements to methods, so try to get closer to making direct estimates of avoidance cost and effectiveness rather than just using proxy metrics. And we'll integrate additional forecasts if we get interest from other groups that want to produce forecasts that airlines can use for contrail avoidance. The final thing I want to emphasize is just that the structure of Contrail Bench is meant to, especially initially, be very flexible and responsive to feedback. So if you have data, whether that's from GMN or somewhere else, that you think would be useful, please reach out. I mean, we learned about GMN because Luke reached out to us a couple of years ago, and we're extraordinarily grateful that he did. There might be other data sets sitting around out in the world that we just haven't heard about yet, but that provide useful information about where contrails were formed. So if you're, are interested in the forecasting part, have some data that you think would be useful, or just curious about how imagery from your cameras might end up getting used in Contrail Bench, feel free to reach out anytime in the future.
All right, thank you, Tristan. Any questions for Tristan? Yeah, I just want to say that after our methodology matures and we can produce contrail observations that are connected to aircraft with a high level of confidence, we would be providing essentially metadata on contrail observations. So we're still dedicated to preserving our operators' privacy. And the good thing about these observations is that you don't really need to know the camera's location at all. So what we'll be providing is just simply, height, latitude, longitude, masks of the contrail and essentially the coverage at different altitudes, and then that can just go into algorithms for constraining contrail prediction models or weather models, et cetera, et cetera. Kevin has a question. Kevin, go ahead.
Thank you, Tristan. That was super interesting. I wanted to ask how receptive commercial airlines are to changing their flights like this.
Yeah, I think so. Right now, the contrail avoidance community, we're sort of in a strange position. There's actually more interest than we can support on our own from airlines in doing contrail avoidance trials. Airlines are very interested in figuring out what doing contrail avoidance in practice is like, at least as part of a small scale exercise. There will be, I think, essentially no interest from airlines in doing contrail avoidance at scale without some incentive to do it. Right now, it's not really clear exactly what that incentive will be, and there will probably be some number of airlines that decide they want to do it without one. I mean, global adoption, I think, is probably unlikely without regulation. So one of the things that we hope Contrail Bench will accomplish is providing a conduit from organizations like GMN, who generate data that can be used for figuring out whether or not forecasts are good enough to do contrail avoidance, to regulators that need to make decisions about whether or not the scientific state of the art is good enough to incentivize contrail avoidance by airlines.
Thank you.
The important thing to say is, as we mentioned, regulations, that the EU is already moving in that direction. and regulations are being drafted, then essentially the EU told airlines, you got to do something about contrails. You have a few years. That's the summary of it. So regulations are being drafted, and if they have to adopt to, let's say, European standards, all flights in and out of Europe will essentially have to follow these regulations. So at least one part of the world is doing something about it.
I have a question, if I could. What can they put a camera on an airplane wing looking back and see the contrail?
They can, yes. And I mean, so I'm not aware of any commercial aircraft that have backward-looking cameras mounted. There are some wide-body Airbuses have forward-looking tail-mounted cameras, and even those cameras, you can tell whether or not the flight is producing at least a short-lived contrail. You can see the contrail forming as exhaust leaves the engine, before the tail-mounted camera passes the exhaust. I mean, the challenge both with the forward-looking tail-mounted camera and a backward-looking one is that you just can't see that much of the contrail. So I suspect even with a tail-mounted camera, it would be hard to tell whether or not the contrail is, lasting for a minute and then dissipating or persisting long enough to have a climate impact. Luke, does that sound right to you?
Yeah, you probably wouldn't be able to see far enough to have any useful information. What would be super useful to install on airplane, and there are plans to do that. I mean, I don't know how advanced these plans are, but it would be to install a humidity sensor. So planes currently can measure wind, they can measure temperature, unless you are a spy plane in the 60s, which had humidity sensors for that purpose. Yeah, modern jetliners don't have a humidity sensor, except a small fleet of Argos airplanes, which do have a humidity sensor. This would be the most useful feature.
Essentially, if commercial aircraft had humidity sensors, we would not be doing this.
Correct.
That would be the way to do it. Right?
Yeah.
It's just upgrades are extremely costly and would take many years.
The first contrail ever observed was actually observed from an airplane by the pilot, but it was in 1919, and it was an open cockpit, and the pilot could just look back and in a turn notice that he was laying a white trail, didn't know what it was. Can't do that today. What pilots can see sometimes is the shadow of the contrail in a cloud or on the ground. So if the sun angle is just right during the day, yeah, you can actually see if you make a long contrail just by looking at your shadow.
Luke is speaking from experience. Damir has a question. Go ahead.
Yeah, this looks very, 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 very promising. And what I'm wondering is, suppose everything goes fine, aircraft industry and everything gets aware, and we have the data. For how long should we wait until some positive effects of avoiding creation of contrails would be seen?
Yeah,
I mean,
so
global warming is not from yesterday. Hopefully, such effects should be seen in near future. Otherwise, somebody will say, "Wow, this is not working."
Yeah, so the contrails compared to most warming agents have very, very short lifetimes. I mean, you form a contrail, and even a very long-lived contrail is gone within a day. So you get the warming that contrails are causing in the sense of the way that they're changing Earth's top of atmosphere energy balance. That responds essentially immediately, like within days, to changes in contrail formation rates. Starting it takes Earth's surface temperature, which is, that's the thing that matters for life at Earth's surface a little bit longer than that to respond, but not actually all that long. The lag between changes to top of atmosphere radiative balance and changes in Earth's surface temperature is, like years to decades, not centuries. There is a very, very long time scale that involves the equilibration of the deep ocean, but you'd see a benefit very quickly.
Yeah, that was my question. So benefits should be seen in a real near future, and so proof of concept would be there, and everybody will see the benefit.
Yeah, well, so I mean, I guess the thing that's challenging is that even anthropogenic climate change as a whole, that signal, in top of atmosphere energy balance and surface temperatures has only relatively recently been or become large enough to be kind of unambiguously detectable above noise. The cooling that you would get from eliminating contrails is, small relative to all of the warming that humans have caused. It's like Emily said, sort of a percent. So we certainly would like to be able to measure that effect observationally. That would be sort of the gold standard proof that contrail avoidance is having the effect that we want it to have. That in practice might be very hard. There are proxies that are more realistic to try to measure, though, if a little bit more esoteric, like trying to say something about changes in total cirrus coverage before and after large-scale adoption.
An important thing to say is that it is a bit of a chicken and an egg problem. So imagine we start observing contrails. We feed that data into weather models. The weather models perform perfectly. All of the airlines adopt contrail avoidance techniques. No contrails are being generated anymore. Where's our data? Right? So there's always a problem of using contrails to detect humidity as kind of a secondary product. So this is only a short-term solution. It's a short-term solution to understand the science. So what Emily has shown is, hey, the atmospheric models are saying contrail should be generated here. The SAC criterion is saying there should be a contrail here. And yet we're seeing clearly no contrails where there should definitely be contrails, and the other way around. So it's also a physics problem. It's also a science problem, understanding what's going on a small level. It's a data problem. It's very complex. So we should not see it as only as kind of an operational thing where, okay, we're going to feed the data in and they're going to do whatever. It is solving actual scientific questions. There's also more dependence on aircraft type, on fuel type, on thrust, on efficiency, many parameters that need to be found, that need to be optimized before any of, I would say, operational goals can be achieved. Now, if we find, let's say, an approximation purely empirically through observations, we have, let's say, thousands and thousands of contrails, and we find that we fit in a machine learning algorithm. The machine learning algorithm says, yeah, the SAC, that's your theory, that's your physics. But I found a way, if you combine things in the right way, don't ask me how, and we're getting 100% accuracy. That is also another way to solve the operational side of things versus the scientific side of things. So the problem is multifaceted. But yes, removal of contrails, the effect would be immediate. Hopefully we won't be doing this for too long. Maybe in a decade or so, if not sooner, aircraft will be upgraded to include humidity sensors. And then, let's say, our participation goes away, but then the scientific question still remains because we measure essentially the humidity content at those altitudes. And if aircraft also measure the humidity content, but the models still don't work and the physics still doesn't work, the problem remains, right? So we're working on many aspects. All right. Any other questions or comments? Excellent. Well, it's great to see this engagement. And please, if you have any other questions, write them in the chat. Bob, you had a question.
I just wanted to talk to Luke. Maybe I think you're about to have a break, right?
Yes, we're a bit late, but let's have a 10-minute break so we can chat and rest of it. All right, so let's see everyone 5 minutes after the hour.
Luke, I wanted to ask if I could. You were talking about the change, and you showed the option to change the config file, the Python code to do that. And I look on my system, and I don't have that ability. I type that line in. Am I just running older software, and I'm not updated enough to have that utility? And I looked in utilities, and I don't see that.
So what is probably happening is that as an early GMN adopter, you've had your config file for a long time, and
right.
config file has evolved, and so those new options are not in your config file. Although you're running the software, you're participating right now, your camera is grabbing a frame every 5 seconds at night. The option to turn it on during the day is probably not in your config file right now, and that's why there is that migrate config utility. And if you do run that on your system, it will keep all your current settings and expose the new config settings in your config file. So it will bring up your config file to the current standard. That utility also backs up your current config file, so you're not going to lose anything. If you don't like it, you can just revert back.
Let me add one more complication here. I have 4 cameras, and so I have stations with config files and all that in each camera. So I'm thinking I was thinking I was going to get with Peter or hear him talk today or later about just upgrade my whole system and scrap everything, and that way I'm up to date.
You could. You don't have.
I will talk about
Pete.
that when I do my presentation. I'll suggest upgrading. So yeah, but I think for the time being, you could migrate the existing configs. It's relatively fast. You just have to get on each of the machines and run the migrate utility, and boom, all those parameters will be there. My experience is it doesn't wreck anything. You can run it in test mode first, if you want to look for yourself.
But I'm not seeing the migrate utility. That's the underlying thing here. I'm thinking I'm not the only one that's in this mode too. I don't know.
Then I would guess that your RMS update is not working correctly.
Okay.
You don't have migrate utility in utils?
No, I don't. If I look in the utils folder under RMS, I don't see migrate.
Oh. And if you do run RMS update, does it complete successfully?
I don't know. I think it does, but I haven't looked for a log or something to see that it's updating okay. So
I suspect that maybe these are Raspberry Pi.
It's a Linux i5 system running for all four cameras on one computer.
Okay, so it's highly probable you need to run that manually, and it'll give you a sudo prompt that you'll have to provide the password. Because ordinarily, if it's run automated, it'll time out waiting for you to supply the root password and just go on without updating key pieces.
Oh, okay. All right.
Are you logged in right now? Are you in front
Yes.
of it? Try RMS update, see what it does.
You just run it manually, scripts RMS update.
All lowercase?
No, RMS.
Uppercase.
I'll put it in
uppercase, and then capital U.
It says RMS update not found. RMS, capital RMS underscore capital U.
I put it in
update.
chat.
Yeah.
Do you see the chat?
Yes. Look at it. Actually, I don't see you in chat there.
Oh,
I just saw it pop up.
That's because I answered P directly. Or
Oh, okay. That's why I saw it. And Luke, I will be talking about the migration to the new data structure and the hierarchical config at the end of my presentation later.
Good.
Or I will try to talk about it. Let's put it that way.
Perhaps a quick question. We have so many fun things in utils and perhaps in scripts. How do I know what they do? Is there an overall list someplace?
Well, in some cases, you can carefully look at those Python
Right, and look in the source. Okay.
Yeah, without saving,
Yeah.
That's one way. Yeah. I'm not sure that they're that well documented, though.
Is it in the wiki?
No,
well,
not
that's
really.
probably.
So one thing,
add it.
yeah, you can run a command with -- help, and that generally describes what it does.
That's helpful. Thank you.
Yeah. Works like any command in Linux where you're just right -- help, and it has a list of inputs, outputs, and a general description of what it does. Yeah. All right. I'm going to give everyone a few more minutes, but I don't want to stop the discussion. So.
Well, I found the migrate config to be extremely useful to bring in a bunch of new parameters.
Yeah, I've just looked at my report, so yeah, I need some updating. So this will be helpful. So I have 4 cameras. Is it appropriate to replace it with some Linux laptop?
Probably. One advantage is you go to one place, you do one login, and then you can access the data's stored in subdirectories.
I'm thinking I get away from SD cards too.
Yeah.
Some trouble there.
Absolutely.
That's the main thing.
There was some article about it, I think, in the wiki, how to do the Linux side, the Linux method.
Yes,
instead of Raspberry Pi.
Yeah, there's the multicam Linux is the document. It's referenced in the advanced install section. It's in need of additional revisions and updates, and we are going to try to migrate it from the current PDF file representation into wiki content so that others can help maintain it. But I did try to revise it recently. We now recommend starting with Ubuntu 24.
Good. Okay, so it's up to that. Great.
Right. The old document was stuck on Ubuntu 20, but we now know everything works under 24. I heard one person say they're running under 22, which surprised me because I had some issues with 22.
Well, I'll just start at 24. But I appreciate what you folks are doing. I put out some radio astronomy code, and yeah, documentation's the boring stuff. I never get to that either. So thank you very much.
Yeah, it's.
I understand the problem.
It's not fun, but it has to get done. And I have a huge backlog of documentation that needs work. In fact, in my talk later, I'm going to suggest that we form a working group to try to work on updating the wiki and documentation. So some of you might be thinking about that in advance.
Very good. Appreciate all you're doing, folks.
All right. Awesome. So let's kick it off again. And I'm going to have a couple of talks that I put together very, very recently. The one you're going to see now is literally an hour before the meeting this morning. And it's to talk about all the things that could be better, all the things that the GMN is lacking, all the potential problems, software, organization, methods, signs that we can do better, or science that we can't do right now because of some technical limitations, et cetera, et cetera. Let me just quickly share my screen here. All right, can you see my slides here?
Yes.
All right.
Yep.
Yes.
I'm trying to make this full screen. All right, I call this talk the GMN, the imperfect behemoth. All right, so where does the GMN fall short? And there are particular areas that I identified as lacking. The first one is the processing pipeline. So last Geminids, the weblog was late for a couple of days. The orbits were late over a week or so. And then flux estimation. So when meteor showers are happening, you want to know what the activity is now. Right now, they are late by maybe, let's say, 6 to 12 hours, depending on the reporting, because the reporting happens at the end of the night. That goes in the pipeline, and then the flux gets computed. And then fireballs. The GMN hasn't initially been designed to observe fireballs. It's been designed to observe faint meteors. So we're going to talk about the software improvements, hardware improvements. They can improve our fireball observations, and finally, organization. It's a ginormous organization that's spread across the world, and I don't even know how it's organized as well as it is. It's one of the important items that keeps the whole project possible. All right, so the processing pipeline. Usually, every day, a camera uploads on the order of 100 megabytes. Something like that, depending on the day, depending on the camera. However, during major showers, that can be well over a gigabyte. And because we have well over 1,000 cameras, the server gets hit by over a terabyte of data within 24 hours and sometimes even a couple of days. So it accumulates many terabytes of data within a span of days. So what it has to do is unpack this ginormous archive, and most of the files are images. And we had this delay during the last Geminids, and this is exactly what the problem was. So it was just taking forever to upload this, to unpack this whole archive, and then only extract a few little files it needs for orbit computation and the weblog. And we also have issues with duplicate orbits in the pipeline, which comes out of some assumptions in the trajectory solver. And there's also a question of the general validation of the orbit pipeline. So if observations go in, how do we know that it's actually doing a good job? It's getting all the meteors, that all the numbers are correct, et cetera, et cetera. All right, so the weblog delays, as I said before, during the major shower peaks, huge archives get uploaded, and we found a solution. And the solution is to just divide the archives into two. Into a metadata archive that has the measurements, the calibration, the status plots, which is usually on the order of 20 megabytes, and an archive that contains raw images. The FF files, the FR files, they can be hundreds to gigabytes in size. And the idea is that when that gets uploaded, the server only extracts the metadata, which is super fast, and then takes the raw images and then just transfer it to the archive server without even looking at it. And that is going to solve all of the weblog delays. The solution is in testing. The server-side script has been updated, and it is really just a matter of time until I merge this into production. And here's Dave Rollinson from Australia, who actually implemented this feature. Hey, Dave. Good morning.
Good morning. That was spectacular timing. That's
right on time.
I thought I recognized that piece of work. Anyway, do carry on. I'm only in to just check the audio and everything works. Thank you.
Yeah, awesome. Thanks for joining, Dave. All right. So second is orbit computation delays. So the way the orbit pipeline works is first it needs to pair meteors, pair individual observations. So your camera sees a meteor, another camera sees a meteor. How do we pair it up in a computer trajectory so it can make a full orbit? So first, We look at all observations from stations which are within about 500 kilometers and in each other's field of view, so they have some overlap. And we look at their detections that are within 10 seconds, and then we just try to make a very, very quick, very, very rough trajectory that needs to be valid. So it has to have the right speed of a meteor, and it has needs to have the rough height, correct height of a meteor. You know, if it's like the solution comes up saying it's at 10 kilometers, okay, that's obviously not right. It has to be usually between like 50 and 130, 140 kilometers. The filters are pretty wide open. This pairing stage is usually very fast. But then the second stage is it feeds those observations into the proper trajectory solver where it solves for the full orbit, for the full speed, and that takes a bit longer. And then the final stage is once a stable solution is found, and a stable solution essentially means it rejects observations which don't fit within the trajectory or which are off due to various reasons, calibration, et cetera, et cetera. It computes the uncertainties. So it reruns the second step dozens of times to compute the uncertainty in the orbital elements, and the radiant, and the speed, et cetera, et cetera. So all these things are just ranked by how much compute they require. And as you might remember, a few years ago, we had severe issues at all. In every major meteor shower, we would experience major delays. So what Mark McIntyre did, he separated the uncertainty estimation part from the candidate trajectory part, and that seemed to improve things tremendously because we can immediately report the candidate trajectories. They show up on the website, and then if it takes a bit longer to compute the uncertainties, well, that's perfectly fine. And this worked great until the Geminis this year, where there were so many meteors that things again ground to a halt. So the new solution, which is work in progress, is that we're going to break up all these steps. So candidate pairing, first trajectory estimation, and then uncertainty estimation into completely separate steps. So the idea is that the GMN server is the central place where all the data comes. It does the trajectory pairing, and then it distributes observations to remote nodes, or these can just be different processes running on the server itself. It can be my office computer if someone wants to donate their CPU time. They can install WMPL. We're going to create a special account and essentially distribute the observations there to compute the first trajectories. And then there's going to be a second process, which is going to compute the uncertainties. And this way, we can scale the network almost indefinitely. We'll just keep adding more remote processing nodes, and that should hopefully solve the problem. All right. So duplicate orbits. So that's something that I've known about this problem for a while. Didn't have much time to look into this, and it really came to the fore when people started looking into some of our data products. And there are about 2 to 5% of duplicate orbits in the orbit data set. And this really comes from a fundamental question: is like, how do you properly pair observations from many cameras? If you have 2 cameras, it's fairly easy. But what if you have 10 or more? Which ones do you take? Which ones do you reject? If you take all of them, let's say 30 plus, the trajectory solution is going to be extremely slow. And at one point, you start seeing diminishing returns. After maybe 5 or 6 stations, any other observation you add is not really going to improve the trajectory solution that much. And what we find is that the trajectory solver had issues with meteors that had a gap in them, or they were split in half by the kind of the FF file cadence, 256 frames and then 256 frames, and then the meteors in between. It would pair them up as different meteors and it wouldn't merge them properly together. And another problem was when you had very long meteors lasting tens of seconds, it would break them up into individual segments instead of understanding, well, it's the same meteor. So we have a solution in progress here. We have optimized pairing filters, and we're still working on validating this new approach. All right. So meteor flux estimation, when you want to see how, when you want to, you want, let's say, casual observers, but also, space safety experts. They want to know what the meteor rates are now, at this moment. And right now, the GMN, the way it's been designed, usually lags by many hours. The classical problem is, have a meteor shower. You want to understand how many meteors pass through an area of the atmosphere per hour that are larger than a certain mass. And the units of the flux are, let's say, 5 meteors per 1,000 square kilometers per hour, larger than a microgram. So this is what we were trying to quantify with the GMN. And the idea is to get this real-time flux estimation. We would have to upgrade the detector to run in real time, which is mostly true, even on the Raspberry Pi 4. The problem is that the calibration is done at the end of the night. So we'd have to move the calibration to also run in real time. And I actually wrote a piece of code that does that. So hopefully, in the next couple of months, we will have calibrations done in real time. And then second is, the second problem is, how do you communicate these results to the server in real time? Well, that's a bit harder because we can't rely on the classical, like SFTP uploads. There will be thousands and millions during during an activity of a major meteor shower. They're gonna kill the server, and we would have to find a better way of doing it through some sort of API calls or some other way. And we also need to improve the flux computation efficiency. The method right now is fairly comprehensive and robust and very accurate, but that also makes it fairly slow. And also works in files instead of a database. So that would need to be improved to achieve real-time flux reporting. And another problem is that when you're computing meteor shower flux, you have cameras that have different sensitivity. So how do you scale it all to the same flux or the same sensitivity, the same limiting mass? We use something called a population index. We essentially assume that meteor magnitudes, meteor masses are distributed according to a certain distribution. And there's this thing called the population index, which is just kind of the slope of the magnitude distribution. That thing is fairly difficult to measure. And right now, we just assume either a default value for a lot of showers, or where it is measured, it's fixed. But it's been shown that a population index can change over time. That's something that we're not taking into account right now. I mean, our flux values are close, but if we really want them to be super accurate, we would need to add kind of a sliding population index estimation as well. And that might require producing careful analyses and studies of individual showers to get to that point. I'm not sure we can do it as a kind of a live data product. All right, and then fireballs. So I think it's pretty obvious that the performance of the fireball detector is lacking. And the reason is simple. There have been no code changes in the fireball detector for almost 10 years. I remember when I wrote this thing, we didn't have any fireball data. I would make a synthetic fireball, how I thought a fireball would look in the data, and then optimize the detector on that, which of course is different from reality. And it definitely needs some attention. So I have some examples here. Unfortunately, these slides are not going to show the video super well. So what I'm going to do is I'm going to show these individual cases. I'm going to just play the video. So this is a good example of when the fireball detector works well as designed. And this is kind of something similar to my synthetic fireballs that I used back in the day. This is great. Yeah, it's perfect. It gets the fireball from the beginning, the bright part, it's perfectly tracked. You get the pieces at the end, and that's it. It's great. It saves these little clips, these little crops, and in every video frame. It saves a huge amount of space. Amazing. All right. So the second case shows when it does an okay job, not a great job. So if we go back to here to the beginning, you can see that it gets the beginning of the fireball pretty well. And then as it gets brighter, it doesn't know what to do. And it just, you don't really get much. Now, this is maybe not the fireball detector's fault. The problem here is that the fireball becomes a giant blob, but the fireball detector has been designed to increase the size of this little window, and it doesn't do that for some reason. So that definitely needs to be improved. And then finally, here's a case where it just completely messes up. So this is a big fireball here, and you just get whatever this is. As you can see here, it gets a bit of it at the end, a few frames at the end, and then that's it. Doesn't do a good job. So that needs to be improved. Yeah, so I'm not sure I have much time to work on this. However, we have a huge database of fireballs, and if someone wants to overhaul the fireball detector, please do let me know. All right. So assuming that the fireball detector has been fixed and improved, what we can do then is we can have a fully automated fireball notification and kind of rough reduction pipeline. So as I said here in the slide, so the first step, we need to have a more reliable fireball detector. After that, we can use very similar techniques to our meteor trajectory estimation. We can have automated trajectory pairing, and then have automated user notification and automated data extraction for manual reduction. So the idea is not to have a fully automated fireball pipeline that does the measurements for you. I don't think that can ever be reliable, but it at least notices them, automatically extracts the data and presents them to you and says, hey, here's something super rough. Here's all the data, go in and make the manual reduction. I do have a sort of a beta version of the pairing code that's been developed, but haven't spent much time on pursuing this further. All right. So the next thing that's a very important component of fireball observations are the total fireball brightness. So the light curve of a fireball tells you the pre-atmospheric mass of the fireball. If you just sum up all the light that was produced by the fireball and you assume something called a luminous efficiency, which is a conversion factor between mass loss and amount of light produced, you can invert the pre-atmospheric mass. The problem is that our very cheap 8-bit sensors, commercial grade sensors, they saturate very quickly around magnitude 0. And all you get is just a giant saturated blob. Now, Damir is working on a saturation correction that is going to take the saturated data and based on the moon and Jupiter and a couple of other calibration points, try to invert back the total amount of light produced by the fireball. Now, this is, of course, always going to be limited with always going to be limited by certain, assumptions about how the camera gain works, et cetera, et cetera. Or a solution is to deploy dedicated instruments. So the team in New Zealand is doing brilliant work where they deployed dedicated lux meters that measure the absolute value of the brightness of the sky. And the assumption is that fireballs are the brightest objects in the sky on short time scales. And when they happen, you will get an absolute value of the brightness of the whole sky. So I'm going to show an example. So they had a really, really big fireball a couple of days ago. And here are individual video frames that I extracted from a video that they got. So you can see it started fairly faint, it brightened. It had a giant flare that saturated half the cameras that observed it. And at the end, you can see a couple of pieces that were left. Unfortunately, it happened over the ocean, so there's nothing to recover on the ground. And it was too fast and too high anyway. However, one of their lux meters was able to get it really well. You can see this huge excursion from the background. And based on my calibration methods, I was able to determine that the fireball peaked at magnitude -21. So it was definitely a super bolide, extremely bright. The initial mass that I inverted was about 20 tons. And assuming a rocky composition, this object had a diameter of about 2 meters. And this also enables modeling of the fireball light curve, which tells us something about the internal structure of the body, which is very important for planetary defense. It's really the only way to sample the internal structure of little asteroids, little objects. And that way, if something big is coming, we'll know how it's going to behave in the atmosphere. All right. So the second thing that we definitely need is 24/7 video monitoring of fireballs. So this is the video in question of that fireball in New Zealand. And you can see that the video makes all the difference, because you remember that case when the FR file didn't do such great of a job? Well, it was this fireball. It did a terrible job. And the video here is invaluable. So what's the problem here? The problem here is that video recording requires a lot of data storage. Huge hard drives. Just for one camera, it requires tens of gigabytes per night. And most GMN cameras run on small SD cards. So we have to upgrade to larger storage. And the problem with SD cards is they don't like continuous writes. So even if you were to enable the video recording feature, it's probably going to fry your SD card pretty quickly. So I think there's going to be, we essentially need to increase the number of dedicated systems with hard drives, with computers that have all sky coverage looking all the way down to the horizon, and a recording video 24/7, including during daytime. All right. And what are some general improvements that the RMS software needs? So right now, RMS works with these cheap IP cameras. It would be really nice if RMS could work with science-grade sensors. Like a camera that has 16 bits, that's raw, that's not compressed, and it has some sort of a format that it can save, that works in the pipeline as well. And then it would be great if the system, whether it's on the server side or the RMS itself, it's kind of a more of a philosophical question of how to approach it, that has some sort of a warning when things go wrong. So user gets an email. I think we discussed that last year. And it would be great if there's a collective status page on the weblog or somewhere on the GMN website that essentially shows and automatically sorts cameras that have some problem. And that's something that might be a bit difficult to develop, because you really need to have really good insight into what the camera is doing. So we might need to develop some additional capability of monitoring capability of just camera status and software status, et cetera, et cetera. All right, so in terms of organization, so Pete Eschman has been leading the charge on improving the wiki page. The wiki page in the current state, or before Pete took charge, was in a fairly messy state. Lots of amazing improvements. A lot of work went into organizing it and adding content. But one thing that I think it's a valid criticism is that it's fairly disorganized. So we had this idea to have a triage on the landing page. When you open the wiki, you have like 5 choices, or let's say 4 to 6 choices, and one choice is, oh, I want to build a camera. Another choice is, oh, I have a problem with the camera. And then, oh, I'm interested in the latest results and the latest science. So you can just very quickly click, and it's going to sort you into another page that's going to have the information that you need. And another thing that's being done right now is that we're consolidating information from various sources like local documents, Google Docs, onto the wiki. because that is pretty important because Google Docs are owned by individuals. And then if a document accidentally gets deleted, all the work goes away. We want everything to be on the wiki. And then another thing that, I'm definitely to blame for is just better communication with project participants. There are a lot of things that happen and that require, I would say, time and attention to properly communicate with project participants, and they just don't occur. And I think that's a big problem right now. There's a lot of cool stuff happening and then doesn't get properly communicated. And that's very necessary to keep up the motivation. You're running these cameras, what are you getting out of it? And that's something that we should think about and work on. And I used to do this more often, but now with the amount of work and the load, it's just becoming less of a possibility, unfortunately. So maybe we can have a discussion about this, or try to find if someone would be willing to volunteer, or just maybe in general keep it in mind that whatever's cool is happening, would be great to communicate it with the team. And then a final thing is, okay, so you get started and you install a camera, and then what? How do you get more seriously involved? Currently, there isn't really a clear path. It's not that we can just give you a handbook and it's like, yep, just read this and, come back after a month and, let's start doing science. Unfortunately, it doesn't work like that. And there are a lot of people who do wonderful things because of their prior experience and expertise, whether they're scientists or software engineers, et cetera, et cetera. But how do we go from, let's say, casual involvement, a little experience, and how do we build that expertise? Right now, I don't think we have a good pathway, and that's something that we can think about. Maybe some sort of a mentorship system. Let's say we have someone who's interested in doing more, we can connect them with the right person, and maybe they can help guide them in the right direction. These are some ideas. All right. So a short summary. The processing pipeline. That is being solved, and hopefully in a couple of months, all the problems will go away. For real-time flux estimation, more accurate flux estimation, we have long-term plans of achieving real-time flux reporting. In terms of fireballs, it's definitely an ongoing work, and for some things, hardware upgrades are needed. I wouldn't say they're definitely not going to be forced. Participation will always be welcome from even the oldest and the minimum viable systems. But if we really want to evolve onto the next level, I think some hardware investment is definitely going to be needed. And we have some, say, ideas and some kind of help is on the way, things that might help there. And finally, so in terms of organization, I'm open to suggestions. If you think you can do better, if you have ideas, please do let me know. And that's the extent of my talk. So I'm opening it up for discussion, questions, criticism, comments. Please go ahead. Okay, we have a question here. So Gene says, is there scientific value to be gained in speeding up the data processing other than addressing the human proclivity to need to know as soon as possible? Of those discussed, the automated fireball processing and rapid notification of potential search team appear to be the most important. Yeah, so in terms of the processing pipeline, I mean, the weblog needs to be updated every day, so we can monitor meteor activity, and a lot of, how can I put it? A lot of things. There's a scale between fully manual and fully automated. I don't want things to be in any of those extremes. I want people to still be involved in the data and look at the data, because you might see very interesting things that might not be picked up by the automated pipeline because it just doesn't conform to the idea of a meteor, a fireball, hey, maybe you're going to see like aurora or some, crazy atmospheric lightning or something that's completely out of the ordinary. Multiple fireballs coming in at the same time, like we've seen before. Those things, the systems are not designed to see those things. So you should definitely look at the data. And then second is, when a meteor shower is happening or there's a new meteor shower that appears, we need to be fast there because we need to make the measurement. We need to make an estimate whether it poses any threat to space assets. We need to report it, register it as a new meteor shower. It is also a matter of having having us as the discoverers, and also how can I put it? Maintaining operational efficiency, which is very important to show that we are a serious project. Right? Jean, go ahead. If you're saying something, you're still muted.
Thinking back to I was thinking about the genesis of my question was thinking back to the Geminid issue, and if we miss a few hours before we see the full impact of the Geminids across the system, that's not a big deal scientifically. It just we just like to know as soon as possible. So I don't know if is that such a worthwhile expenditure of your time and effort to try to make that faster? I mean, is there some scientific value in doing that, or is it just addressing our need to know?
Well, there is scientific value if something, how can I put it, out the ordinary happens, because that way you can mobilize additional resources. Let's say the Geminids have a weird outburst, or the Perseids have a weird outburst. If we can report that as soon as possible, then people are going to go out, they're going to deploy more instruments, they're going to look at their data and be able to access different things. Another thing is that the GMN data products are being used and published by space agencies and NASA as well. It is very important that whoever's operating any assets in orbit understands the evolving risks of an evolving activity of meteor showers. And that's kind of the whole goal of the network, is to be able to provide that information in real time. So yeah, real-time operations are extremely important. Damer, go ahead.
Yeah, for example, why it's important to have it as soon as possible. As we saw in the presentation earlier this evening, there was an outburst of Ursid's meteor shower, which actually went unnoticed from our side. It wasn't for fluxes that were monitored by side. We wouldn't be aware of the fact that the Ursids were in the middle of an outburst, because we were still waiting for Gemini data to be processed.
Right.
So having it clear as soon as possible is most welcome. That's the fact. So if we are waiting for a couple of days, I think this second or third time that we had such an issue with the data. Once was with the shower during Perseids. Now we had an outburst with the Ursids, and that's the point. So we would most probably be very happy if we have it like it is now, when it's dry period, no rain, no shower. So we have data in period of 6 hours or so. So that would be perfect if it were coming out with Geminids as well, but it's impossible at the moment.
Paul, go ahead.
Yeah, and also because of the Geminids, we missed the new shower that appeared in Draco that was detected by the Belarus. That's the law of Murphy. When will something unexpected appear when your system is blocked? And in fact, all these many stupid Geminids prevented us from providing data. So luckily, the small network of the Belarus detected it and could document it and report it. And yeah, we were about more than 1 week later to confirm it.
All right. Thank you, Paul. Jamie, go ahead.
Couple of points about the fireball detection. In the config file, there is a parameter. You can have the minimum pixel square size of 100, and then it can go to a bigger one of 400 pixels wide. Now, it seems to not easily decide which one it wants to do if the fireball flares. But a couple of my cameras have just increased the 100 one up to 150. Doesn't seem to affect the memory use too much. Now we've got bigger SD cards, cheaper memory. It's a cheap and dirty way of just making sure the fireball head doesn't drop off the edge of the square, which happens quite a bit. And the second point is often you get the best positional data from cameras viewing fireballs from far away. Saw that in the Scottish fireball. And simply fireballs from far away are going to be low down. If it penetrates to 20 kilometers height, it's going to be right on the horizon or in amongst the trees of a camera that's maybe only a couple of 100 kilometers away. So please, 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 if we want the network to be tuned for fireballs as well as ordinary meteor showers, just point your camera at a slightly lower elevation. Make sure and include those parts of the sky where a low penetrating fireball is going to be captured. And as for the refraction correction, there's a couple of quick and dirty fixes to RMS that could be done there. Refraction depends on atmospheric density, and the current correction in RMS is based on sea level density. It'd be a simple matter to include a couple of extra lines of code to make sure that the refraction correction was adjusted for altitude. Even without any weather forecasts, you wouldn't need any meteorological data included. Just if a camera is up at 1,000 meters, the refraction correction is going to be substantially different. And also, I've worked on a parallax correction for refraction, which further refines that. It can make about 100 meters odd difference in the accuracy at low elevations. So that's another way, 20 degrees elevation, a rough cutoff of accuracy because refraction becomes a problem below that elevation. But with those couple of adjustments, extra sophistication of the code, I'm sure you would get good data going down to lower elevations than that. I've found good trajectory matches from data down to about 4 or 5 degrees. And so that's worth considering. Just if your camera points down to 5 or 10 degrees elevation, you're covering hundreds of kilometers away, and you're covering fireball possible ablation points that would be extremely useful for meteorite impact predictions.
These are great points, Jamie. Absolutely. So the refraction as it's coded up now, as you say, it's very simple. We'd be very happy to consider better and alternative ways of doing things. If you can suggest sources and new codes, we can definitely look into that. In terms of the parallax correction, that's something that we looked into, and then we for in most cases that in most cases the problem is that the measurement accuracy at those very large distances is usually worse than the amount of correction for the parallax. The pixel scale in terms of meters at the range is hundreds and hundreds of meters versus the amount of correction. Now, it would be great to take it into account, but it will always be less than the accuracy in a sense, unless you have very high resolution cameras, which the GMN are not.
There's a sweet spot though. If you have a low height penetrating fireball, it can drop to a low elevation in the sky and really be not that far away from the camera. We have fireballs in Scotland. Well, Scotland has sea all around it, and you have a meteorite that is, if it's going to land on dry land, then it's never going to be that far away from the camera that you can't get good data. Obviously different for continental land masses, but we definitely have a few where we've been able to work with the refraction correction and fireballs that have impact points on land, and the correction does improve the fit.
I agree. So one thing that's important to understand is that the refraction correction, as things stand right now, is only applied to exo-atmospheric objects, planets and stars. When you make a measurement in RMS, the assumption is that the fireball, and we computed this, when you integrate the amount of atmosphere between you and the fireball, it's always going to be less than the amount of atmosphere from the fireball and behind, or the other way around. I'm trying to understand. Maybe Damir might know more. Whether we are applying correction, the refraction on the fireball in the atmosphere or not.
Yeah, and it's much more of actually the part which is not addressed for is not important at all, because the vast percentage of atmosphere correction is always between you and the fireball, not behind. Behind is always nothing of air, because you're considering something reaching what is the lowest level, lowest height I measured was something below 16 kilometers. So at 16 kilometers of altitude, what is the amount of atmosphere between you and the fireball and the rest of the correction? I don't think that's important. We can put it on the paper and calculate, but I think we did. I think you and me even did that. I do not remember which case was it, but it turns out that we said, okay, this is not something that we will take care of.
Yes, you're right. We are applying the refraction on fireball measurements. That's correct. But it's turned off for the ground objects. There's this feature in SkyFit where you can make measurements on ground objects. It's turned off for those ones. Yes. But
that's the other story. That's completely other story.
Yes. And there is a whole paper that was recently published by a group in Finland, I believe, on the exact refraction correction you're talking about, Jamie. They derive the derived equations. If you're interested, I can send you the paper. But it's a very valid point, and we should be taking this into account. But I believe our accuracy is less than the amount of correction. And then
it is on Meteor News in new that library stuff. So I think it's listed there.
The real problem is that it's not an analytically solvable equation. You have to do iterations, and but you can get it down to some kind of quick and dirty approximation. If you compare empirical data with the model atmosphere.
Okay, I see there's interest. I'll try to find it and post it in the chat after we're done the discussion. All right. Any other items, Jamie?
Nope.
Thank you for the comments. Before we go to Pete Eschman, who I see unmuted himself, Alex had a question. Is there a long-term plan to shift away from Raspberry Pis toward more capable devices, or will it be a two-tier network? Our goal is to enable and support what people can deploy. And there will always be operators who, due to various constraints, will never be able to deploy more expensive systems. In fact, there are operators who still, operate Raspberry Pi 3s, cameras that were deployed more than 5 years ago, and very, they have a nickel and dime budget. So the idea is that we just support as many operators as we can as that is one way of maintaining a large coverage, even though some data quality is not going to be ideal. So to answer your question, I think yes, it will be a two-tiered system. One set of cameras is going to be the standard GMN cameras that are deployed now, which are going to get what we're getting right now. Ideally, with an improved fireball detector, that's going to be doing a better job. And then a second tier system is okay. We have more capable hardware, more capable software that can get more out of the phenomenon that we're observing. So yeah, absolutely. We're not looking to drop support for lower resolution systems and cheaper systems because that defeats the purpose of the network, essentially. All right. Pete, go ahead.
Yeah, this is probably not directly related, but it seems as though there are a number of people here that might want to respond. And that is that there's been some discussion about altering the way we calculate the field of view mapping. In other words, local analysis that Gene did confirmed that he didn't have any instances of a camera pair spotting the same meteor at any distances over 350 kilometers. And so the thought was maybe these field of view indicators should be truncated at 350 kilometers.
Mm-hmm.
This really doesn't affect any actual recording. It simply gives us a better representation of the effective field of view. It would, in many cases, get rid of the very long pointed ears we see on some of the mapping. And so I just want to throw that out there. Does that sound like something everyone would agree to? I mean, to me, it makes a great deal of sense.
Mm-hmm, mm-hmm. Yeah, it makes sense. So I believe that there is a parameter in the function, and it's set maybe now to 500 kilometers. It can very easily be adjusted to a smaller number. So I'll definitely write that down.
Put it on the Mobius strip that is your list of things to do.
Right. I mean, another thing, probably the best way to do it, so I don't keep it locally. If you can open an issue in RMS and say, limit the range to a certain number, and there it's going to be transparent, so anyone can be able to pick this up and look into the problem. So it's probably the best way to document it.
I'll try to remember to raise that as an issue on the GitHub. Thank you.
Awesome. Thank you, Pete. All right. Any other questions? Paul, go ahead.
And maybe a kind of existential question for GMN. How far can we go with putting up new cameras? I remember Korlevich Corrado in 2015 in Austria going around a meeting telling everyone we have to put up 10,000 cameras. My first thought was, okay, buying 10,000 cameras, I see possible, but how do you deal with it, with the data, and how do you store it? And now I see on the dashboard of GMN, there should be 2,100 cameras with a camera ID also, 1,621 contributed to paired meteors, and meanwhile we have lost something like 253 or so that are decommissioned. But how far can we go if we put up another 1,000? Can GMN and the server follow all that input?
These are some great questions, and we're solving things along the way. So essentially, if you double the size of the GMN, of course we're going to have a problem. And we're trying to keep things available, free, flexible. But if the number was to rapidly increase by many thousands, there would have to be adjustments unless a new source of funding appears. If someone says, oh, I'm going to fund the GMN with $1 million a year, all problems disappear, right? It's all about labor, hardware costs, and right now we're trying to keep things at a bare minimum because they can be they're fairly sustainable. And we're not trying to rapidly increase the data flux rate, et cetera, et cetera. And we're trying to make do with the little that we have, because that makes the project sustainable in the long term. Because if you get addicted to more, then the problem is there's a downturn, then you're in trouble. And I would encourage people who want more capability to grow more capability on their end locally and regionally, and that the GMN remains a kind of a minimum viable product on a global scale. So for example, if you want to have 4K streaming video from all of your cameras on a website immediately and now in 3D and whatever, it's like, great, I'm going to support that 100%, but you do it on your end. Because we have operational limitations, right? Like there is no one employed full time at the GMN. It's not how it works, right? And there are things that can be supported, that would need to be, there would need to be more commitment in a sense to be able to support more. So that's kind of the general philosophy. But in terms of the numbers, I'm happy that we're out of the rapid growth phase and that we are in a sustainable phase, and that we are, how can I put it? I would rather at this stage have fewer high quality dedicated sensors than more random cameras. And that is something that I see as a kind of an evolution of the network, where we still fully support any camera contributions, but I would love to grow the more kind of the dedicated sensor part that have maybe some extra capability, full videos, lux meters, et cetera, that can unlock new science. Because we're kind of hitting the ceiling of what the GMN can do with the current capability, and some growth needs to happen that's not just growth in numbers, it's an evolution in capability. All right. Thank you for the question.
Go
I
ahead. Have a related comment, and that is, surely we get to a point where we're oversaturated in some geographic areas. The only benefit is that a cloud that might affect one camera may not affect another. But it seems like there are huge parts of the world where we have no coverage at all. And in many ways, it seems like our emphasis should be on figuring out a way to get cameras running in parts of the world where we have no coverage.
Yeah, absolutely. It's really funny because there are parts of the world that are very obvious and would be extremely strategically important for camera deployment, and yet we can't just get an in. For example, Hawaii, those longitudes are not covered by anything. We have one camera, thanks to Dave here on Cook Island. That's about it. That's probably the closest to Hawaii. But the Pacific, if something major happens over the Pacific and certain parts of the world, Western US, and like for example, New Zealand doesn't qualify because in the southern hemisphere, if it's a meteor shower in the northern hemisphere, we wouldn't see it anyway. So let's say Korea, Japan, there's a big gap there. So that's something that definitely needs to be covered. Central Asia, super important. And there's very little coverage there outside of Tajikistan. And if we could get more large multi-camera systems in Tajikistan, that would do amazing work in terms of coverage. But it all depends on, how can I put it, like infrastructure, local support. And very often people outside of the project ask me, oh, how come you don't have cameras here and here? it's not really up to us. If you might have noticed what Pavol said initially, their AMOS network, these are amazing professional grade sensors, and they have cameras in Hawaii, they have cameras in La Palma, they have cameras all over the world, but they need to travel to these places to maintain the cameras, to pay for infrastructure, to maintain that. And that is the level of involvement that, it's beyond the capabilities and even the philosophy of the GMN in a sense. We could, if there is targeted funding and people, if they want us to do something, there's no problem. We can organize that. But yeah, Gene, go ahead.
So speaking to that topic, is there it would be easier to get cameras in other locations if there were cameras that could be readily shipped to those locations. But to the best of my knowledge, we have no off-the-shelf kind of cameras to send anybody other than telling them to build their own. So is there any progress being made towards having a manufacturer, if you will, or a hobbyist to produce cameras that can be readily distributed?
Well, I would say yes, and that's something that where Luke is making some progress. And in fact, I have another set of slides which are exactly about this topic. But before I transition to this, I think that Dave Rollinson wanted to say a few things. No?
Oh, only one thing, that just going back to what Paul said, I was actually agreeing with you about saying that was against philosophy of the GMN network. Cameras getting decommissioned. Yeah, I know there's an awful lot of cameras in Western Australia that were working 6 months ago and now are not. It's almost always a PoE sensor that fails. About 18 months ago, we had a big outreach program for STEM purposes, delivering cameras to schools where people were interested and motivated. Those people then move on. The security systems for the school's Wi-Fi changes. Something breaks. There's two options. Either I spend all my free time going and arranging to visit schools to fix things up, which I don't mind doing, or I concentrate on the big multiple station installations where I've got 6 or 8 really high quality cameras that are really well maintained. The amount of time I have to spend on the GMN, and I enjoy every second of it, I think I'm better focusing on the cameras that deliver the best science that I can possibly deliver. And if the STEM side isn't working because people are no longer interested in that, there's no point in me going and maintaining the camera because it's not achieving its primary mission of doing STEM because no one's interested anymore. If people are interested, sure, I'll reach out, I'll go and support, I'll fund cameras, I'll do all that kind of thing that I'm blessed to be in a position to be able to do. But I'm not going to push water uphill. And so that's why so many cameras in Western Australia decommissioned. I'm trying to get some back online, especially in the locations where we've got poor coverage. But if I had all the time in the world, I'd do it. I just don't. But I will keep the core network functioning as long as I can do. And there's no problems with that, the big multi-station systems. Anyway,
thanks for your comments, Dave. Yeah, I mean, this really brings up the view that, camera, when we talk about a camera, it's not really just the hardware and the box. A person stands behind a camera. That is the important perspective. And there needs to be that kind of support. And I communicate directly with every single operator, and that's my perspective, is that each system is a person, and without that support, there is no network. This is just not hardware to just throw out there. It requires active maintenance and involvement, and that's why the community approach is extremely important. All right, let's continue this discussion after my next set of slides. If the slides were open. Oh, there we go. All right. Okay, share. All right. So let's talk about the camera enhancement program. So we want to enhance existing GMN installations. We were lucky to work with Luke, who obtained some funding, to be able to provide this service. And the idea is that we go from single camera systems with Raspberry Pis that have no video recording, and we take existing infrastructure. So where cameras exist, where we have people on the ground, to enhance them to 6 camera systems that have all sky coverage, that have a PC. These systems are plug and play, would have video recording, and a crucial component of this is these would be specifically contrail observing platforms. All right, so this is what I'm talking about. We go from a single camera system to the multi-camera system. And the way this funding scheme would work is that 80% is covered by grant for contrails, and the operators would have to fund 20%. So because Luke Systems, these are incredible systems built by Peyton, who's in this meeting here. I don't think this picture does it justice. When you crack it open, you'll see how well it's organized inside, and the way that the heating and cooling is done, and it's all full of 3D printed parts. The lenses are super easy to maintain, swap out, focus. I've been operating one of these systems since November. It survived winter time, no problem, and this winter has been brutal. These are the areas of interest specifically for the contrail project. So because the money, the grant, is tied to contrail research, these are the areas of interest where we want to enhance the systems. So we find through satellite observations that a lot of contrails are being made or created, generated, come about over California. And then you can see it in satellite imagery that they slowly drift over many hours over Arizona and then dissipate over New Mexico. Currently, there are contrail cameras in Arizona. Luke's is one, but there are no contrail cameras in California. So we are willing to dedicate one of the systems to California. So if you're located there, specifically Southern California, because most of the contrails and the weather moves essentially towards the east, please reach out and we'll see what we can do. We may or may not fund another camera installation in the Southwest because it's so well covered, and ideally we would want something in the Phoenix area, but Luke is already there. So we're still not sure if we would want to add more in, let's say, New Mexico. I think we need to collect a bit more data and maybe make that decision in maybe 6 months to a year. Another area of interest is the Deep South. So if you look at the amount of contrails that are detected by satellites, and if you convolve that with the amount of clear skies, so if you just look at airplane traffic and clear skies and humidity, the U.S. Southwest stands out as the part of the world with a lot of contrails and a lot of clear skies, relatively speaking. So we would like to put one contrail system there. And finally, the area around the Ottawa-Montreal area is unique on the continent because there are these, there's a system called MODES that essentially interrogates aircraft, and they send the wind speed. For some reason, that only happens, the system is only turned on, or the systems that do this only exist in around Ottawa and Montreal. Europe does it as well, but unfortunately it's not covered with GOES, the satellites, which is something that we want to pair our observations with. So these are the 3 areas of interest in North America. If you live in one of these areas and you would like a new camera system, a new all-sky camera system, please reach out. And finally, oh, Bob, go ahead. I think we already found our first location. Is that right? All right. I'm not sure.
Yeah, I'm sorry. Can you hear me?
Yes, I can.
I'm sorry, I had the headset on wrong here. Yeah, I'd definitely be interested. In fact, Pete knows that I've been pulling my hair out trying to design a 6-camera system, for months. And um, yeah, I've got the facility, and I can swap out the 2 cameras I have currently running, put it in there. I'm more than happy to invest the time and the sum and so forth to do that. So sign me up.
Awesome. Thanks, Bob. Pete, go ahead.
Yeah, I can talk to the gentleman who has a multicam system. He's located near the Vandenberg base in California. So he's already running multicam. We could try to get him to switch over to continuous mode if that would help.
Absolutely. We would have to, that would be extremely helpful. And if he's, let's say, at least 50 to 100 kilometers away from Bob's location, that would also be great. And even if they're within, let's say, 20 kilometers, that would also be good for contrails, because we might develop a similar kind of a 3D contrail observation system. So any distance in California would work. So that's excellent.
Okay, well, his system right now is a bunch of individual cameras that he built. I think it's a 5-camera system. You see the little blue dot there just above the word Los Angeles?
Yep.
That's him.
Yep.
I believe it's a 5-camera system, and it is running multicam. I don't know about his data storage. We might have to get a bigger hard drive in it.
Yep.
And I guess that's another question I would have is, how big a drive do we really need? Can we get away with a 2 terabyte SSD for a 6-camera system running video?
So for contrails, we don't necessarily need raw video capability. We just need those individual video frames. But the cameras that Luke will send, they have a huge hard drive, and they can store, I think, 2 weeks of raw videos for all the cameras. So that, let's say, that is great for fireballs and other things. But if we can get away with enhancing current cameras without installing new hardware, that would be great. But we probably do want to add another camera in the area as well.
Okay.
All right. Thank you, Pete. And then, in terms of coverage in Europe, we have a budget of 5, so these are all 5. We want to install 1 camera in the Netherlands. There is a contrail group that works in the Netherlands. There's one in Delft and a couple of other places. And they have their own optical systems. We would love if we could compare our contrail data to theirs. And that's another location for a contrail camera. And finally, we would love to have a camera in Spain. Has clear skies, and there's this group in Spain who does contrails. And those are the 5 locations of interest. The program, of course, has some requirements. There needs to be an existing installation, and the camera needs to be in good standing. So essentially, the operator knows what they're doing. And there should be no major obstructions, trees, houses, lights, bugs. Ideally, it would be a normal location without any major problems. And yeah, we would find 5 to 6 cameras in these areas of interest. And another requirement is that, as this funding comes from a contrail for contrail research, this data should be made available for contrail research up to the point to make it even open data. So with the videos and everything, so if they could be made openly available, not a strict requirement right now, but let's say at some point in the future, that would be ideal. So what's some new science that we can unlock with these systems? So obviously meteors and fireballs. So we can just increase coverage for faint meteors. If there are any directions where the new cameras can help, that's great. We get the full videos for fireballs. And then for contrails, What this is going to allow us is to observe the full life cycle of a contrail. So essentially right now, if you only have one camera, it can observe a contrail for maybe 10 minutes before it drifts outside a field of view. Having an all-sky system, you can have a contrail being made in one part of the field of view and then drift over, and you can track it for half an hour, 40 minutes plus. And of course, if we can observe a contrail that's made in California and then we catch it in Arizona, that would give it a kind of an arc of many hours, which would be super, super interesting. And yeah, so these cameras, just like essentially all the cameras for which we've developed this capability, we can directly connect contrails to aircraft because it's an important thing to be able to tell which aircraft is making a contrail. Otherwise, airlines don't care if you can't say that. And we will be able to use this information to validate atmospheric models of humidity, winds, temperature, et cetera, et cetera. And that's one of the reasons why I want to target that area up in Montreal with the Mode S data, because we would get direct measurements of the winds as reported by the aircraft, which is unfortunately not true for the rest of the continent. Yeah, this is a little summary of areas of interest, the way the systems work. And the important part is the operator participation. We're not giving these away for free. And we want the operators to have a stake in the system and to show they're serious. So that's all I got. I'm happy to take questions. Should be something in the chat. All right. Yeah, there's some comments about the thermal performance. Yeah, I mean, so Luke is running these in Arizona. I visited him in October when it was the coolest day of the year, and it was 32 Celsius. I almost died. And they survived the Arizona summer, and they survived Canadian winter. So, as far as I'm concerned, that makes them pretty qualified to run anyway. All right, so if you're interested, if you know someone who would be interested, please do reach out, as we would like to get this done pretty soon and hopefully have the cameras deployed in a couple of months. So that's the big plan on this end. All right, and now I'm opening the meeting. I'd say the regular programming is done, and I'm opening this meeting to any other discussion points, anything that people would like to bring up. All right, and if there is nothing, because there's only 40 minutes until Luke is here. Because there's only 40 minutes until the next session, I will actually keep the breakout rooms open, keep the meeting going. I'm not going to stop it. I'm just going to pause recording. And if you guys want to chat until the beginning of the next session, please go ahead. I'm going to take the time to rest a bit, and see you all in 40 minutes. All right. Good night, Gareth, and folks from Europe who are going to sleep. So thank you for joining. All right, well, welcome to our second session for today, mostly for folks in North America, New Zealand, Australia, and Asia. And I see a couple of Europeans are braving the night, so thank you for staying up to watch the talks. All right, so in the first session, we had quite a few talks. It actually went longer than expected, over an hour than expected. So we only had like 40 minutes of rest, which was actually quite unusual. I think the longest one so far, which is really nice. So the way we're going to do this is we're going to have a round of introductions, and then I'm going to do a short recap of session one. In previous years, I was able to show you the slides because I had the recording, but because this session went so long, I didn't get a chance to save the recording. I just paused the recording. So you'll just have to trust me and then go back and watch the recordings. So I'm going to provide maybe about a 15-minute summary and 15-minute recap of session 1. And then if at any point you have any questions, please interject and I can just very quickly answer your questions. But all right, so before that, we're going to do a round of introductions. Even if you are a previous GMN member, please introduce yourself for anyone who's joining us today for the first time. Please put your hand up in Zoom. There should be a button under React, under the little heart down there. And yeah, say a few words about yourself. I'm going to go first. I'm Denis Vida. I'm a research professor and a research scientist here at University of Western Ontario, and I like meteors. All right, Peter McKellar, go ahead.
Yeah, right. Peter McKellar here from New Zealand. You've been involved with GMN for a couple of years now, and with a part of an enthusiastic group here who are keeping about 150 cameras going. I actually logged in on the earlier session, but I'm afraid sleep and listening to European accents telling technical stuff didn't work, so I went back to bed. But a little bit more alert now, except there's grandchildren in the next room, so if we get some odd noises, that's from me. Anyway, looking forward to it.
All right, awesome. Thank you, Peter. All right, who's next? Bob, go ahead.
Okay, just a quick one. I'm in Invercargill, it's in the southern coast of New Zealand. I think most know quite a few of these faces. So I've just put up a 5-camera array in northern Southland that seems to be going all right. So we've got pretty good coverage in the southern New Zealand. That's me.
Awesome. Thank you, Bob. Dave, go ahead.
Dave Rowlinson, based in Perth, Western Australia. I run a few cameras in WA and also contribute to the code base a bit. Thank you very much.
Thank you, Dave. All right, Steve Matheson, go ahead.
Oh, hi, I'm Steve. I'm work with Peter in New Zealand, and we look after swag of those cameras. I'm also the guy that built the status viewer, if you have any questions about that. And that's me.
Awesome. Thank you, Steve. Hadrien, go ahead.
Good morning, everyone. Hadrien Devillepoix, based in Perth, work at Curtin University, and I work on a project called the Desert Fireball Network. Interesting fireballs.
Awesome. Thank you, Hadrien. All right. Peter Ashman, go ahead.
I'm here in Albuquerque, New Mexico. We started with GMN in about August of 2021, and we've got about 30 cameras now, looking to add another 16 or more. Hopefully bring up 3 6-camera systems if we can pull that off. I just want to give a quick status report on the successful use of the new SkyFit. I just produced a play par file during the break and got it promoted to a machine. Worked perfectly. Thank you.
Awesome. Thank you, Pete. Logan, go ahead.
Hi, I'm Logan Cordonnier. I'm a postdoc at the Air Force Research Lab out here in New Mexico. My interest is in the long-lasting trails that meteors leave behind, which I'll be talking about here shortly.
Awesome. Thank you, Logan. Jamie, go ahead.
Hi to all those in the lands down under, New Zealand, Australia. I'm up late, you're up early. I'm a meteor fiend since I was a kid. I've got some meteor cameras up on the roof. They haven't seen a bean since the beginning of the year. It's been totally cloudy. Please send us some sunshine. We need it. I'm an analysis fiend. I love doing trajectories, fireball analysis, all that kind of stuff.
Thank you, Jamie. And if people missed, you're up in Scotland. Is that right? All right.
Yes, up here in Scotland, 56 degrees north. We get summer twilight in the summer months, but we hardly see the sun in December, January. So missing that yellow golden orb.
All right. Thank you, Jamie. Next up, we have Yleana. Did I pronounce that correctly?
It's Yleana.
Yleana.
Thank you.
Sorry.
Hi, everyone. It's nice to meet you all. My name is Yleana Ceballos. I'm originally from the United States, but I'm currently studying. I'm a first-year PhD student at Kochi University of Technology in Japan. So we are new to the network. We just installed our first camera. A second one is underway, and I'll be discussing more of that later on during my presentation. But I'm happy to be joining the network. Thank you.
Thank you. All right. Who else would like to make an introduction? Luke, how about you?
Hey, Luke from Phoenix, Arizona. Nice, beautiful, and sunny today. I've been involved with GMN for a little under 3 years, responsible for bringing the Contrail project to Denis and the network, and occasionally breaking the code and fixing it a little later.
All right, awesome. Thank you, Luke. And for those who are suspicious of Luke's American roots, he's originally from Belgium. All right, next up, Steve Wynne-Harris. Go ahead.
Yeah, hi, I'm Steve Wynne-Harris. I'm a sheep and beef farmer here in the east coast of the North Island of New Zealand. I have a couple of cameras on the roof of my house and just recently installed a Fireballs 360, which is Bob mentioned, the 5-camera array with a lux meter in it. So we're rolling those out around the country. I do the media for Fireballs ATRR, and then a year or so ago, after we found Takapole, I realised that there was a title missing in our repertoire, so I awarded it to myself, Fireballs ATRR National Meteorite Search Coordinator, self-appointed.
Awesome. Thank you, Steve. Tomek, go ahead.
Hello, my name is Tom. I'm from Europe, from Poland. In general, I'm new here. In general, I specialize in king impact craters, but also meteor physics, calculating stream fields. I'm building my first cameras. I'm testing few sensors. I'm thinking about greater resolution to introduce. Let's see what will be. Thank you.
Awesome. Thank you, Tommy. All right. Anyone else? I see a couple of faces here that haven't introduced themselves. Jesse, how about you? Yes, you have to.
How about the cat? Can you introduce it?
Oh, this is Tabby. we can't hear Jesse. That's the problem. Bri, your audio doesn't work. Sorry about that. All right, Ted, go ahead.
I'm Ted Klein here in northern Colorado. Hammer radio led me to radio astronomy and now to the GMN, having great fun for about a year now with 4 cameras on that observatory behind me.
Awesome. Thank you, Ted. Ross, go ahead.
I'm Ross Dickey, and I'm from Gore, New Zealand. Gore is way down at the bottom of South Island. I'm 40 miles inland from Bob Griffin and Invercargill. I operate 2 cameras, and one in Gore and one in Tapanui. That's it.
Awesome. Thank you, Ross. I see Boris is here. Boris, go ahead.
Hi, everyone. I'm Boris. So I'm working with Denis at Western University in London, Ontario. I'm working on the contrails, so we're annotating the data set which we've been collecting from the cameras. I'm also training some machine learning models that we use to detect these contrails. So yeah, nice to see you all here.
Thank you, Boris. Boris is humble. Boris is our resident machine learning and AI expert. All right. Awesome. Anyone else would like to introduce themselves? All right. Well, if not, I am going to proceed with the summary of session one. As I said before, I don't have the recording, so I can go through the slides because it went over time and I didn't get a chance to save it. However, I will show you the session one abstract, and I will comment on the talks. And if you have any questions, please interrupt me with any questions and I'll be happy to answer them. All right, so for many years, there were a lot of questions in the forum about meteor spectroscopy, and I am far from an expert, so I decided to call the real expert, which is Pavol Matlovič from Slovakia, who has been operating special systems. And in fact, he has been doing some very cool lab work where they put a meteorite in an arc jet. So it's essentially a device where they accelerate air, extremely hot air, thousands of Kelvin, to many kilometers a second, which essentially simulates the environment at which objects enter the atmosphere. So what they do is they melt or vaporize the rock in the arc jet, and then they observe the spectrum. But he also gave us kind of a whirlwind tour of how to do video spectroscopy using video cameras, and he gave kind of an overview of the field where there's a classical method where there are three very prominent spectral lines of meteors: iron, magnesium, and sodium. And there's this ternary diagram which looks like a triangle, and you can plot up where meteors fall in different parts of the plot. And classically, there are these groups of different types of meteors. There's sodium-rich, sodium-poor, irons, et cetera, and how they relate to different sources in the solar system. If you have any more questions about meteor spectra, please reach out to Pavol. And then Jamie talked about the Great Scottish Bolide. Jamie, would you like to give a 2-minute summary of your talk so I don't butcher it?
Yes, there was an amazing fireball up here in Scotland last summer. It happened at local midnight, but still in the twilight. We had many GMN cameras imaging it. Had this absolutely humongous flare 10 seconds in, which bleached out the second half of all the camera views. We had to go scavenging for images on the internet. It was widely reported in the media, lit up the whole country, brighter than moonlight for a split second. So we found all these Aurora cam images. There was a fisheye weather meteor cam image, and we were able to do the usual trajectory estimation. There was a stunning iPhone 16 Super Pro Max video that showed all the fragments in minute detail, and that really rounded off the calculations at the end of the trajectory. There was some trepidation in the UK meteorite community about whether or not we should go and look for it, but it was in very remote terrain. There was no public roads and there was only one railway station, the highest railway station in the UK. But fortunately, Luke Daly, who's from Glasgow University, part of UK Fireball Alliance, he was very gung-ho, raised a budget for all the food and hostel accommodation, and we all trooped up to this hostel by a loch for 5 days in August. The weather was mixed. We got eaten alive by midges. First time I've been up to 3,000 foot level in Scotland for about 30 years. Completely knackered me, but we were up on the ridge looking for meteorites, and unfortunately we didn't find any. I was with my colleague Will Joy, who's an expert meteorite hunter in somewhat hotter countries than Scotland, and the teams of several people searched for days on end on several of the mountain ridges in quite good search terrain. Sadly, we didn't find anything. The search for the main mass was spoiled by risks of thunderstorms, so we hope to go back this year. But it was the best time I've had in the whole year. We suffered for our art, but we enjoyed every minute.
Thank you, Jamie. And whoever's interested in fireball trajectory measurements, they should definitely watch the talk. I mean, Jamie's talk is a master class of how fireball trajectories should be measured, and the dark cloud analysis should be done. So definitely watch the video if you're interested. Thank you, Jamie.
Thank you.
I have to add, and I say to Jamie, I was highly impressed by the mountain terrain that you went into. It was very impressive. Yeah.
Awesome. Thank you for the comment. Next up, we had Justin. He was a summer student with me last summer who developed a method of automated measurement on meteor camera imagery. This is not necessarily for the GMN. It's for a narrow field camera that we operate here. It's kind of a very super fancy camera that can count individual photons, extremely sensitive, where meteors look like little streaks, little kind of Gaussians that are streaked. So he developed a method of fitting 2D Gaussians, 2D moving Gaussians to imagery. And it's very impressive, but not a lot of use for GMN imagery unless we want to manually analyze a lot of narrow field camera imagery. For example, if someone's operating a 16 millimeter camera and they want to make manual measurements, this is the way to go now. All right, and then we had Quanzhi who talked about looking for big killer asteroids. So essentially, all impacts on Earth, as far as we know, are random, come from the near-Earth objects and the asteroid belt. And it is a tantalizing thought that what if there is a source that's coherent? What that means, it's not random. They might be coming from a particular orbit. In 2015, the Czech meteor group noticed, and of course the Polish as well, noticed that there are a lot of fireballs coming from the Taurids, which are in very similar orbits, and they've essentially confirmed the existence of this Taurid swarm, which come in very concentrated orbits. And there were a couple of asteroids, 100-meter size asteroids, which might have been connected to this swarm. So what Quanzhi has done in collaboration with our group here is took those fireball observations, and then we directed a search for these big asteroids. During a period of opportunity in 2022, we haven't found any, which is a good sign, which means there aren't any giant killer asteroids coming from the Taurids. But it's not let's say the case hasn't been closed yet. And there's going to be another opportunity in about 6 years, and we hope that the Vera Rubin Observatory will be able to observe it a bit better. And then we had Jürgen Rendtel, who is a visual observer, extremely experienced visual observer, who talked about the comparison of meteor rates observed visually and using the GMN flux, and how we were able to see some very unique meteor shower activity that otherwise would be missed. And then we had Alex from Romania, who joined the network just a couple of months ago, but already hit the ground running, developed some really cool new software where his software records the video in real time, and then if something gets detected by RMS, it cuts out the whole video in color and then saves it, pushes messages through Telegram, notifications through Telegram. Very impressive work, and we're probably going to see more from him soon. Then we have Hervé, who talked about the deployment of the GMN network in Morocco, and they're going to be deploying quite a few more cameras there in the next year or so. And then we have Kokhirova from Tajikistan. They operate cameras in a very, say, unique place in the world. At the Central Asian longitudes, there aren't any cameras for various reasons, and they're the only ones. In fact, the GMN strategically funded those cameras there, so we have good meteor shower coverage at almost all longitudes, and they presented some analysis of the meteor observations from their cameras. And then we had Regina Radowska, who works for the European Space Agency and is a member of the International Astronomical Union's group that essentially holds the keys to meteor shower naming and classification. And she essentially gave a talk of how the GMN has contributed to establishing a lot of meteor showers, but also gave instructions of the kind of proper procedure of how one should follow if we want to report a meteor shower or establish a meteor shower. Next up, we had Patrick Shober, who talked about his work that was published in Nature Astronomy. Very impressive. And he essentially demonstrated that there are a lot of carbonaceous chondrites, which are these extremely primitive meteorites. Let's say there's a dearth of them that fall on the ground. And it wasn't really clear if it was an atmospheric filter because they're much weaker than stony meteorites. And he essentially showed that, in fact, if you look at the orbital data, including the GMN data, he showed that, in fact, they don't even make it to Earth. And then the atmosphere is an additional filter. And that's why the number of recoveries of carbonaceous chondrites is so small. Next up, we had Chloe. She's a student at the University of Manchester, and I recently started working with Chloe on making a comprehensive catalog of GMN fireball observations, which we are planning to publish. And she might be even looking for collaborators who'll be willing to manually analyze the fireballs that we have in our hands. And it's going to be a part of her PhD thesis. And then we had Mirjana from Croatia, who talked about the Comet Chasers project, which is pretty interesting. This is another citizen science project where they operate robotic telescopes to observe comets, and even a new comet 3i Atlas, and a couple of other comets that are currently active, and I think anyone can join in. And then we had Auriane. So you might remember a couple of years ago, there was this object called 2023 CX1. It was first discovered as an asteroid in space. We had a few hours until it hit the atmosphere. And if some of you were there for the first session, she showed a video of a person in Australia talking to his family, and the family went crazy when they saw the fireball. That's Hadrien. He's right here on this call. Auriane talked about all the scientific analysis and the amazing science that we were able to do using this on this asteroid, and how it's the first time that we had an asteroid in space, a fireball in the atmosphere, and a meteorite in our hands. All right, and then we have the contrail hour. This is a new field here at Western, and we had essentially an overview of why tracking contrails is important. Emily talked about the science behind contrails and how they're important for climate change and what we can do about them. Then Liam talked about the technical side of things, so the machine learning detector and the associator that he developed, and Luke talked about the contrail detection pipeline and the huge amount of work he put into RMS, into SkyFit, into automated plate fitting using SkyFit. And in fact, it's so cool that after I'm done with the summaries, I'm going to show you what I mean, and you're all going to be extremely impressed. And finally, in this session, we had Tristan. And Tristan works for contrails.org, which is a nonprofit in the US and the UK. And essentially, they interface with the policymakers, with the airlines, and they're the ones we are collaborating with regarding contrail observations. And essentially, they will, once we have a final data product, they're going to be the ones communicating with the stakeholders and who are going to help us mitigate 1 to 2% of climate change, hopefully. All right, so that's all in terms of the first session, and I did promise that I will show you how the new fitting algorithm works. So some of you might know a thing or two about making calibration plates, and we have the software called SkyFit. So what I'm going to do now is I'm going to call SkyFit on a data set from Spain, and I'm going to run the code. And I'll pretend that I don't know where this camera is pointing. I don't have a calibration plate, so I'm going to say cancel. And it's asking me for pointing information. Let's say I have no clue where the pointing is whatsoever. I'm just say cancel. So it's going to use some default numbers. They're going to be all over the place. And we can search for an image with stars. Let's say that I like. See this image here. And the usual step would be to find a pointing and then manually click on all the individual star pairs to make a calibration. Well, we don't have to do that anymore. There's this beautiful button here called AutoFit. You hit that button, the software automatically finds the pointing. You can now see in the background the stars are roughly aligned. And now it's asking us, do you want to proceed? Do you want to make a fully automated solution? I'm going to say yes. And now in the background, you can see how it's finding a better solution. And there it is, done. This is a fully automated fit. If you look at the fit residuals, they're bang on. Almost 30, like 40 arc seconds. And this is going to save us a lot of time. There are a couple of other upgrades that were made in SkyFit, which are, I would say, kind of quality of life upgrades. So for example, if I get rid of all these stars, now you can see star names. See exactly which star you're looking at. We added planets. You can see spectral types of stars, and even we added constellation lines. So you can see Gemini here and a few other things. So yeah, it's very super easy to use now. And there's a whole other section for star detection, and there's too much to cover now because we're running out of time. But yeah, if you're interested, definitely talk to Luke more about it. But this is an impressive piece of work, and I think we're planning to merge it into the main code base in hopefully a couple of weeks. So, all right. So that's all I got.
Does that deal with the distortion models and all that sort of thing? Does it deal with the distortion models, right?
Yep. Yeah. Fits the distortion, fits the photometry, gets rid of residuals. It's a complete calibration, a complete automatic calibration. In fact, it's automated to such an extent that there's a script. You just tell the script, look at this directory, find a file that has enough stars, make the fit in the calibration plate, and that plate should be good to use. And after a bit of experience with the automated script, and once we take care of all the kinks, we are planning to have a fully automated solution where you install a new camera, the camera realizes, hey, I see stars, I don't have a plate, let's make a plate, and that's it. We won't have to make calibrations anymore. It's going to be fully automated. It's going to save a lot of time. Pete,
is that in pre-release? Is it?
No, it's in another branch called Feature Psych Kit Image, but it's going to be in pre-release soon.
A complete misnomer. It started as I wanted to get rid of an old package, and then I fell in a rabbit hole, and I was like, oh, wait a minute, and I can't let it go now.
Yeah. Yeah, I believe it started as you try to use a different method, and I told you, hey, why don't you just use Ransack and see what happens? And here we are. Awesome. Amazing work, Luke. All right, sorry, Pete Ashman, you have a question, and let's start.
No, I just have a comment. I mentioned this earlier, but I want to reiterate. Literally during the break, in a matter of about 10 minutes, I switched to the right branch on the Windows machine, grabbed the files, produced a new plate par, just clicked on some of the obvious stuff. I just ran it on the archive files directory, and it was like within 0.1 something pixel. So it worked perfectly. Automatically went to radial 7 odd, I think.
Yep.
And I did the pick the best image and just said do it, and it was done. Very impressive.
You may have been the first one to test it on Windows, so I'm glad it worked. Because on Windows,
well, you're welcome.
Because actually on Windows you don't have the local astrometry.net packages, so it went to this server over here to find a solution.
Did. Yes, in no time at all.
Yeah.
I mean, there was no noticeable delay or anything. It just did it.
All right, awesome. Well, we're a bit late. We need to let Hadrien tell us about drone-assisted meteorite recovery. Hadrien, go ahead.
Right, I'm gonna share my screen.
We can see it.
Can you all see it? Great.
All good. Go ahead.
First thing I'll say is I'm very impressed by the recent developments in automated astrometry. I had to play with that myself for like one specific type of our cameras a long time ago, and I know it's a massive effort. So seeing that is awesome. So yeah, today I'm not going to be talking too much about fireball data reduction, which is what I mostly do or like usually look at. I'm going to be talking about in the like fireball to meteorite pipeline, the actual like recovery part. So this project I've had the pleasure of like project managing for the last couple of years. And I'm going to tell you how that works. So first, to like just paint the scene. A lot of people here would be familiar when you have a big fireball, you got a chance for a meteorite, and obviously finding fresh space rocks, like rocks that if it fell recently was spent the last 4.5 billion years in space and is now on Earth, and we can pick it up. That's very exciting. The problem is. Sounds like Jamie's covered a lot of the fireball calculations, which is a great introduction for that. It's like we can't pinpoint usually to like within meters where the meteorite is, and therefore the question of how do we find it is a relatively big one. So the way this has been, I guess, traditionally done is you send people out, depending on how remote or how many people you access to. Like you could have anywhere between say like 4 and maybe 100 people. I think there've been searchings done with over 100 people, which is amazing. And then you'd walk up and down on the area where you think there would be meteorites, and the area you're looking at is typically on the order of like a couple square kilometers or a couple hundred hectares. For that in the different units, but it's like really tedious work. So those are GPS tracks of a search I did a couple of years back. Unsuccessful one. I think we found about 7 horseshoes, but we didn't have any luck finding the meteorites on this particular occasion. Then what naturally comes to mind when you're doing that, at least for me, and to other couple of people, is well, surely there's a better way of doing this. And for me, that comes after half an hour of like manual visual searching, walking up and down. We're like, well, surely there's a better way of doing this, and a drone imaging the ground sounds like a reasonable way to start. To cut it short in terms of like where we are now and how we got here is like, so we had a PhD student called Seamus Anderson, who's now doing a postdoc at NASA. That was basically his job. His main PhD work was to solve that problem. He solved that problem. I gave him as a test case. There's lots of testing campaigns to get there. A lot of things to put together because you got to capture the data, process the data, and then obviously present it to humans in a meaningful manner. So it's useful. And then 5 square kilometers of a full site, he found meteorites, probably about, I think it was about golf-sized ball. You can see the scale with the Sharpie there. I was really impressed with that. So here's the case I gave him. We didn't have particularly good fireball observations, only 2 observations. One of them was about 400 kilometers. So like getting kind of some data reliability issues. It's like, here's the area there on the right. It's big. Good luck. And if you come back with a meteorite, I'll be very impressed. And he came back with a meteorite. So that's where we were at the end of 2021, beginning of 2022. Problems we've had with what he developed. So Seamus wasn't a trained software engineer, didn't have any training in software engineering. And obviously it was very code heavy. So like code base wasn't very stable. Bunch of the logistical problems, like we're trying to operate basically gaming computers in the field, and where we go, we usually get temperatures like 40 degrees. We're all powered from generators or solar, and that created like big problems for keeping things running. If you've got a computer just on its own, takes like half a kilowatt. And it was also very, very heavy on the people in the field, because you couldn't get any sort of help, or you couldn't get people from the outside to help you with like the review process, all that stuff. It was all done locally on one computer. So this is what we're trying to address with like the upgrade package I've been managing over the last few years. I don't know how well you can see this, but this is what basically our current solution kind of looks like. So we've got a drone here capturing images of the ground. We do use it with like an RTK, it's a real-time kinematic space station, to make sure like the metadata, GPS metadata in altitude in particular, is really nice, and the altitude remains nice and constant, so we get consistent data quality without having to do too much overlap on the drones, but making sure we actually like see the entire area we want to cover. Every time the drone comes back for battery change, we get the SD card out, put in a laptop, and then we start basically, we start uploading that data currently via Starlink to our cloud web platform, where basically like everything happens. So all data processing, which relies on another virtual machine that does all the heavy lifting, like the machine learning side of things for meteorite detection and training those models. Then detections can get reviewed by people who are outside the field, which is for us is a massive time gain. People from like comfort of their office can just do the clicking around, all the human manual steps we can fully get rid of. So that means that people who are in the field then can babysit the drone and then do the follow-up in the field, and really concentrate on the activities that people in the field like have to do. So that's the general gist. There's probably about a year's worth of like a good software engineer's time to actually make all of that work. It was a pretty big effort, but I'm just going to run through like the steps. So first we capture some training data. So training data can come from either real meteorites or spray painted black rocks that look like they could be convincing, at least to a human, like meteorite shapes and colors. Take drone pictures of them and label them. So we've got that interface in the new web platform to do that easily. So how do we detect meteorites? Under the hood, we use the YOLO model that we like retrain specifically on meteorites. But yeah, it's basically the same types of machine learning models that you've seen that detects like, that can detect like various things. And yeah, that's pretty impressive. But it tells us in the images where the meteorites are and what's the, I guess, confidence that those are actually meteorites or some of the things. So there it is applied on white meteorites. So it gives us like bounding boxes about where the meteorites are. It also gives us a size of the objects we're looking at directly when we do the georeferencing with the drone, which is quite handy. And then the review process. So out of that, meteorites are rare. They don't particularly look different, at least to a drone or even to a human standing a few meters away. They don't look very different to other black rocks, to, in Australia, kangaroo poo, wombat poo, spider holes, a bunch of other false positives that are like basically inevitable. We can't really make better training sets to work these things, or we can to some extent, but we still get tons of false positives. Because for us, we really don't want to be missing the meteorite we're interested in. So we have to let in lots of false positives, like on the order of 100,000, which sounds like a lot. But if you got a team reviewing those on the computer before you actually have to visit every single one of them, then that process is quite efficient. So the idea is that we've got different reviewing stages. We'll look at them on computer first time really quickly, just like a small thumbnail, and then we can look at in a bit more detail, like zoom in and out, like is there other similar looking candidates around. Then something we used to do, we don't do anymore, was send a follow-up drone to avoid humans having to walk. Turns out that step is not really efficient compared to how efficient we've made the actual in situ follow-up for humans. So I'll get back to that. So I'll just go over very quickly. So that's what the interface looks like. It's like a 3x3 tile that's mapped on the on your keyboard. So you can just quickly, is this potentially a meteorite? Just say yes. So you can actually run through run through pretty much those 100,000 with like a team of 10 people, like relatively quickly, without people having to spend like hours, days at their desk doing that, which also you don't want, because then they get tired and they might miss things anyway. Yeah, second stage, so yeah, just get a bit of a wider view in the meteorite, can zoom in and out, which is quite handy. And it's like, do you still think this could potentially be a meteorite? That's really the question we're asking. And if that goes through, then we take that directly to what we've been calling stage 4, which is the in situ follow-up. People in the field, so we've developed this, so it's currently in the web on the website basically, but it's like a GPS like enabled little map that's got satellite imagery and the drone imagery at like full resolution, basically like overlaid on that, so you can zoom in right in to see everything, and then you see yourself like move on that little app. So it's basically like Google Maps, but with drone images and our meteorite targets. So we're able to like very quickly hit a large number of targets. So just going to tell you about a recent case we had middle of winter last year. Actually, it was just after Meteoroids conference, which was cool. Got some help from Denis to model that one, because it looked a bit weird. And predicted an area that's outside of our, I guess, typical prime meteorite searching ground. So here we're looking at the like southwest corner of Australia, and we've got the Nullarbor Plain, which is a limestone plateau where it's generally relatively easy to find meteorite. But as you can see, we're slightly outside of that, so it means the terrain is quite different. There's actually some variations in elevations, which create some logistical issues for drone flying. So we had to cut it up in smaller sections of like where the altitude of the ground was relatively constant, but it was about 1.6 square kilometers. And then we sent a team of our PhD students out. It was a long drive. I think it was like 800 kilometers from our base in Perth, most of it on like good roads, but then towards the end it was kind of I think a day of like this sorts of driving, and I think they even have to get an axe at some point to create a track to get to the full area. Not going to play the whole video in the interest of time, but you can go back to it if I share the slides later on. There you go. So drone we use, not going to spend a lot of time there. It also doesn't matter too much which drone you use, as long as it's got something with a decent like RGB camera. We use kind of a professional drone for that, just because it's like goes a little bit quicker than like a smaller like DJI Mavic, for example. But it doesn't matter too much, apart from the real-time kinematics part, which is now available on most kind of like semi-professional drones, starting from semi-professional drones. Yeah, so this is what the interface looks like. So we get a really good overview of like all the different steps, the different stages of review, how are the uploads going. So the upload is actually our bottleneck currently. So Starlink, we can only pipe through about 4 megabytes per second of data where we are. And that's kind of doesn't quite keep up with over 24 hours with like the amount of drone data we're collecting. So uploading all the time, and we typically manage to upload maybe about 80% of what the drone captures. So try to obviously to start with the areas where of higher likeliness for meteorites. And as soon as we got things processed, so meteorites detected by the algorithm, reviewed by people and what can be reviewed, so like eliminating most of the false positives, so getting help from lots of people, then we start getting this map with candidates that we need to follow up in the field, and then people in the field can just immediately start doing that and walking around with their tablets and start obviously saying no, unfortunately, to most of them. On this one, they had a lot to go through. Like they had to go to, I think, 700 to 800 of those targets. And then right at the very end, so basically our 3 PhD students, so Del, Yona, and Michael, split the last remaining candidates between themselves, but these were the last ones. They hadn't found the meteorite. They were like starting to lose hope at that point. But turns out the second to last one was a meteorite. So I think it was the 727th out of 728. So yeah, literally leave no stone unturned. Like go to the very last candidates, even if you've lost hope at that point. So this is what it looks like in the drone image picked up by the algorithm. Also gave us a nice indication of the size of the object as well. can you spot it in there? So this is the full resolution, the full 44 megapixel resolution drone image. It's a bit hard to see, but yeah, there it is. It's just this little black thing in the corner. So we had a very happy team of PhD students who just found a fresh meteorite sample. They were really happy. I was really happy. Really showed now that the thing works, and the new platform, the new workflow works really well. It came back having the meteorite is about 300 grams. As you might have seen from the image, it was like kind of off the fall line, the nominal fall line quite a bit. We still have to investigate like why that is and look at models again maybe. Another picture of the meteorites. One thing I'll say is the crowdsourcing aspect, like getting help from people from the outside, is really important. So this was another fall site where we did not find the meteorite we were after, but we found 6 or 7 old meteorites. As you can see, obviously people doing the stage 4, the in situ follow-up, they were like the 2 guys in the field, but then those candidates, you can see they were picked up by like other users in the previous steps, and I think that makes it like quite powerful. Like we get a lot more people involved to help with that process, and they can basically take ownership as well of those discoveries, even though they're not in the field. So I think this is quite powerful. I'm not sure how I'm doing on time, but I'll give my summary here. So like it's really a massive logistical data problem I think that we've solved, and I think it's working almost as good as it could now. Much faster than obviously humans, and obviously less brain draining than manual visual searching. It's for our purpose of meteorite searching, it is fully operational. So next steps for us is we want to share that tool. We want other people who can run their own drone surveys to come and log in, upload their data, and run their own teams to find their meteorites. So if you want to try it, even if it's just a test, you don't have a specific stream field to search yet, and you just want to get ready for it, please come talk to me. I'll get you access on the platform. Yes, and I'll leave it there. And there's the web address if you want to go have a look for the platform. Thank you.
Amazing, Hadrien. Very impressive. All right. Are there any questions for Hadrien? I guess everything becomes a data problem, right? Steve, go ahead.
Yeah, we had one little go with a thermal drone. Jesse could speak to it if his mic was working. He was there with my son who had the drone. Any thoughts about that? Perhaps not so relevant in a situation like this where you've got a lot of rocks, but for us over pasture or something would be handy. So anyone done anything with thermal drones?
Yeah, so there's a really good paper by Patrick Hill on doing thermal on snow in Canada, where as you might imagine, the black rocks on snow, that becomes, for a thermal point, becomes a lot easier. Like the meteorites are hot, everything else is cold. I think so. One problem with thermal is how quickly can you survey an area at high enough resolution with a thermal camera, because thermal cameras usually are quite low resolution. To me, that's a limiting factor. We're hoping to maybe integrate some of these like multispectral or thermal aspects to eliminate some of the candidates that the RGB gives, but I don't really see the RGB as a first step for surveying going away anytime soon. But I think thermal multispectral could become useful for the follow-up in ruling out some of those candidates, so we don't have to walk to 800 candidates before we find our meteorites.
Awesome. Thank you, Hadrien. I think in the interest of time, we have to continue. A short comment about black rocks and snow or ice. In 2000, when Tagish Lake fell, it fell on an iced over river. And over a couple of days, because the black rocks soaked up the solar radiation, they heated up, they melted through the ice, and they became locked in the ice. They had to use chainsaws to release them and to cut up huge blocks of ice to get them out. So
very Canadian.
Very Canadian. Very Canadian. All right. Thank you so much, Hadrien. I know a lot of people have questions, but Peter, please write your question in chat, and I'm sure that Hadrien is going to answer it. All right. Thank you. Logan, you're up.
Share my screen here. Hopefully you can see that.
You're all good to go.
Okay, great. So this evening I'll be talking about meteor radio afterglows. So to just give a brief overview of what those are, these were first discovered about a decade ago by Ken Obenberger, and they are the intrinsic radio emission produced in the plasma left behind from a meteor. So they last anywhere from tens of seconds up to a few minutes or so. The emission itself is broadband, unpolarized, and isotropic, and has been observed so far between about 20 to 60 megahertz. So the video on the right here shows an example of an MRA seen by a all-sky radio telescope array. The emission mechanism, however, is still somewhat mysterious in that we aren't quite sure what plasma processes are going on that produce the MRAs. So a couple of options are Langmuir waves or a thing called resonant transition radiation. However, those are outside the scope of this talk. Both of these explanations, however, require a source of suprathermal electrons, which are equally mysterious. So in order to make the radio observations, we used a long wavelength array in New Mexico at the Ceballos site. As seen in the bottom image here, this is an array of 256 of these kind of bow tie antennas arranged into an ellipse. It's capable of observing between 10 and 88 megahertz and has an all-sky imaging mode known as Orville, which has a 20 megahertz bandwidth divided into 198 individual channels, which is capable of imaging the sky every 5 seconds. For data storage purposes, these 198 channels are averaged down to only 6 for long-term archival storage, and that's the data I looked at for my research. Now, in order to find the MRAs in this radio data, we actually did a directed search using a previous catalog of phenomena known as persistent trains that I've spoken about the past couple years at this conference. So we use those to search directly for the MRAs, basically saying we know a meteor occurred at this time and place in the sky based on this previous catalog. Let's look at the same place and time in the radio data to see if there's any corresponding emission. So doing that, we ended up with about 2,900 meteors that the LWA could have observed, of which only 675 were actually seen to have produced any sort of detectable radio emission. And I'll point out that the persistent train catalog was originally based on Global Meteor Network data. So there, in the past, was pointed out that there's a potential association between persistent trains and MRAs. So persistent trains are the optical kind of analog to this radio emission, long-lasting optical emission that some meteors produce. So in 2020, Ken observed there were 4 meteors that had both the optical and the radio emission, and from that kind of hypothesized that maybe they share a joint emission mechanism. Evidence for this was that the 2 emissions corresponded with each other, but not necessarily with bright parts of the meteors like flares. However, based on the data we obtained for this research with the 675 MRAs and 600 some persistent trains, we ended up finding they don't really strongly depend on one another. They have no problem forming independently in that you could have a persistent train without an MRA and vice versa. However, statistical tests did show they do co-occur more frequently than would be expected if it was a purely random, independent phenomena. So there might be some sort of underlying connection going on there. So I'll just show a few of the results from this MRA catalog. This plot here shows the average velocity of the parent meteor versus the flux density at 38 megahertz measured in Janskys. That's essentially just a measure of how bright it is in the radio frequencies. So from this, we can see a pretty clear dependence that higher velocity meteors are capable of producing these brighter MRA events. And that makes sense because the ionization or the amount of plasma that the meteor produces scales as a function of velocity, Therefore, the faster meteors produce more plasma, makes it more likely for whatever plasma processes are going on to occur. We can also compare the MRA flux, the radio brightness on the x-axis here versus the parent meteor brightness on the y-axis. And again, we see a pretty nice dependence here, where brighter meteors in the optical tend to produce brighter meteors in the radio. And finally, we calculated the spectral index of the MRAs, which is basically the relationship between the frequency it's observed at and the brightness of the MRA at that frequency. So these have a power law relationship where the exponent is known as the spectral index. So for these meteors, we found it had an average value of about -3.3, which is consistent with previous studies. So our sample here is pretty much representative of what had previously been observed. Now, something about MRAs that was known back in 2016 is that they appear to have a lower altitude cutoff below about 90 kilometers. So this bottom figure on the left, the solid blue line shows the expected altitudinal distribution of the meteors, whereas the red histogram shows the actual altitude range spanned by the MRAs. So you can see there's a very significant shortage of MRAs below about 90 kilometers. And you can see that as well in the figure on the right, which is from our 675 events. There's a pretty precipitous drop below about 90 kilometers. And this likely has to do with the number density below that altitude starts to ramp up pretty quickly, such that the plasma mean free path isn't quite long enough to support the emission. Now, something else that was previously observed for the persistent trains for the optical phenomena was that the occurrence rate of these events varied very nicely in a semi-annual fashion. So you can see its variability over the roughly 2 years of our data taking campaign, and it has very nice twice-a-year increases. And this is closely mirrored to the ozone content at that particular layer of the atmosphere, which is very necessary for the light production in the optical regime. MRAs, on the other hand, as shown in the bottom figure, do not exhibit these same variabilities. In fact, you can pretty much draw just a straight horizontal line and pass through the uncertainty bars. It's also important to note that the instrument itself, the LWA, wasn't necessarily consistently sensitive over that window, insofar as it had like software updates and hardware difficulties, which also could have influenced the resulting shape here. Something else to point out is that the velocity dependence of these two different phenomena. So in this figure, average velocity is shown on the x-axis. The occurrence rate of each respective phenomena in percent is shown on the y. The red line shows the occurrence rate of MRAs. Again, it's very heavily skewed towards higher velocities, with those above about 70 kilometers per second having a 40% occurrence rate or so. And this tracks with what I said before about how it's related to ionization and velocity. MRAs, or persistent trains rather, on the other hand, shown in blue, are skewed towards these lower average velocities. And that has to do with the fact that the ozone that they need to produce light exists only in a certain layer of the atmosphere. And if it's going too fast, it's likelier to burn up higher in the atmosphere and not make it down to sort of the sweet spot where the ozone lives. And if you want to see one that has both an MRA and a persistent train, your best bet is to look around about 35 kilometers a second or so, where these two lines intersect. And finally, sort of an interesting, unexpected result is that there appears to be a very strong dependence on the entry angle of the meteor. So entry angle here is shown on the x-axis, where 0 degrees corresponds to being parallel to Earth's surface, 90 degrees is coming directly down. The MRA events, those shown in red, heavily prefer the shallower entry angles. So this leads to maybe two potential possibilities, insofar as it's either something physical, in that actually being more horizontal is more favorable for whatever plasma processes are going on in the MRA, or this is some sort of geometric or observational bias such that the angles between the radio telescope and the MRAs are more favorable for detection when they're shallow. We did some examinations on this particular question. However, it's somewhat inconclusive because the data all came from a single station, so it's difficult to disentangle between the two possible scenarios. However, we're lucky here in New Mexico in that there are 3 of these LWA stations, so that going forward, the plan is to observe the same event from more than one station, which should hopefully give an idea of whether this is an actual physical mechanism or just has to do with the particular angle that you happen to be seeing the meteor with. So just to summarize here, the catalog that we produced of these 675 MRAs is the largest to date, and it is largely consistent with previous data in terms of altitude, spectral index, and so on. We also found that persistent trains in MRAs, while they do appear to have a statistically significant connection, aren't as closely related as previous studies had indicated. The MRA rates don't seem to have any sort of seasonal variability, but they do appear to have at least a strong observational dependence on the entry angle, which we hope to resolve with follow-up research. This data has all been published in this journal article down here several months ago. And I'll just end by saying that without the Global Meteor Network data, it wouldn't have been nearly as comprehensive as it was. So thank you, and I can take questions now.
Amazing. Thank you, Logan. I have maybe a first question, and maybe a question that's it would be in mind of someone who's done forward scatter before. How do you know that these are not reflections?
Yes, that's a good question. Partly because they are broadband, so they are emitting over a range of frequencies. For something like forward scatter, it would be whatever the transmitter is transmitting at that particular frequency would be very strong, as opposed to being over a range of frequencies. So that's kind of the biggest clue. The other is that we see them all around the sky, not from a particular direction, as would be necessary for some sort of forward scatter.
Thank you, Logan. And another quick question for Logan. All right. If not, thank you, Logan. And if someone does come up with a question, please put it down in the chat. And next up, we have Pete Eschman. Pete, go ahead.
Okay, let me see if I get the screen share to work now that I really need it.
We can see your screen, and we can see you and we can hear you. Go ahead.
Okay. We have released 2 RMS images for Pi, one revised and one new. The bullseye image has OS and RMS updates. The bookworm image is now obsolete because Trixie has fixed problems we had with that image. Trixie is now the recommended image for Pi 4 and Pi 5. These updates are required because RMS, the Raspberry Pi organization released Trixie. When they release a new version, the previous version, in this case Bookworm, moves to legacy status. Then the version that was legacy, in this case Bullseye, moves to obsolete status. The Bullseye software repository is now frozen and not updated with new versions of software like GIMP, which we use for making our mass files. We're still seeing a few system updates for Bullseye, but they will dwindle and eventually stop. As you may know, OS updates have already stopped for our old Buster systems. We continue to provide RMS code updates for Buster and Bullseye, but stopped providing them for Pi 3 Jessie in June of last year. Bullseye is a legacy image for Pi 4. We are keeping it For now, for those who are unwilling to give up older remote control software, such as AnyDesk, Real VNC Server, TeamViewer, and NoMachine, Bullseye cannot run the new Raspberry Pi Connect software, which requires the Wayland display protocol. Memory swap storage has been increased to 2 GB for both images. This should improve paging content in and out of RAM. And the wiki section 3.7 documents how to use both images. If you want to replace an aging micro SD card, we strongly encourage you to upgrade to a new system. Upgrading helps avoid problems and reduces support loads on our GMN volunteers. Trixie has moved to Wayland graphics, which replaces the older X11 graphical interface. Older remote connection software requires X11 and does not work under Wayland. We believe older software will eventually support Wayland. Otherwise, the revenue streams from paying customers will dry up. You can switch Trixie to X11. However, this step backward requires reinstalling Conky screen display. Trixie offers remote connections using Raspberry Pi Connect. It is free to use with a small number of connections, but payment is required when more connections are needed. The free version limits access to system owner, and access is not intended to be shared with others. For most people, Raspberry Pi Connect may be preferred, while RustDesk may be more appropriate in other cases. RustDesk is a great open source option for remote connections on Trixie and Bullseye. RustDesk install options are covered in the shared directory located under user RMS. It works well for a collection of Pi and Linux PC running RMS. It runs from a single RustDesk server. However, it is possible to use multiple servers by specifying the server and, if required, server key in the connection stream. If you set one server as your default and connect using another server when needed, you can actually have your default server configuration one way if primary connection is to a number of Meteor cameras, or set differently if you need connections to both Meteor cameras and outside systems. For Trixie, VNC connects inside your local network. Tools like Tailscale can provide an IP address for VNC connections outside your local network. Wayland VNC does not support file transfer on Trixie. On Bullseye, you can still use the free VNC server for connections outside your network, and file transfer is supported. File sharing is supported by Raspberry Pi Connect and RustDesk. Files can be shared inside your local network with directories set in Samba on the Meteor system. The Samba directories shared and RMS data are configured for both images. Read-write permissions are enabled for shared, and while read is only enabled for RMS data. Your Samba directories can map to virtual drives on a PC running Windows, Linux, or Mac OS. RustDesk is a great open source option for remote connections on Trixie and Bullseye. I'm sorry, I lost my place. Why upgrade to a new image? Image upgrade is a great option when it's time to replace an aging micro SD card or to move to USB connected SSD drive. Upgrading avoids diminished support for an old version. As fewer people use an old version, there are fewer people to spot problems and maybe less time available for volunteers to provide solutions. Upgrading lets you take advantage of newer and more capable Raspberry Pi Connect for remote access. You may benefit from newer, more capable Python engine and a more optimized operating system. Maybe it's time to move to a new Pi 5, which can run up to 3 cameras. If so, Trixie is required on a Pi 5. When upgrading to a new image, be sure to use Scripps RMS Backup, which creates a zip file containing your important files, and it saves it to the user's home directory. Copy the zip file to a USB drive and have it handy later for disaster recovery or by moving important files to a newly flashed image. Always be sure to check the wiki before flashing from an image you downloaded earlier. We periodically update our images with operating system and RMS code patches and updates. What's coming next? We are rolling out a move to multicam. I'm sorry. There we go. We're rolling out a move to multicam data structure even for single cameras. This will be a highly recommended but opt-in process. This moves vulnerable key files away from areas where RMS update operates. These key files, including config, mask, plate par, and camera settings JSON, they will be protected. Data storage is moved to a camera ID subdirectory under RMS data. RMS utilities will be able to operate with old or new data structures. For those running Pi 5, adding a second camera will be a logical extension of the new system. We are moving towards a hierarchical structure for settings now duplicated on multicam systems, placing them in a single system config file. A system config file would include static values like latitude, longitude, elevation, and other config parameters. Camera-specific values would reside in small config files located in the camera ID directories. Basically, the system file would be in this area, and then the camera ID files would be in the individual camera directories, even for a single camera system. And basically, what would happen is the station directory would hold the common values. And as you know, much of what is in a config file is stuff we never touch. It has to do with a lot of the internal settings that are used for processing. So the search for config parameters would start in source RMS here, and then it would proceed to stations, and then it would proceed to the camera ID directories. The config parameter found at one search level would override anything found at a higher search level. If no value is found for a given parameter, default values would be used. Documentation for Bullseye and Trixie is in the wiki section 3.7. Section 3.6 documents RMS plots and images that are created each morning on your system. Multicam Linux and Multicam Pi docs have been revised and are linked in section 2.3, Advanced RMS Installations and Multi-Camera Support. Wiki links to Google Doc files have been replaced with PDF versions, and this content is being migrated to wiki formatted text. Help is needed to improve documentation. It would be great to spread the workload over a group of volunteers to speed up changes. Thanks for your time, and I'll be happy to hear comments and try to answer any questions.
All right. Thank you, Pete, and for maintaining these systems and then, yeah, keeping up with the incessant pace of of upgrades and OS updates. I don't know what we do without you. I see that Dave has a question. Dave, go ahead.
Yeah, just to reiterate that comment, working on documentation is everyone's least favorite job, and you do such a great job, Pete. So thank you so much for the work you put in.
Absolutely.
Well, that's certainly appreciated, but we really need to spread that workload over a bigger group of people. So would, I think, be highly valuable if we could get a team of people going on this. We had a link to a guy who's a semi-retired technical editor, but he unfortunately was unable to continue working with us, at least for this year. So that's kind of set us back a bit on the type of redesign that Denis had spoken about, with buttons for the big choices, and then a clear Q&A section, a clear problem-solving section, and so forth. So volunteers welcome.
I see that Luke has his hand up. Is that a volunteer, Luke?
Yes, Luke.
Yeah, no, I just wanted to thank you so much for what you do. It's really tough work and underappreciated. You've asked for help. You've been sending a lot of help signals the last few weeks and months, and so we really have to do something about it. So I don't know how do we, Denis, I don't know if you have any idea, like how do we raise that level? I mean, we don't want to lose Pete.
Yeah. I mean, he's a key part of keeping things running for sure. To get someone to that level, I mean, you need someone with enough expertise to know what's going on and then be able to produce documentation. Yeah, find people who are willing to participate. I don't know what else to say. I mean, you know, if we can in any way, you know, stick the I don't know. We can probably try to, you know, use some, you know, newer tools for reorganization and see if something comes out of that. But, you know, that would also have to be manually checked.
Yeah, because it's really the wiki page that how do we keep that up? Like it's a bit of a nightmare.
Mm-hmm. I think after the initial reorg and once the triage is done, I think that is going to tremendously help. And we have an outline of how we want to do it. The way I like to explain it is I don't know if you guys watch Idiocracy, but when the guy goes into a hospital and
I
then
live in one.
the nurse has to decide what's wrong with him, and there are these like icons and they're all like pictograms. It's like, oh, something's up with his head. Oh, something's up with his leg. That's pretty much it. It's like you go to the wiki page, you land there. Oh, I want to build a camera. Oh, something's wrong with the camera. Oh, I have a question about something. Oh, I want to know about science. And from there on, once you're triaged, it's much easier to follow the structure. Because right now, when you land on the page, there's a lot going on. And exactly. And that needs to be significantly simplified. And I think we have a strategy of how to do it. And then once that is in place, it will be conceptually easier to keep it updated. Because right now, I think the problem is, let's say, oh, I want to go in, I'm going to maintain the wiki, I want to do something. And you're just immediately slammed with all the various parts and you don't know what to do and where to put it. Once an initial reorg is done, I think it's going to make it 100 times easier than it is right now to add content and maintain things.
Right. As a developer, like when we change something in the code, I don't ever go to the wiki to say, help, well, I need to change this because it's not current anymore. And maybe I should, maybe we all should do that.
Right. And you don't know where it is, right? But once we have it built and then camera operations, under camera operations, there's going to be like calibration. Okay. You know, right now there's a whole page about SkyFit and how to do things. And once you're there, you can automatically update it and just add a section, auto calibration. And it's super easy to understand, what's going on. So yeah, the initial reorg is very much necessary. That is, I think, the crux of the problem. Not necessarily the content itself. Yeah.
All I've done recently in the past few weeks is shoehorn stuff into the old structure as best I can. In other words, edit the section on flashing images so that it's pointing to the new stuff, try to document the two current images, but it's all sitting within the old framework. And I think when it comes time to moving files that are basically doc files now represented by PDFs, it's a matter of getting that content reformatted as wiki content. And then it's more open for edits. But I am very new at wiki editing, as you can tell from what I've done. I mean, I'm dropping new images in on Demir's plot explanations, and they're blowing up much bigger than they should. You gave me a link to how to reduce the size, but I haven't had time to go back in and do that. And there are a lot of our new plots that aren't explained, and they need to be explained. I mean, we've got the new FF intervals plot that has no explanation anywhere. I mean, I've got an image sitting there now. We just need to put some text, around it. At any rate, that's sort of where I see things.
Yep. Thank you for comments, Pete. Yeah, we definitely need to take that into consideration. Yeah, let's stay in touch. That's all I can say. And maybe follow up after the meeting to say to the main group, these are the conclusions. We definitely need help on the wiki. Priority number one, happy to chat with people who are interested.
Right.
Yeah. Try to get people on. Awesome. All right. Well, thank you, Pete. And we have a final talk. We are over time, but we have a final talk in this little subsection. It's Sam Hemmelgarn. Unfortunately, Sam can't make it. She is currently observing. She's running a telescope at Lowell Observatory. I think they're hunting for Kuiper belt objects. However, she did send a recording of the talk, which I will play right now. So, give me a second here. So some exciting work that resulted. It's a result of my research visit to Lowell a year and a half ago, where we decided to do a bit of machine learning, and Sam is absolutely brilliant when it comes to that. Okay, sharing my screen with sound, and please yell if something's wrong. I'm playing the video now.
Hello everybody, my name is Sam Hemmelgarn. I'm a second-year PhD student at Northern Arizona University. I am excited to share with you all this project that we've been working on, data-driven physical classification of meteors using GMN data. I've been working on this with my advisor Nick Moskowitz along with Denis Vida. And if you attended the GMN meeting last year, I did a talk regarding this project then, but I'm excited to share with you all how it's evolved over the past year and what we've come up with. So as I'm sure many of you are familiar with, meteor events such as the one on your left are recorded by meteor cameras all over the world on a nightly basis. When these events are observed by 3 or more cameras, they can be triangulated, and from that we learn information about the meteor such as its radiant, its orbital properties, and physical parameters. Specifically, what this research focuses on is how we can use these physical parameters to determine whether the meteor is of asteroidal, cometary, or carbonaceous composition. One current method of teasing out this compositional information is by calculating a meteor's Kb value. The Kb parameter is based off a theory by B.J. Levin, which described how heat conducts through a meteor once it enters the atmosphere, and it's dependent on certain material properties of the meteor. Saplecka in 1957 rearranged Levin's equation, called the left side Kb, and then put all of the observables on the right side. In that paper, he evaluated just over 200 photographic meteors to determine theoretical Kb values based off the known properties of iron, stony, and porous bodies. He then further classified another 3,600 meteors in his 1987 paper and defined the groupings that we use today. That you see listed along the bottom, the asteroidal, carbonaceous, and cometary classifications. The primary limitation here, however, is that KB takes a small number of input parameters. While Ceballos was able to create this method with several thousand meteors, today there are many networks around the world observing meteors on a nightly basis. Here I listed just a few of these networks. This is definitely not an all-inclusive list, but I wanted to point out that the GMN alone maintains a publicly accessible data set of over 2 million meteor events. With the rise of AI and machine learning algorithms, this presents a unique opportunity to apply new techniques to these large data sets. With that, the science driver of this research is to see if machine learning can classify meteor composition based on observed properties, especially given the number of measured parameters we have for each event. Specifically, we're applying an unsupervised clustering algorithm to GMN data to do this. As far as the data that we use to train our machine learning algorithm, we use data from the Lowell Observatory cameras for all-sky meteor surveillance, otherwise known as LOCAMs. LOCAMs is a network of GMN cameras consisting of 48 cameras across 8 stations in the state of Arizona. We used observations from 2023, and this data set initially consisted of about 60,000 meteor events. We used the best 50% of meteors from that data set, which gave us 28,177 meteors. Each event had 13 features or observables, and some of those features you can see listed down at the bottom of the slide there. What you're looking at on the right-hand side is a plot of our data with initial velocity on the x-axis and beginning height on the y-axis. We calculated KB for each meteor event and color-coded them based on the broad physical classification they fall into using this metric. We then use these groupings as a roadmap of sorts to ensure that our algorithm is producing results that translate into physical reality. So when our algorithm clustered data in a manner similar to what we see in the plot, we considered those physically realistic results. We also evaluated the ability for KB to produce distinct clusters with the silhouette score. We also applied silhouette score to our results from the clustering algorithms. And that's the number that you see at the bottom of this plot here. And I'll explain what a silhouette score is here on the next slide. As far as the methods that we used, our workflow consisted of data normalization, dimensionality reduction, and then applying a clustering algorithm. We explored multiple techniques at each stage, including different choices for the number of clusters, because many of the clustering algorithms in the sklearn package require the number of clusters as user input. But for clarity and for the sake of time, I'm just going to focus here on the final workflow that we used, along with the 3 and 11 cluster models that we ultimately adopted. So we began by normalizing our data, and normalization ensures that each feature has equal weighting. And the function we used was the sklearn min-max scalar, and we normalized between -1 and 1. The dimensionality reduction technique that we settled upon was factor analysis, and I'll go into further depth on the next few slides of what factor analysis is and how it works. But dimensionality reduction techniques are important because they simplify high-dimensional data by identifying the most informative features. They also speed up computation and make the data easier to visualize and interpret. For clustering, we settled upon a Gaussian mixture model, which clusters data by modeling it as a combination of Gaussian distributions using expectation maximization to assign points probabilistically to groups. And what's really cool about the Gaussian mixture model and even factor analysis is that once you train the algorithms and you get the coefficients from that training, you can then back out the mathematical formalism for both of those techniques and use those coefficients to apply the model to future data sets going forward, which is something that we were hoping to get out of this project and that we actually did. Finally, we evaluated clusters based off of inspections. So we compared the clusters that we got from the clustering algorithm to the initial velocity begin height KB plot that you saw on the previous slide. We also use silhouette score, which is a metric used to evaluate how well an object fits within its assigned cluster compared to other clusters. So scores closer to -1 indicate that data points may be assigned to incorrect clusters, whereas scores closer to 1 are indicative of more well-separated clusters. To give you a little bit more insight about what factor analysis is and how it works, factor analysis is a dimensionality reduction technique that identifies the latent or unobserved variables that underlie the structure of a given data set. And what factor analysis does is it models the observed variables as a linear combination of a smaller set of hidden factors. Mathematically, it's very similar to principal component analysis. And what it's going to do is take the spider diagram, which is quite clunky with 13 different observables, and then reduce them down into just a few latent factors that capture the main structure in the data. Now, when we run the factor analysis with 3 components, this is what we see. Note that what is listed here are the strongest features contributing to these factors. All parameters contribute to each factor in one way or another, but those with smaller factor loading scores don't meaningfully influence the factor structure. So what's pretty cool about factor analysis is it uses the covariance between these observable parameters and pulls out that latent structure, which is different from principal component analysis, which takes that variance and tries to maximize it between the 3 components or however many components you're using in your analysis. And what's also more interesting about factor analysis is it gave us the opportunity to interpret what each factor is and what latent variable is describing each different factor. So in factor 1, we interpret that as the kinematics of the meteor because it contained the parameters such as the velocity parameters and the beginning and ending heights. Factor 2 we interpret as a size normalization factor, or even observing geometry is captured in that factor as well, because you see zenith angle, trail length, mass, and duration. And then what ended up emerging as probably the most important factor governing how meteor behaves in the atmosphere is this activation threshold factor, which contained parameters such as energy received before ablation, the beginning atmospheric density, and beginning height. When we apply the factor analysis Gaussian mixture model algorithm using 3 clusters, what we see in the right-hand panel is that it recovers the primary structural trends found with KB as seen by the separation between cometary and carbonaceous meteors. The more important visualization here is the one on the left-hand panel, which shows how these clusters are distributed in factor space. Along the x-axis, we have the kinematic score, and the y-axis is activation score, where the location of the scatter plots represents the median value for each cluster. The size of the scatter points translate to the median size normalization score, where you can think of larger points as meteors that have higher masses, and then the contours you see encapsulate 66% of the data points for each cluster. The way these are interpreted is that a high kinematic score translates to higher velocity meteors, whereas the activation score quantifies a meteor's resistance to ablation in the atmosphere. As we would expect, cluster A, which seems to consist of mostly carbonaceous meteors, has a higher activation score, while the 2 cometary groups have lower activation scores. In the 11 cluster model, we recovered a similar broad separation between cometary and carbonaceous meteors, but with additional internal structure within each group. While this visualization contains a lot of detail, I want to focus on 2 clusters that are important for how we arrived at our final classification. So cluster B, shown on the left, occupies a broad region of factor space and doesn't map to a well-defined region in the panel on the right, unlike most of the other clusters. Similarly, cluster F appears as a high-velocity cometary subcluster that overlaps the same region of factor space as the other cometary groups. Since neither of these clusters exhibited behavior that translates cleanly into a distinct physical population, and because the Gaussian mixture model provides membership probabilities for each event, we ended up reassigning these meteors to the next most probable cluster. To aid in the physical interpretation of the remaining clusters, we applied the trained model to 9 well-studied meteor showers with measured bulk densities, and we also examined the orbital regions occupied by each cluster. Here, I'm just going to focus on the orbital distribution analysis. So we used the Tisserand parameter with respect to Jupiter because it incorporates 3 key orbital elements: semi-major axis, eccentricity, and inclination, and it's already pre-calculated for every event in the GMN dataset. Along the top of the plot there, you're going to see classifications in Tisserand space, while the vertical annotations indicate our interpreted divisions in activation threshold score. As expected, cometary clusters occupy comet-like orbits, and asteroidal or carbonaceous clusters fall in asteroidal regions of orbital space. The primary exception is cluster A, which exhibits asteroidal material properties while seeming to reside on a cometary-type orbit. The physical interpretations here inform what we refer to as the H-class model, which maps to the inferred material hardness of a meteor. Now that we've identified the types of material that populates each cluster, we can add some physical interpretations to them. So I'm going to pull that activation versus kinematic plot we saw a few slides back. Back over here, we've gotten rid of cluster B and cluster F, and we've added our physical interpretation to each different class onto this plot. Now we've also ordered the class names based on activation score. So class A, the hardest carbonaceous group, has the highest activation score, and cluster K, the softest cometary group, has the lowest activation score. And what we found through all of this is that there seems to be this natural separation between hard and soft, where harder carbonaceous type meteors tend to have positive activation scores, and soft cometary type groups tend to have negative activation scores. So here are my key takeaways. I'm going to kind of skip over this since I'm running a little bit long. If you'd like to refer back to it, I think Dennis will post a recording. Feel free to pause there. But I'd rather leave you guys with my contact information since I can't be there with you to give this to you live. There's a QR code to my GitHub that contains the code of the analytical model that we derived from the machine learning algorithm. So please feel free to download that. I just want to note that I need to push an update to make the classifications produced by the code match what was presented here, because it was kind of a late iteration to reorder the clusters by their activation threshold score. But the code works. Feel free to download it, make any changes that you would like to it. Feel free to edit and all of that kind of stuff. Also, please email me if you thought the talk was cool or would like some more detail regarding any aspect of the project. Shoot me an email and I'd be happy to fill you in. Thank you. Have a good meeting.
All right, that was Sam's talk. Yeah, if you have any questions, please email her. But because we've done this work together, maybe I can answer a question or two. I mean, in summary, all the previous classification methods were more, let's say, theoretically based. But what Sam was able to achieve here is just looking at meteor data, the composition comes out. You can nicely see the the cometary objects, the harder asteroidal objects all come out. Even iron objects come out just by interpreting the data in the right way, without imposing absolutely any theory and biases on the data. Which this is the power of data science. All right. Any questions here before we move on? All right. Well, if not, let us take a very short break until 45 after the hour. That way we'll all get a chance to for a bio break or something like that. And then we're going to continue with Dave's talk. See you all in a few minutes. All right, let us continue. Dave, are you ready?
I believe I am. I will try and share my screen.
All right.
Here we go. I've got the audio turned on now, so
Awesome.
Hopefully when everything disappears, it's going to work. Great.
Yeah.
Okay, my name's Dave Rowlinson. I'm a volunteer at Perth Observatory, and when I first became involved with the GMN, I reached out to Perth Observatory and said, look, I've become part of this project. I've got a camera in Western Australia. There's very few other cameras. Could I put some on your roof? And I thought, being a professional observatory, they would go, who are you? You know, go away. But they said, no, that's a brilliant idea. Please do come along and show us what you could do. So we put up one camera, and then we put up another camera, and then more and more and more, and then more stations, and the whole thing just got bigger and bigger and bigger. And one of the issues that occurred to me is, how do I know whether I'm seeing the whole of the sky or not? This was a chat on the group chat, and I did a terrible job of explaining what I needed. But eventually, Denis realized what I wanted was a plot in the azimuth and elevation plane of the pointing of the cameras. And he went away and he wrote it very, very quickly and came back. And the result was something like this. So if I just drag what that's plotted on the desktop, you can see we've got a fairly chaotic spread of cameras pointing up at the sky. Some of them overlap and there's some gaps. But how good my camera pointing isn't the point of this talk, is to try and illustrate some of the things you can do with this little utility. So it's stored in the RMS code base under utils, and when you want to run it, Python -m utils, field of view sky map. and it works on the standard multicam directory structure. So it'll look into source stations for any cameras that you've got, and when you run it, it reads in the configuration files, it reads in the plate paths, and it produces that pointing. Now that's all great. That chart is great, but wouldn't it be nice if instead of north being off to the right and it arranged like a sort of a sky map, the north was upwards? So we can do that, and we can arrange it like that. And that for me was a lot more handy, because then I imagined myself looking down upon the cameras and at the way they were pointing. One of the problems I often have with the cameras is a little PoE injector fails, the PoE splitter fails. So often I want to ping the camera. And when I do that, I need to know what the IP address of the camera is. So another feature that got added was you can plot the projection of the cameras, but also include the IP address. So if you can't see a camera or camera's not responding, you can quickly work out what IP address it should have and then ping it. That's really handy for trying to debug installations where you've got lots of cameras and you can't necessarily remember what the IP address is, especially if you've got it written down on paper and you've got it pinned to the wall somewhere. That was a really, really great feature. But how about the actual field of view itself? You can see I've got one camera there, which is very, very small on this. It's I think it's either a 15 or either 12 or 25 millimeter camera. I'll just get rid of the camera that's over the top of it. So plot this again, hopefully G should disappear. Great. So we've got the camera K. Where is camera K? What's camera K's actual field of view? So if we just add another command switch, instead of just giving the IP addresses, we can see it's got a pointing of 20.8 by 11.2, 227.3 square degrees of sky is covered by that camera. Now, it looks really worrying because that camera is pointed south, and isn't the sun going to be a problem? Because these longer focal length cameras often struggle when the sun is pointed straight into them. But of course, I'm in the southern hemisphere, and the sun is no problem at all because it's in the north for me. So that's a plot of the position of the sun every 8 hours throughout the year, and you get that classical, almost litigious figure showing the path of the sun through the sky. Well, given that we don't have any concerns with the sun, how about the moon? Because often you can lose a lot of observation time because the moon is across the field of view of the camera. This is a much more messy plot because the moon's a little bit less organized the way it moves around the sky. And you can see that my cameras that point north, yes, as expected, they get the moon through the field of view, but the cameras that point south aren't so badly affected. And I'll get rid of the moon because the moon makes a real mess of the plot and it all becomes quite untidy. Now, a while ago, there was a nova in Lupus. I think it was maybe 2 years ago. So if I want to see if any of my cameras could pick that up, this is where I get the RADEC wrong and something goes wrong. You can type in a RADEC, give it a little title and run that. And we will see that, yes, there's nova in Lupus. The RADEC is up at the top, 27.0 minus 40.1, and it does sweep through the field of view of camera AU000D. Well, that was lucky. And I think a couple of years ago, we did actually recover quite a good image of that nova from that camera. Now, there is the blaze star, which is going to crop up, hopefully, anytime soon. Hopefully not right now, because I think it's really close to the sun right now, so we're not going to get much observation of it. So let's try the RADEC of the blaze star, 237.1, 28.3. If I'm getting any of these wrong, please forgive me. I'm not. Oh dear, what's going on? Oh yeah. Please forgive me. I do. What's it complaining about? show raw deck. Oh, that's it. I'll put it in quotes. Right, so I've not got much of a view of the blaze star because it's very far into my north sky. It rises just before my dawn, and it's only there for a few minutes. But could I take my long focal length field of view camera and point it north? Well, if I just put the sun back on there again, show sun, I can see that the sun never actually gets far enough north in my sky for it to become a problem. And especially during our summertime in December, which confused a lot of people from the Northern Hemisphere, I think the sun will be around here. So it'd be quite brave, but I think I could move that camera AU000K and point it in the area. And then if the blaze star does erupt, I might be able to recover something. It's still quite brave to do that, I think, but I think I could get away with it. If not, I'll tell you all next year that I've burnt out my camera. And finally, let's look for a star that is probably well known for everyone, Cadopus, which is show Radek 237.1, 28.3, Canopus. And if I plot that, I will see that it goes through, I put it in quotes again, haven't I? I've got the Radek wrong. 96.0 minus 52.7. And it does in fact go through the field of view of my long focal length camera. And hopefully, if everything goes well, if I look on the GMN weblog at around the right time of day, Canopus should come into view just up here, and there it is. So for this one star, on this one occasion, all the math checks out, and the star's in the right place, roughly the right time. That's all I have to say about that utility. I found it quite useful for doing this kind of work, seeing what images, what cameras pick up various objects in the sky. And are there any questions?
Thank you, Dave. This is brilliant. Yeah, questions? Of course, the plan is to use this with T Corona Borealis, right? When it happens.
Absolutely, absolutely. So, and then the whole T Corona Borealis led to an extension to Event Monitor. This again cropped up on the groups when someone said, "Could we use the GMN cameras for monitoring this?"
Yeah.
And now we can, and that feature will probably get rolled out later.
Yeah.
Yes,
yeah.
Bob.
I came in a bit late. What is the utility called, and where can I find it?
It's in the standard RMS repository. So you go Python -m utils field of view sky map, and then if you're using a multicam setup, tilde source stations. And the data I'm using comes from a file that's included in the RMS repository. So if we go ls source RMS tests example station data, there's a bz2 file in there, stations.tar.bz2. That's actually that exact data set. We use the cameras from Perth Observatory because there's nothing confidential about it. It's a publicly known place. And if you've got any questions and you can't get it to work right, it could be my code, or reach out through the GMN group chat. I'm on there. I'm on there plenty.
All right. Thank you, Dave. If there are any other questions for Dave, yeah, put them into chat, and maybe at the end we can do a bit more demonstrations during the Q&A and workshop. All right. Thank you, Dave. And next up we have Yleana. Go ahead.
You'll have to take my screen up with Dennis because I've lost my Zoom control window.
Yeah, absolutely. There we go. All right. I'm going to mute your audio and stop your video. Is that okay? Okay. You got it on your end. All right. Yleana, go ahead.
Hello, everyone. Thank you. Can everyone see my screen?
Yep. Still in the presentation. Oh, yeah, it's all good now. Please go ahead.
Okay. All right. So hello, everyone. Good morning. My name is Yleana Spayos, and I am a first-year PhD researcher at Kochi University of Technology, supervised by Dr. Masa-yuki Yamamoto. So today I'll be presenting on our current status and future plans on integrating the RMS system with our radar, infrasound, and upcoming spectral systems for precise mass and trajectory analysis of meteors. So our focus is on developing a multimodal observation approach to improve the accuracy of these determinations. So a little about me. That picture is of me at JPL with a replica of the NISAR. Just to give you some context, I have a background in mechanical and biomedical engineering. So this is a new space that I'm stretching into, but I've always had an interest in space observations. So I have some research experience at NASA, Wallops, and JPL with a focus on navigation and photonic crystals for X-ray imaging. And at KUT, my current research, as I mentioned, focuses on the multimodal meteor observation analysis. And I specifically am interested in constraining meteor mass using integrated data from various sensors. So this interdisciplinary approach, I believe, leverages my experience in both engineering and space science. A little bit about KUT. KUT has a legacy network for forward scattering radar observations of meteor activities, and this began in 2003. The main station is a 5-channel ham-band radio meteor observation interferometer, HROIF for short. And it previously received a continuous wave with a frequency of 53.75 megahertz in the VHF band. And then we also have 2 additional receiving stations with single antenna each. These are Yagi-Uda antennas. And they were established at distances of 23 and 13 kilometers away from the main KUT location. So although operations are currently suspended as of right now, this infrastructure provides a foundation for integrating new observation modalities and expanding our research capabilities. So I'm looking forward to getting that up and running within the coming months. In addition to radar, KUT also has an infrasound sensor network, which consists of about 35 sensors, which are distributed all across Japan. But a majority of the network is distributed over Shikoku Island, which is where KUT is situated, and it's, I believe, the 4th largest island in Japan. And each sensor is integrated with, I believe, a 3-channel accelerometer, barometer sensor, microphone for detecting the noise level, and these sensors detect ultra-low frequency waves from meteors and reentries, which provides valuable energy data. And so this network enables us to capture the acoustic signatures that complement our other observation methods. And so as far as optical goes, we have established a permanent optical station here at KUT a few months ago with RMS, and we are situated in the southeastern part of Shikoku Island. So this is a map of Shikoku, and the blue dot is where KUT is situated. And so, of course, this geometric arrangement is crucial for enabling multi-station observations. We plan to deploy a second station in the west. This is a rough outline of what we expect, but we're not exactly sure where point B is going to be as of right now. We're determining that and hope to set up the station within the coming months. So this will significantly enhance our ability to track meteors in 3 dimensions. And of course, as most of us know, one of the most powerful tools is understanding meteor composition through spectroscopy. And so by capturing the spectrum, we plan to use ZWO ASI cameras with diffraction gratings to capture the spectra, which allows us to transition from not only tracking meteor movement, but also analyzing composition, which would provide deeper insights into their properties. So that is also underway. And of course, determining meteor mass is a complex challenge, and single mode data often leads to ambiguity regarding meteor behavior. And so by integrating all these modalities, we can cross-check physical, chemical, and visual properties and reduce uncertainty, thereby improving the reliability of our results. So the RMS cameras are intended to provide coincident observations of meteors observed by the radar network, which should overlap with the main beam of the radar. So that also is going into deciding the location of our second camera. And so we are trying to determine mass by establishing the relationship between energy and light produced by these cameras, and factoring in luminosity and calculating mass and mass loss from that. So all of these plans are underway. And once again, by combining these modalities, we hope to achieve a robust mass determination once all of the stations are set up and we are able to collect data from that. So this is the pathway that we are looking into evolving KUT into a more comprehensive multi-model observatory. So our first RMS station is active. We are JP 0005, and the infrasound stations are, of course, fully operational. The next steps are, of course, the deployment of the second obstacle station. Spectroscopy is underway, and getting radar back up and running, finding a transmitting station for that. And then we will fully integrate all of them, which would complete the multimodal framework. Additionally, some projects that we're working on are using SkyFit2 to process raw video input from fireballs that have been observed in the local area. Most recently, there was a fireball in August of last year, which was reportedly one of the largest reported in the region in several decades. So we are currently processing that and also combining that with infrasound data to analyze that event. So thank you very much for your time. This was an introduction into KUT and what we are currently working on over here with several different modalities and sensors. If you have any questions or would like to collaborate, please, you can find me at my email. And also that is a QR for my portfolio. Thank you for your attention.
All right. Thank you, Yleana. This is absolutely brilliant work, and yeah, simultaneous observations, both optical and infrasound and radar, is exactly what we should be doing for meteors and fireballs. And an absolutely brilliant project would be, if you have access to a very dense infrasound network, is definitely a comparison between infrasound yields and optical energies. And I would say a very key enhancement to the system would be the installation of those lux meters that the folks in New Zealand operate, because they will give you absolute and calibrated light curves of fireballs in a very easy way and absolute energies. So you definitely want to talk to them and try to set up a system like that. Yeah.
Thank you very much for your input. I will definitely look into that.
All right, awesome. Any other questions for her? All right. Well, I'm glad to see that someone else is also braving the spectral work, and we're looking forward to hearing updates from your end in the next couple of years. All right.
Thank you.
Awesome. Thank you. And the final talk is a recording by Mark McIntyre, who unfortunately couldn't make the meeting today. And his talk is about the ongoing improvements in the GMN data solver and pipeline. So one thing that I haven't mentioned is that at the end of the last session, I had a couple of slides on all the problems with the GMN. And if you're interested in hearing about everything that's wrong with the GMN, please make sure to watch the recording. That's going to be up on YouTube later today/tomorrow. And Mark here is tackling a very significant portion of the problem of the GMN or pipeline sometimes being late by doing a lot of code restructuring, optimization, and improvement. All right, so I'm going to share Mark's video. Let's see. This share sound, share, and play.
Hello, everybody. I'm Mark McIntyre, and I'm going to be talking to you today a little bit about the work that we're doing to improve the performance of the GMN data processing pipeline. That's the back end that takes all the data that your cameras are uploading and uses it to generate the trajectories, the orbits, and all the other information about the meteors that we've detected. So a bit about me. First of all, apologies for not being with you in person. We're at European Astrofest today in London, where my wife's giving a workshop, and so we can't be with you online today. But I'm an astronomer and astrophotographer based in Oxfordshire. I'm a member of the UK Meteor Network, and I'm section director for the Society for Popular Astronomy in the UK. So what is the problem that we're working on? So we're a victim of our own success as a network. When I spoke to you last year, I explained that the volumes had grown considerably, and that the solver was running too slowly. In fact, it's reached a point again, unfortunately, where it's taking more than 24 hours to process a day's worth of data. Last year, we did some work on the most computationally intensive part of the process, which is the Monte Carlo stage, and I'll show you a bit about what that means in a second. But now it's the initial stage of the solver, the simple phase of the solver, as I call it, that is the bottleneck. Additionally to that, the network is now generating as many as 500,000 observations a week. And that means that the database, the observations database, has become enormous and unwieldy. And that's really slowing down the system and makes it really hard to do any kind of work to speed things up. So that's what we're focusing on. We want to speed up the initial solution stage, and we want to improve the database. I said replace here, and that is actually what we're doing. So this is the original solver, a very simple diagram showing the original solver with a phase to find candidates. And a candidate is essentially just a group of observations from different cameras, which might be of the same meteor, and which we're going to try and solve to see if they are the same meteor. And then what we used to do is used to chuck it into a solver, which would do a simple solution, just very quick and dirty solution to see if it made sense physically. Is the meteor traveling up into space instead of down? Is the altitude impossible? Is the speed impossible? That kind of thing. We do this sort of simple checks there, and then we do a much more complicated, much more precise analysis using a Monte Carlo simulation, and that generates the fully scientific, accurate data that we get out at the end of it. And originally, we couldn't do any of the reports, couldn't build the website or anything until all of this had finished, and so you can see why it was a problem. Used to take between 30 minutes to 3 hours to do the first stage, and the second stage was taking as long as 8 days a couple of years ago. We did significantly improve that. And the data volumes, these numbers for data volumes are significantly out of date. We are now getting much bigger data volumes than this. So what we did in 2025 is we split that second step, the solving step, into two. We split the simple part of it away from the Monte Carlos. And then we designed the Monte Carlo stage so that it could be run in parallel, independently from the simple stage. And that meant that we could run the simple stage, generate some output, which we could use to build the website and the reports. And meanwhile, in the background, the Monte Carlo step could go off doing its thing and adding all that scientific accuracy that we want from our data for the sort of primary purposes. And again, that was taking 30 minutes, 3 hours for the first stage, and under 6 hours when I did this presentation about a year ago on the simple stage. Unfortunately, by the end of last year, simple stage, the candidate stage, was still taking about the same amount of time, but the simple stage was taking considerably longer, sometimes more than 24 hours. And that meant that all the reporting and the website and everything was delayed. It was impacting the feeds that we provide data to scientific community and to space agencies, and that was all being impacted. And it really wasn't acceptable. So we're focusing on that first stage. And you can think about the first stage really as being the simple processing that we were doing after the candidates had been created. So on the left, you've got the candidates being created, and then they were passed immediately to the simple stage, which would process them. What we're doing now is we're going to save the candidates to disk, and that's a pretty quick operation, save them to disk, and then multiple nodes will come in and multiple computers will collect some candidates from that folder, process the candidates, and upload the results back to the server. And the server can do the same thing as well. And what this means is that we can spread the load across multiple computers within the university network. And so if the load gets too heavy for the server to manage, Denis can find another computer somewhere, fire it up, get it to solving some simple solutions and uploading them to the server, and the server will go off and do the Monte Carlo stuff in the background on the solutions that have been uploaded. So that's, in a nutshell, what we're doing. This is what it looks like at work. So if you look at the middle of this image here, you can see that, I should mention, by the way, the solver runs in a loop. So it runs 24/7 continuously, going back through the last 7 days worth of data to look for new observations that need to be examined and tested against the existing data set. So it's constantly running in the background. And what you can see here is that it started running through one of its processing loops. It's connected to the server, it's found some candidates, and it's downloaded those candidates, and it's going to process them. And here it's starting to process those 5 candidates. Now there are 5 candidates, it's starting to process them. And here is the end of that job. It's finished processing them, but it's only found 4 solutions. The 5th one failed. And there could be any number of reasons why it failed, but it's most likely it failed because the solution wasn't physically realistic. You know, the meteor, it might have been 2 observations that were just by coincidence at the same time, and they weren't really of the same event. Many ones failed. And here you can see it uploading the 4 solutions back to the server, along with the local copies of the database, which contain information about the observations that were used and the trajectory that failed. And that will then get added to the database on the server, so that next time we come around the loop, we won't try to resolve this same failed solution, unless we've got a new observation that might add value to that solution, in which case we will try again. So that's the basics of how the distributed part of it works. As part of that, we've changed the database, and I'll tell you a bit about the database just for interest. Currently, the solver uses a large text file as a database. It stores the last 3 months of observations and the failed and successful trajectories in a format called JSON. If you're a computer programmer, you'll be familiar with JSON. But you can think of it just like a kind of an indexed form of a text file, where there's like something that says what this entry is, and then the various parts of it are listed. I'll show you an example in a second. However, that database is growing by about 500 megabytes a month. It's very slow to load, it takes a lot of memory, and it does not support multi-user access. So when I mentioned before about having multiple nodes processing data, that would not be possible with the stuff stored in a JSON database, or would be very difficult at least. The live database, which just contains the last 3 months, is 1.3 gigabyte file, and you can imagine how slow that is to load. The other problem with it is because it's in memory, it's loaded into the memory of the computer. Can't share it with other computers. So if I make an update, if I find a new solution and I update the in-memory copy, that's not saved to disk until the processing run is finished. We can't save it more frequently because to save a 1.3 gigabyte file takes maybe 5 minutes, and it's just too slow. Here's an example of what the database looks like at the moment. This is literally a text file with a series of what are called key value pairs. So you can see that this is got a path to the solution. We've got this is a failed trajectory, so you can see the date in Julian format, gravity factor, ignored stations, and so on and so forth, all the data that we've got about it. So we have replaced that with a SQL database, SQLite database. This is much faster because we don't have to load the whole database into memory at startup. It supports concurrent reads, so multiple threads can read from the database, multiple processes can read from the database, and it takes up a lot less space on disk. It doesn't support concurrent writes, but that doesn't matter because of the way the solver works, and we've been able to work around that limitation effectively. And also SQLite has a kind of a process that if two processes try to write to it at the same time, one of them will back off and wait for the other one to finish. So although it doesn't support concurrent writes, it does allow us to do what we want to do. So this is great. It allows us much faster startup. We don't have to spend 5 minutes loading a huge JSON database. It takes up much less memory because we haven't got to put 1.3 gigabytes of database into memory. And crucially, it allows multiple processes to share the data, because when we update the SQLite database, that change happens immediately on disk. And that means that another process can immediately retrieve that data and do what it needs to do. So for example, the final phase, the Monte Carlo phase, can start picking up solutions straight away as soon as they're written to the database. It doesn't have to wait maybe 2 to 3 hours, maybe 24 hours for the simple phase to finish. Okay, so that's pretty much it. In summary, we're reworking the whole solver to scale horizontally across multiple computers within the university. Both the initial, simple, and the Monte Carlo stages can now be distributed. We're using standard distribution mechanisms for the data, but already used by GMN. So, for example, using SFTP. The database has been converted to SQLite, allowing for faster performance and more concurrency. And the approach is extensible. So, most of the time, GMN will only need one computer to run on, but during busy meteor showers, we can add a second or a third or a fourth, as many as Denis can get his hands on in the department, and they can share the load and keep things running at appreciable speed. And this approach is all extensible beyond this. If we do want to start using compute outside the university, this would potentially allow us to do that. Okay, that's about everything I wanted to say. Unfortunately, as I said, I can't answer any questions right now, but if you do have any questions, or if you're interested in understanding more about this, do feel free to contact me through groups.io, or if you have my email, then drop me an email, and I'll be happy to answer any questions. Thank you very much for your time.
All right, and that was Mark's talk. Yeah, this is very necessary. So the solver and the pipeline are no longer late, and we can maintain operational efficiency. So as you can see, there's a lot of avenues avenues of improvement, and that ends our regular programming and the talks. There are maybe a few other things to show in terms of technical things, but this is the unstructured workshop and the Q&A where you're free to raise any concerns, ask any questions about anything, and maybe I guess for Yleana's sake, I can show you the Lux meter results if you don't mind. Let me see, SkyFit, no. So this is the work that was done by the folks in New Zealand. Absolutely brilliant work. Let's see, these are the slides. So essentially the problem is that the GMN cameras saturate quickly, and getting unsaturated light curves is, well, pretty much impossible. So let me share my screen. So some of you've already seen this during the first session, but I'm going to share my desktop again. All right. So there was a very, very bright fireball on 4th of February, just a few days ago in New Zealand. So here are the frames, the video frames up top. It started fairly bright, then brightened even more, and it had a giant flare that saturated half the cameras in North Island in New Zealand. And at the end, you can see some final fragments here. And if we didn't have the Lux meters that the guys installed there, it would be extremely difficult to get the unsaturated light curve of this object. And you can see this is the raw data coming out the instrument. There's this apparent luminance in Lux, and you can very clearly see the excursion from the background that I manually selected into software, and then based on our calibration technique, you can convert this into magnitude. And this one had a peak magnitude of -21, which is extremely bright. This was a super bolide. And the integrated brightness allowed us to estimate the initial mass, about 20 tons, or convert to a diameter, assuming rocky composition was about 2 meters. So this was a fairly significant object that showed up in some satellite data as well. And I'm sure that there is infrasound data for this object. And yeah, installing these kinds of instruments in Japan will allow you to do the same thing and confirm the relationship between the blast radii and the scaling laws used for infrasound, and validate it on optical data.
Thank you for sharing this. This is great, actually. I will do more research and look into this. And yeah, it's been quite a struggle working with oversaturated camera data and trying to get usable information from that. So this would be very helpful.
Yeah. And each lux meter is $10 connected to a Raspberry Pi Zero. It's very, very cheap. The only downside is that it's only 10 samples a second, but it's going to give you the total absolute light curve, and the mass is going to be correct. Maybe these peaks are even sharper. Maybe you can't resolve all of the details in the light curve, but it's a really good first step. And I believe that the lux meter design has 3 stages at 3 gain levels. But looking at this now, I'm not even sure that additional gain levels are necessary, considering that this one has done such an amazing job. And this is the most sensitive level. So as you can see here, the limiting magnitude that you can see is maybe like minus 10, 11, 12, really depending on how close the fireball is. And one thing to keep in mind is this was actually quite far. So the fireball here at the peak was a few degrees above the horizon. But there are ways to make the calibration. It's all integrated in WMPL essentially. So. All right.
Wonderful.
And I think you might want to reach out to Terry, which I'm not sure if he's here on this call, but the folks from New Zealand can definitely connect you to the right people. All right. And I have another cool feature to show. So it's another SkyFit feature that we did not cover yet, but it's a part of the, how do I turn this off? Okay. But it's a part of the recent updates. Here's my desktop, the schedule, 51. So essentially, there's been a massive proliferation of satellites in low Earth orbit, and some of you might have noticed satellites in your imagery. And if you ever wanted to know which satellite you're looking at, well, that was quite difficult. And then we just added a feature where you can download a satellite catalog, project it in Skyfield, and identify individual satellites. There's one problem with this, and that is that the satellite catalog, it's not like a star catalog. Satellites don't stay put. Their orbits change frequently, daily. So essentially every day you have to download the satellite catalog and then keep a database of past orbits if you want to go back in time and check the data. But there are features in RMS and scripts in RMS that can do that, to download a satellite catalog and save it in a cache. But it's all been fully integrated in SkyFit. However, when you call the SkyFit option to show satellite tracks, it will only download the latest catalog unless you have a previous satellite catalog saved in the database for the date of interest. So here, I have some data from Australia that I pulled from the server from about a week ago. And then I just called SkyFit in the usual way, and I just add sat tracks, the sat tracks option. And I'm going to run this. And yeah, open, and then I can see here, let's read what it says, essentially saying it's looking for the satellite catalog file, and it found the one from February 1st. With the time difference between the data and the catalog about 27 hours, which is the closest one it has. So it means that the orbits are going to be slightly different. And then it runs the satellite predictor and it plots all the satellite tracks. So what I'm going to do now is I'm going to do auto levels, and I'm going to switch to max pixel, so it shows all the brightest things. And I believe picture 51. Yeah, so if you change the frames, it's going to compute satellite tracks, and it may take a long time. So I'm just going to disable this feature for now, and then go to image 51. That's the one. All right. So you can see a few satellite tracks here. Let's look at this one here. And let's try to identify these satellites. So I'm going to hit show satellite tracks. And it's going to crunch the numbers in the background. And bam, there we go. So this one is Starlink, this number. And there are actually two tracks here. Two Starlink satellites. The exact numbers. And then if I go to the next frame, it's going to compute the tracks for these, and it's going to tell us which one is which. And yep, there's Starlink this one, and this one here. Maybe one upgrade that we can do is if you click on the name of the satellite, it's going to open up the satellite ID page with more information. But yeah, that's a little feature for now. And this one here, you can see it's maybe a bit off because the catalog is old. These are the Huolian Wang Chinese satellites, which seem to be as bright as Starlink's. And you can also see there are a bunch of other satellites which aren't super bright, but it's essentially showing everything in the field of view, including MEO and GEO satellites, which we definitely can't see. They're way too faint. So FYI, another cool feature in Skyfield. All right. Okay, we have a couple of questions in the chat. Okay, we have Dave. Dave, go ahead, and then we're going to go get back to the chat.
Yeah, just to say that the new work in SkyFit is absolutely amazing. It's working on the GUI style code is a lot harder than the stuff that just runs as a process in the background. Yeah. It's a costly amount of work. It's phenomenal. It's a brilliant achievement, and I'm not just stoked that you've got the automatic plate pile fit working. If you'd written it as like a background script, that would be cool, great. But getting it to work in SkyFit, showing the star names, showing satellites, things like that, that is just a phenomenal piece of work. A year ago, people writing to me saying, oh, that bit of code you've written that jumps to the next star in the least densely populated region is really cool, going to save so much time. I mean, I'm stoked that you rendered that code virtually obsolete with the new work that's been done. I think it's fantastic.
Thank you for the kind words, Dave. Yeah, the automated star fitting was really interesting. Luke started working on it and was using methods in scikit image. And talking to him was like, no, like this is just it's not powerful enough. And then I do a Google search, and the first thing that comes up is, using image registration using a RANSAC. And I felt ashamed before because I have a master's degree in computer vision, and that is exactly like there was a topic of 2 courses that I took, which is exactly that, which I completely forgot. And then I looked it up and thought, this is exactly how to solve this problem. The image registration using RANSAC is like it, and it worked out the box. Luke tried it, it's like, yep, it works. It's like that's the solution. So it was there staring at us in our face for a long time, and it works. Yeah, it works brilliantly.
Great.
Yeah.
Have I lowered my hand? I think I have.
Yes. Yes, you did. All right. Thank you for the kind words. All right, so we have a couple of other questions. Can the GMN predict debris fields for re-entering anthropogenic stuff? Yes. If we observe a re-entry, if we see the end of the re-entry, then we can feed that into our dark flight stuff, and it's the same as a meteorite. We would just need to have a rough idea of the end mass. We probably have a rough idea of the density of the object, and we just put it in our dark flight code, and yeah, no problem whatsoever. The only problem with re-entries is they have extremely low entry angles, which means the strewn fields are massive. We're talking about tens of kilometers of the probability ellipse. So yeah, in terms of trying to find some debris from a re-entering satellite based on that would be extremely difficult, unless there's a lot of debris. But I think there aren't sufficient observations that we can kind of go and see. Of course, the Holy Grail would be, we observe a re-entering satellite, the end of a re-entering satellite with our cameras. We compute the dark flight and we go out and recover the piece and we can connect it and blah, blah, blah. And that would be exciting, and probably it's going to happen within the next couple of years because the number of satellites that went up has been steadily increasing. But we have to keep in mind that all of the Starlings that were launched in low Earth orbit, their average lifetimes are about 5 years. And they were started being launched in 2019, 2021. 5 years is coming up. So in the next couple of years, we're going to start seeing a lot more re-entries. Essentially, if you look at the number of launches on satellites in low Earth orbit, you just add a kind of a 5-year delay to that. And that's, how long is it going to take for that stuff to start coming down? Bill, go ahead.
Yeah, would it be good enough to say eventually issue predictions that say FAA or it could be used for hazards?
Right. So, there already are what are called TIPS. The Space Force actually issues, or Space Force, NORAD, issues reentry predictions or reentry notices. And there are already, the European Space Agency does that, and a couple of other people already published this online. The problem with reentries is that it is the uncertainty in the reentry time and location is huge. We're talking about like a whole orbit or half an orbit, which is the problem is, first of all, when an object gets very low, the cone of visibility of this object becomes very small. So for example, when it's down at 100, 200, 150-ish kilometers, we're talking about a cone of visibility of a few hundred kilometers, just like with a fireball. But the problem is it's a satellite, it's still not ablating, and it has to be sun illuminated to be observed optically, and then to observe by radar, you can do it. The problem with most radars is that it needs to be within a certain range of elevations, and there are very few radars around the world. So again, because of this low cone of visibility, especially it's so close to the surface, it's just difficult to measure. It's difficult to get. And that's why, and then plus combine that with the huge uncertainties in the atmospheric density as it's plowing through the atmosphere, satellite orientation, attitude, the atmospheric uncertainty, so many things accumulate. The uncertainties are huge. And that's why the predictions are for a whole orbit or half an orbit. Are there ways to solve this? Yes. I mean, if given enough resources, we could potentially utilize GMN cameras to maybe measure re-entries before they happen, or it would have to be some sort of a different way. Yeah, in terms of impact hazard to, I guess, anything on the ground, or you mentioned FAA, which I thought you meant commercial aviation. There is essentially no risk to commercial aviation from re-entering space debris. So if you look at meteorite flux to the ground, which is orders of magnitude higher than any re-entering space debris, we ran the numbers a few years ago, and essentially, given let's say that the current commercial aviation activity persists for many years, it would take 100,000 years for a significant meteorite, 100 grams or 500 grams, to hit an airplane in flight. Re-entering space debris is orders of magnitude less. So we're talking about, millions of years, given the same constant rate of flights and re-entering debris. Yeah. So that is not really a concern. The concern is that if there is a known object that is significant, that has large pieces that might fall on a populated area, and there is, I think, probably a 10,001 chance or higher that debris might hit something, that then is cause for concern. And what did I want to say? So the problem with a lot of re-entries is, how can I put it? There are a lot of people who they're absolute experts in theoretical ablation modeling of re-entering debris. So they build 3D models of satellites, put in all the equation of ablation of individual materials. They do extremely detailed modeling, hydrocode simulations, and then when they run these simulations, they can tell whether, well, let's say they can theoretically predict whether some pieces of an object might survive and make it to the ground. These are extremely advanced models run on supercomputers, very fancy physics. The problem is that there are no observations to validate the models. And there were isolated cases where these models failed spectacularly. You might remember a couple of years ago, there was you might have read in the news that space debris crashed through a house in Florida, a couple of feet away from a kid who was studying in his room, and just went all the way from, crashed through the roof and through the floor and made it all the way down. And that was essentially a battery pack released from the ISS, and all the models said it should have completely burned up in the atmosphere.
Yeah, rocks are easier.
Rocks are easier, right? Well, there's more data on rocks. That's the thing. So yeah.
Thanks.
We might get there with re-entering space debris at some point, but it's all about data and validation and measurement, and yeah. All right. Let's see. Oh, there might be more stuff here in the chat. Let's see. Steve says there was a video the fireball Dennis just talked about from Wellington. Yeah.
No, correction. That was the Canterbury event. We had a flurry of events, and I got confused.
Yes. Yeah. So there were, I think, 3 major fireballs in New Zealand in a matter of days, and yeah, the latest one was the biggest one.
Yeah, and most of the security videos of that just are like our GMN cameras, are just huge, just a monstrous big flash.
Yeah. And that's why let's say the classical approach of, well, as I said before, the fireball detector needs to be overhauled. But that's why having raw videos saved makes all the difference for these, because they don't suffer for any compression from most of the compression artifacts. So yeah. All right, so let's see. Tomic says, what can you do to eliminate the risk of oversaturated images of bright fireballs, other sensors, camera parameters? Yeah, I mean, this is a great question, right? Like, how do you get the details of a fireball that's very bright and saturating these cheap sensors? I would say if you're very serious about it, you should get a DFN camera that the Hadrien and his crew operate, and these are brilliant fireball detectors. They get much more detail in the brightest parts than GMN cameras do. They cost more, but those are really the instruments definitely to use. So, yeah, I mean, otherwise you could potentially deploy cameras that that are where the gain is not cranked up as high. But then the problem is how to calibrate that camera. You might need to dynamically change the gain. For example, every hour or so, you crank up the gain to get some calibration stars, and then you bring it down in the less sensitive mode. That would be another possibility. Or you could potentially have, let's see, have a system with 5 or 6 cameras that are very sensitive, but then you operate one camera with a fisheye lens that is not as that is not sensitive at all and doesn't have the resolution. However, it will give you fairly accurate positions at the brightest points. But again, you need to run the kind of the data collection and calibration, the calibration step. So kind of crank up the gain, or maybe do a longer integration every hour or so to collect some stars, just to have something for calibration. And then otherwise operate it in like an extremely insensitive mode. That would be one way of doing it. But even then, if you have something that's like magnitude like -20, yeah, that won't help. So for example, when we had the Nova Mesto fireball, there was a daytime super bolide, and it was caught by dash cams. It was early in the morning, and it was very bright out. The dash cam was running at like 25 frames a second, but the exposure time was 1/1000th of a second. And the ISO was very low. And even then, when I was looking at the fireball, it was pretty big saturated blob during domain fragmentation. So I'm not sure what you'd get if you ran a camera overnight at 1/1000th of a second of exposure. It would just be, you can try, I guess, but yeah. Great question. Yeah, let's see. So Gene says, all right, so I think Gene had another question which we unfortunately skipped. I want to go back to that. Yeah, so you're curious if Sam's classification method can be connected to ternary elemental diagrams using spectral data. And I replied, yes, so the plan is to observe meteors using like high quality science grade cameras, invert their physical properties using advanced ablation models, and get spectral data, and then see what kind of parameters Sam's model spits out. If we can reliably connect the two, it means that we no longer need to use those advanced techniques. We can only, based on those observables, the height, the speed, the acceleration, et cetera, they can be used as evidence and kind of indicators of density and strength, et cetera, et cetera. So, Dave has a question. Dave, go ahead.
You keep talking about high-grade science cameras.
Yeah.
The cost for me is getting a location where I can install equipment.
Yeah.
Installing better equipment at that same location is quite doable, I think. I mean, are we talking an order of magnitude higher, 2 orders of magnitude higher in cost? To build a really good system, what is it?
Yeah, I mean, if you want to start, you see, it's a struggle, right? It's really strange that you can get these cheapo 291s, 307s for like $30, and they're incredibly sensitive. If you get the same sensor in an industrial camera, it is terrible. It is not sensitive at all. We have no clue why. I think they just don't adjust the gain in the same way in the factory. It's just for a different application, I presume.
Yeah.
So first of all, it's just hard to find a science grade camera that is as sensitive as these incredibly cheap sensors. I have no clue why that is. But let's say you are able to find something that is, let's say, 12, 14 bits instead of 8 bits. And it's either USB or Ethernet, whatever, and you connect it to RMS. What that gets you is no compression, linear response, potentially higher FPS and a higher dynamic range. So you're no longer saturating very quickly. 8 bits is a tiny dynamic range. And the lack of compression means that you're going to get cleaner meteors and better measurements. So for example, I'm not very confident that the GMN photometry is solid. For fainter meteors, we can show that it's okay within maybe a third of a magnitude. But for science grade applications where you want to be fitting ablation models, you want to make sure that's within like a 0.1 magnitude or better. And that's where science grade cameras come in. And also, they won't saturate near the peak. So you access more meteors. The problem there is higher data requirements. So essentially, you would have to save raw data to disk in some sort of a format and then process that instead of either MKV videos or FF files, et cetera, that are currently integrated into ArtMS. Ideally, we would have something similar to the Preacher software developed by Freepon, where individual video frames are saved as fit files, and then RMS runs in those instead of videos or whatever. That's, I would say, a fairly easy modification that can be made. Yeah, so that's one. And the second is getting very accurate timing. Ideally, having like a camera with onboard timestamping for various applications for meteors, fireballs, and other things. Right now we're kind of getting away with the timing that we have, and we're aligning time between cameras to get an estimate. But it would be nice if we can get kind of a full-on proper timing. Yeah, and if you really want to do really cool science and you have a lot of money, you're getting at hundreds of thousands of dollars, then you can get like an EMCCD camera that Justin talked about in the first session, where it's like a photon counting camera running at 32 frames a second and sees meteors down to like magnitude +8. But that's a completely different story. But just the fact that we can support these kinds of science cameras, I think would just open up more possibilities. But yeah, sorry, I don't think I answered your first question. That's how expensive that would be. You can probably get a fairly good science grade camera, and by science grade I mean it doesn't have all sorts of compression or of sorts for $500 to $1,000 for one camera.
Yeah, that's kind of prohibitive for building a network of 20.
Yes,
that's a decent car.
Yes, absolutely, that's for sure. But deploying a few for special purposes, you can get away with that.
That's doable.
Yeah. All right, a couple of other comments. Let's see. Yeah, so Gene says, past October, a Boeing 737, I believe it was somewhere in Colorado, suffered a shattered cockpit window. Yeah, so this was a weather balloon by a startup called Windborne. And I believe I already mentioned them during the first session. So essentially what they do is, they realize, we're launching a weather balloon. We're doing radio sondage. We connect the little packet, we connect to a balloon, we send it, it flies for tens of minutes, the balloon goes up all the way to the stratosphere, pops, and then that's it. What they decided to do is to add just a little valve to the balloon and I believe ballast. And then they just send the balloon up. It has a pressure sensor, and then it gets rid of some gas, goes down, and then once it reaches a certain altitude, releases some ballast, goes up again, and it stays up for weeks on end. And now they have a network of hundreds of these balloons flying across the world at all times, and they're sampling sampling the atmosphere in an unprecedented way. And because they have so much, how can I put it there? It's called a collisional cross-section, let's put it that way, is so big relative to other things such as space debris and meteorites and even normal radiation balloons. It just happened that one of those collided with an aircraft. It's interesting. Luke said once that the only thing he's ever seen in his 30 years of flying is a weather balloon zip by. Well, he zipped by in a jet next to a weather balloon. So it makes sense that was it. And I think it was actually confirmed by Windborne that was the problem. All right, yeah, I see the link. Yeah, to the ISS space junk crashes into home. Yeah, that one's fun. Yeah, ND filters. That one's pretty interesting. Yeah, yeah, you can definitely put an ND filter on a camera. And I guess, if you calibrate it and you know exactly where it's pointing, you can. I just rather do it in the software. Just change the exposure time of the software, and that makes it more configurable and more dynamic. Because that way you can increase the sensitivity if you need to collect calibration data. All right. All right. Any other questions and suggestions? Topics for discussion? All right. Well, if not, I am going to conclude this meeting. And thank you all for coming. Make sure to watch the first session if you haven't seen it yet. Quite a few interesting talks there. And if you're wondering what's up with this new contrail push, everything is explained there. And yeah, that's it. So thank you for coming to the meeting. It was another wonderful session, and see you all next year, if not sooner. So, all right. Thank you and bye.
Bye all. Thank you.
Bye-bye from Scotland.
Yep.
Thank you.
Bye, Jamie.
Thank
Good
you all.
night.
Thank you.
Bye.
Good night. Bye.
Go to meet Jamie.
Yeah.